The Senior or Staff DevOps Incidents Masterclass, Volume 2.
In Part 1, we mastered the platform, the delivery pipelines, and the internal developer experience. But today, we leave the world of YAML behind and enter the ghost in the machine. We are moving from high-level automation to low-level systems engineering. Part 2 focuses on the incidents that happen at the kernel level, the database consensus layer, and the complex boundaries of cloud networking. This is where we separate the operators from the architects.
Part 1 Recap the Foundation.
Before we dive into the abyss, let us look at what we have already covered. In Volume 1, we analyzed 34 high-scale incidents across 8 categories, including Kubernetes orchestration failures, CI/CD delivery gaps, and the hidden traps of infrastructure as code. We established the debug framework as our forensic standard. If you have not watched Part 1, we highly recommend finishing that foundation before entering the hardcore distributed theory of this volume.
Part 2 The 8 Chapters of Distributed Catastrophe.
We are continuing our journey with 49 additional scenarios across these final 8 pillars. Category 9, Advanced Cloud Networking and the Edge, Mastering Traffic Flow and Protocol Level Failures. Category 10, The Kernel Abyss and Interface Scaling, when the Linux kernel and CNI reach their physical limits. Category 11, Data Strategy and Stateful Survival, Protecting the Database and Persistent State from Destruction. Category 12, Distributed Messaging and Consensus, Managing Consistency and Flow in Distributed Architectures. Category 13, High-Scale Performance Engineering, Advanced Compute Bottlenecks and Observability at Scale. Category 14, Cloud Economics and Regional Resilience, Managing the Cost of Scale and Provider-Level Failures. Category 15, Identity, Security and Supply Chain, Zero Trust Architecture and Identity-Based Breaches. Category 16, Multi-Cluster Federation and Chaos, Managing Fleet-Wide Operations and Resilience Testing. Every scenario continues to use our 9-step framework with elite interview follow-up challenges. Category 9, Advanced Cloud Networking and the Edge.
Focus, Traffic Flow and Protocol Failures at the Cloud and Mesh Boundary.
The network is the computer, but it is also the most fragile part of a distributed system. In this section, we deal with the failures that occur when your architectural assumptions meet the reality of packets, sockets, and cloud provider limits. We will explore why copy-pasted proxy configurations break modern protocols, how default DNS settings can DDoS your own control plane, and the silent packet drops caused by asymmetric routing in complex cloud VPCs.
Category 9 Incident List.
We begin Category 9 with these 7 high-stakes networking forensics. 35. The Cargo Cult Ingress Trap, copy-pasted timeouts breaking WebSockets. 36. Intermittent DNS failures, N.:5 overhead overwhelming core DNS. 37. Service mesh misrouting, complex Istio and Envoy virtual service conflicts. 38. TLS regional failures, missing intermediate CAs in specific regions. 39. Latency from N+1 calls, architecture-level chatty calls causing 5-second page loads. 40. SNAT port exhaustion, outbound port depletion at the NAT gateway. 41. Asymmetric routing, packet drops caused by mismatched return paths in VPCs. Let us start with the danger of blind copy-pasting, the Cargo Cult Ingress Trap.
The Senior DevOps Incident 35, The Cargo Cult Ingress Trap.
Marketing team has just launched a highly anticipated live support chat feature. Within minutes, thousands of users are complaining that the chat window keeps closing and reconnecting every 60 seconds. The developers insist their Node.js code is stable and the pod logs show no errors. You look at the Nginx ingress controller and the traffic is flowing, but connections are being violently severed. You have fallen into the trap of cargo cult engineering, where a copy-pasted configuration from 3 years ago is now sabotaging your modern real-time protocols.
Symptoms, the panic moment.
Here is the behavior of the network edge during the WebSocket instability. 1. Client experience, browser consoles show WebSocket error code 1006, abnormal closure, at exact 1-minute intervals. 2. Ingress access logs, Nginx reports HTTP 499 status codes, indicating the client closed the connection, or 504 gateway timeouts. 3. App metrics. Pod CPU and memory are near idle. The backend is not under load. 4. Load balancer. The cloud load balancer in front of Kubernetes shows a spike in active connection resets. The connections are not timing out due to load. They are being terminated by a hard-coded policy at the proxy layer.
Hypothesis, thinking like a senior.
A junior engineer might try to add more replicas to the ingress controller. As a senior, I analyze the protocol lifecycle. Hypothesis 1, application level keep alive failure, ruled out. The Node.js server is configured to send heartbeats every 30 seconds. Hypothesis 2, cloud load balancer idle timeout, ruled out. The AWS ALB idle timeout is set to 3,600 seconds. Hypothesis 3, proxy buffer timeout. The ingress controller is using standard HTTP timeout values for a long-lived stateful WebSocket connection. Decision tree signal. If connections drop at perfectly regular intervals like 60 or 90 seconds, while logs show 499 errors, then always suspect a proxy-level timeout configuration. Investigation. The 6-step debugging masterclass.
Step-by-step edge forensic work.
We must verify the exact Nginx directive that is killing the streams. We execute these steps. 1. Inspect ingress manifest. We examine the annotations on the chat service ingress object. We see standard settings for SSL and CORS. 2. Dump Nginx config. We exec into the ingress pod and run cat/etc/nginx/nginx.conf to see the generated server block. 3. Search for timeouts. We search the configuration for timeout values. We find proxy_read_timeout and proxy_send_timeout are both set to 60 seconds. 4. Trace the source. We check the global config map for the ingress controller. We find these 60 seconds values were inherited from a legacy standard web template created years ago. 5. Correlate with heartbeats. We realize that because the app heartbeat is 30 seconds, but Nginx expects a read within its buffer window, any slight network jitter causes Nginx to close the idle stream. 6. Root cause identified, protocol config mismatch. The Nginx ingress was configured for short-lived REST requests. WebSockets require much higher read and send timeouts because they represent a single stream that may be silent for minutes between messages. Let us look at the evidence in the generated Nginx configuration. The evidence, the legacy timeout trap. This directive defines how long Nginx will wait for the upstream pod to send data. If no packet is received for 60 seconds, Nginx closes the connection. For WebSockets, this is far too aggressive.
The fix, protocol-specific tuning.
We must increase the read and send timeouts specifically for the real-time routes to allow long-lived streams. Senior warning, do not increase the global Nginx timeout to 3,600 seconds. This will cause ghost connections from dead REST clients to hang around in memory for an hour, eventually exhausting your connection pool and triggering an OOM kill on the ingress pods. Here is the YAML implementation for tuning Nginx ingress annotations for WebSocket support. Disclaimer, always test code in a non-production environment. By applying this annotation to the specific ingress object, we tell Nginx to allow this connection to remain open for up to 1 hour even if no data is being sent. This immediately stops the 60-second reconnection loop.
Prevention and guardrails, the post-mortem.
To prevent cargo cult configurations from breaking future features, we implement these guardrails. 1. Config drift linting. We use confdest in our CI/CD pipeline to verify that any new ingress object using WebSockets also contains the mandatory timeout and upgrade annotations. 2. Vertical probing. We add a synthetic probe that specifically tests WebSocket handshake and persistence, alerting us if a connection is dropped before the 5-minute mark. 3. Documentation as code. We move away from wiki templates and move toward Helm library charts that have a WebSocket Boolean flag, which automatically injects the correct hardened settings. A senior engineer knows that there is no such thing as a standard network config in a microservice world. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Why does Nginx require a proxy_send_timeout in addition to a proxy_read_timeout for WebSockets?
Answer, a WebSocket is bidirectional. Proxy_read_timeout controls the silence from the backend pod to Nginx, while proxy underscore send underscore timeout controls the duration between successive write operations from Nginx to the backend pod. If either direction exceeds the timeout, the TCP socket is closed. You must tune both to ensure symmetry in long-lived streams.
Senior follow-up 2, the scale and trade-off trap. You increase the timeout to 3,600 seconds. How does this affect your rolling update strategy for the Ingress controller pods?
Answer: it significantly slows it down. During a rollout, Nginx tries to gracefully drain connections. If you have thousands of WebSockets with 1-hour timeouts, Nginx might wait a very long time for them to close. You must tune the worker shutdown timeout to force close these connections after a reasonable window, for example, 5 minutes, to allow the rollout to complete.
Senior follow-up 3, the Day 2 migration reality. You are moving to a service mesh like Istio. Does the Nginx timeout annotation still work?
Answer: no. In a service mesh, the Envoy sidecar becomes the new in-cluster proxy. You must migrate your timeout logic from Ingress annotations to Istio virtual service and destination rule objects. The HTTP timeout field in the virtual service is what will now control the stream lifecycle.
Senior follow-up 4, Curveball. You have perfect timeouts. Yet users behind a corporate firewall still experience 60-second drops. Your Ingress logs show 0 errors. Where is the connection being killed?
Answer: the client-side proxy. A senior engineer knows that the path from the user to the pod is long. The user's corporate office likely has a deep packet inspection (DPI) firewall that terminates idle TCP connections aggressively. The fix is not in your infrastructure. It is in the application code. You must implement aggressive application-level keep-alives, pings, every 20 seconds to keep the intermediate proxies alive.
Pro tip, the WebSocket protocol header.
Never assume Nginx will automatically upgrade a connection. Always ensure your configuration explicitly passes the upgrade and connection headers. Without these, modern L7 proxies will try to parse the WebSocket traffic as standard HTTP/1.1, leading to massive memory corruption in the proxy buffer and intermittent, impossible to debug 502 errors.
The Senior DevOps Incident 36, the N.:5 Core DNS DDoS.
It is Monday morning. You are seeing a mysterious 5-second latency spike for every outbound API call to AWS S3 and Stripe. Your Node.js and Python applications are timing out. You check the network. It is fine. You check the external API providers. They are 100% healthy. You look at the core DNS pods in your cluster, and their CPU is pegged at 100%. Your cluster is effectively DDoSing its own DNS server, and every external request is being penalized by 5 seconds of total silence.
Symptoms, the panic moment.
Here is the data that revealed the DNS congestion. 1. Application logs, DNS resolution timeout appearing for external domains like stripe.com. 2. Core DNS metrics, the DNS underscore request underscore count underscore total is 10 times higher than the actual number of user requests. 3. Latency profile. External resolutions consistently take either 10 milliseconds or exactly 5005 milliseconds, 5 seconds. 4. Cluster events. Core DNS pods are frequently being OOM killed or throttled due to CPU saturation. The system is trying too hard to find things that do not exist, leading to a massive amplification of DNS traffic.
Hypothesis, thinking like a senior.
A junior might try to increase the number of core DNS replicas. As a senior, I analyze the search path logic. Hypothesis 1, core DNS cache is too small, ruled out. Increasing the cache size has 0 impact on the CPU load. Hypothesis 2, upstream DNS AWS or GCP is throttling us, ruled out. Direct lookups from the worker nodes are sub-millisecond. Hypothesis 3, DNS search path over traversal. The default Kubernetes N.:5 setting is forcing the system to append internal cluster domains to every external lookup. Decision tree signal. If external DNS lookups take exactly 5 seconds and core DNS CPU is spiking, then always suspect an N.search path issue. Investigation. The 6-step debugging masterclass.
Step-by-step DNS forensics.
We need to see the path of a packet. We execute these steps. 1. Run TCP dump on core DNS. We capture DNS traffic and see that a single request for google.com triggers 5 separate lookups. 2. Analyze the queries. We see the queries google.com.namespace.svc.cluster.local, then google.com.svc.cluster.local, and so on. 3. Check pod configuration. We run cat/etc/resolve.conf inside an application pod. We find options n.:5. 4. Identify the logic in Linux. If a domain has fewer dots than the n dots value, it first tries all search paths before trying the actual domain. 5. Measure the failure. We realize each failed internal lookup takes 1 second to timeout. 5 failed lookups equals 5 seconds of latency before the final successful external lookup. 6. Root cause identified. DNS search path exhaustion. Because google.com only has 1 dot and n dots is 5, Kubernetes forces core DNS to check 5 non-existent internal domains for every 1 external request. This creates a 10 times traffic multiplier on core DNS, crashing the control plane. Let us look at the packet capture that exposed the DNS multiplication. The proof: DNS search path probing. This is the default Kubernetes setting. It means any domain with fewer than 5 dots, like stripe.com, will be treated as an internal service first, triggering a cascade of useless queries.
The fix: implementing Node local DNS cache.
We must reduce the load on the central core DNS pods by implementing a caching layer on every single worker node. Senior warning: do not just change n dots to 1 in your pod spec globally. While this fixes external latency, it will break internal service discovery. For example, my service will no longer resolve unless you use my service.namespace.svc.cluster.local. You must implement a smarter caching layer. Here is the YAML implementation for deploying Node local DNS cache to solve DNS amplification. Disclaimer: always test code in a non-production environment. By deploying a DNS cache on every node, we intercept the n-dot search path lookups locally. Instead of 5 network calls to the core DNS pods, we have 5 local memory lookups. The 5-second latency vanishes.
Prevention and guardrails: the post-mortem.
To protect our DNS layer permanently, we implement these guardrails. 1. FQDN enforcement. We mandate that all external API calls in our application code use a trailing dot, for example, api.stripe.com. This tells the Linux resolver it is a fully qualified domain name and to bypass the n-dot search path entirely. 2. DNS autoscaling. We implement the cluster proportional autoscaler for core DNS, ensuring that as the number of nodes or cores in the cluster grows, the DNS capacity grows linearly with it. 3. Core DNS metrics alerting. We set a Datadog alert on core DNS_DNS_request_type_count_total with a focus on NX domain responses. A high rate of NX domain is a leading indicator of a misconfigured search path. A senior engineer does not just fix the latency, they fix the query amplification that caused it. The senior follow-up stack.
Senior follow-up 1: mechanism deep dive. Why does Kubernetes default to n-5 instead of a smaller number like 1?
Answer: Kubernetes aims for ease of service discovery. The n-5 setting allows developers to use short names for services, for example, database, and have them resolve across namespaces. This flexibility requires a deep search path. However, in high-scale environments with many external calls, this convenience becomes a performance bottleneck.
Senior follow-up 2: the scale and trade-off trap. You moved all external calls to use a trailing dot, FQDN. What is the risk regarding certificate validation?
Answer: SSL/TLS hostname mismatch. Some older TLS libraries treat google.com and google.com as different host names. If the library compares the FQDN with the common name, CN, in the SSL certificate, the validation might fail even if the DNS resolution was successful.
Senior follow-up 3: the day 2 migration reality. You are using Node local DNS cache, but some pods are still bypassing it and hitting core DNS directly. Why?
Answer: kubelet configuration. For Node local DNS to work, the pods must be configured to use the local IP, for example, 169.254.20.10, as their primary name server. This requires updating the -- cluster DNS flag on the kubelet or using the DNS config field in the pod spec to point to the local listener.
Senior follow-up for Curveball, you have node local DNS and low N dots. Yet, DNS resolution still takes 2 seconds for one specific Python service. You check the logs and see IPv6 ARA queries. Your infrastructure is IPv4 only. Why is this a problem?
Answer: the dual stack penalty. Many modern libraries, like glibc, perform parallel lookups for both IPv4A and IPv6 ARA. If your DNS server or network does not support IPv6, the ARA query will time out after 2 seconds before the query is accepted. You must configure the application, or the podresolve.conf, to use single request reopen to prevent the ARA lookup from blocking the response.
Pro tip, the trailing dot rule.
Teach your developers the power of the trailing dot by simply writing myapi.com. Instead of myapi.com in their configuration files, they can shave 5 seconds of latency off their application without a single infrastructure change. It is the most effective low-effort performance optimization in Kubernetes networking.
The Senior DevOps Incident 37, the Service Mesh Identity Crisis.
It is a high-stakes launch day. Team A deploys a new marketing landing page on shop.company.com. Simultaneously, Team B updates the core checkout API. Suddenly, 50% of all traffic to the landing page is being routed to the checkout service, resulting in massive 404 errors. You check the Kubernetes services, they are correct. You check the DNS, it is pointing to the right load balancer. The traffic is entering your cluster correctly, but is being hijacked by your own service mesh logic. You are facing a virtual service collision in Istio.
Symptoms, the panic moment.
Here is the behavior of the internal traffic during the routing conflict. 1. Non-deterministic routing. A single URL occasionally works but often returns the wrong service response. 2. Istiometrics. The Envoy proxy logs show UH or no healthy upstream flags for requests that should be valid. 3. Configuration state. Both Team A and Team B have synced their Argo CD applications with 0 errors. 4. Crosstalk. Landing page logs show incoming requests for paths that only exist in the checkout API. The service mesh control plane is merging conflicting rules into a single, corrupted routing table at the Envoy level.
Hypothesis, thinking like a senior.
A junior engineer might suspect a pod-level failure and restart the entire namespace. As a senior, I analyze the service graph collision. Hypothesis 1, ingress gateway selector mismatch, ruled out. The gateway is correctly accepting traffic on port 443. Hypothesis 2, pod label collision, ruled out. Team A and Team B use distinct namespaces and unique app labels. Hypothesis 3, virtual service host shadowing. Multiple teams have defined a virtual service for the same host string without using proper delegation, causing Istio to merge them unpredictably. Decision tree signal. If traffic for host A is reaching service B intermittently, and both have valid Istio configs, then always suspect a virtual service host collision. Investigation. The 6-step debugging masterclass.
Step-by-step service mesh forensics.
We need to see what the Envoy proxy actually believes is the truth. We execute these steps. 1. Analyze cluster state. We run istio-cutl analyze -a to look for cross-namespace configuration conflicts. 2. Identify the conflict. The analyzer flags a warning virtual services with the same host shop.company.com in different namespaces. 3. Dump Envoy routes. We use istio-cutl proxy config routes on the ingress pod to see the final merged routing table. 4. Inspect JSON config. We find that Team B accidentally used a wildcard host or a duplicate host in their manifest to test a feature. 5. Check pilot logs. We check the istiod logs and see conflict events during the XDS push to the edge proxies. 6. Root cause identified, fragmented virtual service ownership. Istio allows multiple virtual services to claim the same host. When they do, and both define the same root path, the behavior is non-deterministic. Team B's configuration shadowed Team A's traffic because of alphabetical ordering in the pilot merging logic. Let us look at the conflicting manifests and the envoy route dump that prove the collision. The evidence: overlapping virtual service hosts. By allowing different teams to define the same host in different namespaces, you have created a race condition. The first one processed by Istiad wins, or they merge in a way that breaks both.
The fix: implementing virtual service delegation.
We must enforce a hierarchical ownership model. We will define a single root virtual service and delegate specific paths to individual teams. Senior warning: do not fix this by just renaming a host. You must fix the permission to route. In a large organization, no team should be able to claim a global host like shop.company.com without inheriting it from a central gateway configuration. Here is the YAML implementation for Istio virtual service delegation and path-based ownership. Disclaimer: always test code in a non-production environment. This is the senior-level architectural fix. By using the delegate keyword, the platform team retains control over the host identity, while allowing sub-teams to manage their specific path-based logic in their own namespaces safely.
Prevention and guardrails, the post-mortem.
To prevent routing hijacking in the future, we implement these guardrails. 1. Strict namespace scoping. We use the export to field in all Istio objects to ensure a virtual service in the payments namespace cannot affect traffic in the marketing namespace. 2. Validating admission webhook. We configure a custom OPA gatekeeper policy that rejects any virtual service that attempts to claim a host already registered in our global service catalog. 3. Istio Analyze in CI. We integrate Istio-CUDL-Analyze directly into the Jenkins and GitLab pipelines to fail the build if a PR introduces a host collision. A senior engineer treats the service mesh as a multi-tenant platform where boundaries must be mathematically enforced. The senior follow-up stack.
Senior follow-up 1. Mechanism deep dive. How does Istio's pilot handle conflicts when multiple virtual services define the same host?
Answer: Istio attempts to merge them. However, if multiple virtual services define conflicting rules for the same matching criteria, such as the exact same prefix path, the behavior is undefined. Usually, pilot picks one based on the oldest creation timestamp, but this can shift during a control plane restart, making the failure seem intermittent.
Senior follow-up 2. The scale and trade-off trap. You implemented sidecar resources to restrict configuration visibility. What is the performance trade-off?
Answer: memory and CPU savings versus operational overhead. By default, every Envoy sidecar receives the configuration for every service in the cluster. Sidecar objects limit this to only necessary dependencies, which drastically reduces the RAM usage of your pods. The trade-off is that you must now manually maintain a list of dependencies for every microservice.
Senior follow-up 3. The Day 2 migration reality. You are migrating from Nginx Ingress to the new Kubernetes Gateway API. Does this collision problem still exist?
Answer: the Gateway API solves this through HTTP route attachment. It uses a parent or child relationship where the gateway explicitly allows or denies an HTTP route from attaching based on its namespace or labels. This moves the security from undefined behavior to explicit permission.
Senior follow-up 4. Curveball. You have perfect virtual services and no collisions. Yet the checkout API is still receiving traffic meant for the search API. You check the Envoy logs and see the host header is correct. Why is the routing still wrong?
Answer: hidden cause. This is service port collision. If two Kubernetes services use the same port number and your Istio sidecar configuration is not using MTLS or SNI-based routing, the underlying Linux IP tables might be forwarding traffic based on the IP and port alone, bypassing the L7 host header check. You must ensure port names and numbers are unique or fully adopt MTLS.
Pro tip: the Istio-CUDL proxy status command.
When debugging service mesh routing, always run Istio-CUDL proxy status. This tells you if the sync between the control plane and the Envoy pod is stale. If your config is correct in Git but the proxy status is stale, the issue is not your YAML, but a performance bottleneck in the Istio pilot control plane.
The Senior DevOps Incident 38. The Singapore TLS handshake failure.
It is Monday morning. Your global e-commerce site is healthy in the US and Europe, but every user in the Singapore region is reporting connection, not private errors. You check the SSL certificate. It is valid, not expired, and issued by a trusted root CA. You check the US region. The same certificate works perfectly. Your US-based developers cannot reproduce it, but your Asian traffic has dropped to 0. You are facing a regional TLS chain failure.
Symptoms, the panic moment.
Here is the data from the regional network probe. 1. Client error net air_cert_authority_ invalid appearing in Chrome and Safari in specific geographies. 2. Handshake trace running curl from a Singapore-based jump box fails with unable to get local issuer certificate. 3. US verification running OpenSSLS_client from a US laptop shows verify return code 0 OK. 4. Browser logic most modern desktop browsers work, but older Android devices and specific regional ISPs are failing consistently. The certificate is technically valid, but the path required to prove its validity is missing for certain clients.
Hypothesis, thinking like a senior.
A junior might try to reissue the certificate from a different provider. As a senior, I analyze the trust chain and certificate bundling. Hypothesis 1, DNS poisoning in Singapore, ruled out. The IP returned matches the regional load balancer perfectly. Hypothesis 2, clock skew on Singapore nodes, ruled out. NTP is synced across all global worker nodes. Hypothesis 3, incomplete certificate chain. The server is only sending the leaf certificate, relying on the client to already possess the intermediate certificates. Regions with older trust stores or stricter ISP proxies cannot complete the chain. Decision tree signal. If TLS works in one region but fails with invalid authority in another means, then always suspect a missing intermediate CA in your server-side bundle. Investigation. The 6-step debugging masterclass.
Step-by-step TLS forensic work.
We must verify what the server is physically transmitting during the hello phase. We execute these steps. 1. Simulate regional request. We use a VPN or a regional Lambda function to run OpenSSLS_client against the Singapore endpoint. 2. Check the chain depth. We look at the certificate chain output. We see only S/CN equals shop.company.com and no intermediate entries. 3. Analyze US client behavior. We realize US clients succeed because they have previously visited other sites using the same CA, so the intermediate is already in their local cache. 4. Inspect Kubernetes secret. We check the TLS.crt file in the Kubernetes secret. We find it only contains a single begin certificate block. 5. Validate with CA provider. We check the Let's Encrypt or DigiCert portal and confirm that our certificate requires an intermediate CA to reach the trusted root. 6. Root cause identified. Incomplete server hello. The DevOps team manually created the Kubernetes secret using only the site certificate, forgetting to concatenate the intermediate certificates. This created a fragile trust that only works for clients with cached intermediates. Let us look at the OpenSSL output that exposed the incomplete chain. The evidence, the incomplete certificate chain. This is the definitive proof. The client received the site certificate, but it does not know who issued it. It cannot find the R3 intermediate certificate in its local trust store, so it aborts the connection.
The fix, implementation of the full chain bundle.
We must update our secrets to include the full path from the leaf to the root. Senior warning, never just upload the leaf certificate. Most modern certificate authorities use at least one intermediate level to protect their root keys. You must concatenate the certificates in the correct order, leaf first, then intermediates, then root. Here is the Bash and YAML implementation for creating a validated full chain TLS secret. Disclaimer, always test code in a non-production environment. By bundling these together, the server will now send the entire path to the client during the TLS handshake. The client no longer needs to have the intermediate cached. It can verify the chain instantly.
Prevention and guardrails, the post-mortem.
To prevent regional TLS failures in the future, we implement these guardrails. 1. Cert Manager automation. We move away from manual secret creation and implement Cert Manager with Let's Encrypt. Cert Manager automatically handles chain concatenation and renewal. 2. Chain verification in CI. We add a script to our infrastructure pipeline that runs OpenSSL verify on every certificate secret to ensure the chain is complete before it is applied to Kubernetes. 3. Global synthetic probes. We configure our monitoring Datadog or New Relic to run TLS handshake tests from at least 5 global locations, specifically including regions like Singapore and Sao Paulo. A senior engineer knows that trust is not universal. It is a path that must be provided. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why do some browsers work with an incomplete chain while others fail?
Answer: AIA, Authority Information Access, fetching. Modern desktop browsers like Chrome and Edge can see the URL of the intermediate certificate inside the leaf certificate's metadata. They will automatically download the missing intermediate over HTTP to complete the chain. However, mobile apps, curl, and older Linux-based clients do not perform this auto-fetch, leading to a hard failure.
Senior follow-up 2 the scale and trade-off trap. You added the root CA to your server bundle. What is the network trade-off?
Answer: packet overhead. Every extra kilobyte in the TLS handshake adds to the total initial round-trip time. If you have a very deep chain, for example, 5 levels, you might exceed the initial TCP congestion window, forcing an extra round trip before the application data can be sent. We should bundle the intermediates, but usually we can omit the root CA since the client must already have it to trust the chain anyway.
Senior follow-up 3 the day 2 migration reality. You are migrating to MTLS, Mutual TLS, for internal services. How does the chain problem change?
Answer: it becomes a two-way street. Not only must the server provide a full chain to the client, but the client must provide a full chain to the server. If your internal service, Mesh CA, is not trusted by the legacy apps in the cluster, you will have massive internal handshake failures. You must distribute the trust bundle to all containers via a config map mount.
Senior follow-up 4 Curveball. You have a perfect full chain certificate. Yet users in China are still seeing TLS errors. Your OpenSSL test from Singapore is 100% green. Why is China failing?
Answer: the SNI and Great Firewall issue. A senior engineer knows that in certain jurisdictions, the Great Firewall performs SNI, server name indication filtering. Even if your TLS is perfect, if your domain is on a block list, the firewall will inject a TCP RSD or a fake certificate during the handshake. The fix is not technical. It is regulatory or requires a local China region CDN.
Pro tip, the SSL Labs quality check.
Never consider a TLS migration complete until you have run the domain through SSL Labs or a similar tool. Look specifically for the chain issues section. If it says extra download required or incomplete, your configuration is fragile. A senior grade TLS setup should show a grade A+ with a perfectly contiguous chain provided by the server.
The Senior DevOps Incident 39. The architectural N+1 latency storm.
Your mobile application has just introduced a detailed dashboard. Everything worked in the performance lab with 10 test records. But in production, users with large accounts are reporting 5 to 10 second page loads. You check the backend service CPU, it is near zero. You check the database, it is idle. You check the network bandwidth, it is wide open. The infrastructure is resting, yet the user is waiting. You are facing the N+1 architecture trap, where microservice chattiness has turned your high-speed network into a serial bottleneck.
Symptoms, the panic moment.
Here is what the distributed tracing and network metrics revealed during the slowdown. 1. Latency profile. Request time increases linearly with the amount of data in the user's account. 2. Tracing data. Jaeger or Honeycomb shows a comb pattern where one primary request triggers 100 sequential sub-requests. 3. Infrastructure load. All systems report low utilization. No CPU spikes, no memory pressure, no disk queuing. 4. TCP metrics. Massive volume of small packets with high connection overhead but low total throughput. The system is death by 1,000 cuts. Each individual call is fast, but the sum of their sequential round trips is catastrophic.
Hypothesis, thinking like a senior.
A junior might try to increase the network bandwidth. As a senior, I analyze the call graph and execution model. Hypothesis 1, slow database query, ruled out. Individual query traces show 2 milliseconds execution time. Hypothesis 2, ingress throttling, ruled out. Rate limits are not being triggered and no packets are being dropped. Hypothesis 3, sequential n+1 calls. The backend is iterating through a list and making a synchronous network call for every item, accumulating network overhead and time to first byte for every single hop. Decision tree signal. If app CPU is low, DB is idle, and latency grows linearly with data volume means, then always suspect sequential network round trips or n+1 logic. Investigation, the 6-step debugging masterclass.
Step-by-step latency forensics.
We must prove the sequential nature of the failure. We execute these steps. 1. Trace visualization. We open a single trace ID and look at the waterfall view. We see a staircase pattern where each bar starts only after the previous one finishes. 2. Analyze network overhead. We calculate the latency floor. If one call takes 10 milliseconds network overhead and we make 100 calls, we have a mandatory 1-second delay even if the processing is 0 milliseconds. 3. Check application logic. We find a loop in the code for item and list get details item. 4. Measure connection lifecycle. We see the app is not using connection pooling, so it is performing a full TCP and TLS handshake for almost every subcall. 5. Inspect service mesh. We check Istio metrics and see the request underscore duration is dominated by envoy underscore outbound latency. 6. Root cause identified, serial network execution. The application architecture was designed for local function calls, but was deployed as distributed microservice calls. The accumulated network jitter and round-trip time across 100 sequential calls created a 5-second latency wall that infrastructure cannot scale past. Let us look at the trace pattern that exposed the sequential death loop. The evidence, the sequential loop. By awaiting each call individually within an iterative context, the application forces the network to wait for a full response before sending the next request. At scale, the speed of light becomes your bottleneck.
The fix, implementation of parallelism and batching.
We must move from sequential execution to the scatter-gather pattern or implement bulk API endpoints. Senior warning, do not simply wrap every call in promise.all. If you have 500 orders, you will trigger 500 simultaneous outbound connections, which will exhaust your pod's ephemeral ports and potentially DDoS the downstream service. You must use a worker pool or a throttled concurrency limit. Here is the JavaScript implementation for throttled parallel processing to optimize distributed latency. Disclaimer, always test code in a non-production environment. This is the senior grade fix. We allow 10 network calls to happen in parallel. This reduces the total latency from 5 seconds to 500 milliseconds, while protecting the downstream service from a connection surge.
Prevention and guardrails, the post-mortem.
To prevent n+1 latency storms in the future, we implement these guardrails. 1. Bulk API standards. We mandate that all internal services must provide a bulk endpoint, for example, /v1/status IDs equals 1, 2, 3, to allow fetching multiple resources in a single network round trip. 2. Latency budgeting. We set a network hop limit in our service catalog. Any request path that requires more than 3 internal hops must be architecturally reviewed for data duplication or caching. 3. Tracing alerts. We set a Datadog/new relic alert for trace span count. If a single trace generates more than 50 child spans, the engineering team is notified of a chatness violation. A senior engineer understands that in microservices, data locality is often more important than micro-granularity. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Why does service mesh sidecar injection, like Istio, sometimes make the n+1 problem significantly worse?
Answer, double proxy latency. Each network hop in a mesh involves the packet passing through the source envoy and the destination envoy. This adds approximately 1 to 3 milliseconds per hop. While negligible for a single call, in an n+1 scenario with 100 calls, the mesh tax alone adds 300 milliseconds of pure overhead to the already slow sequential execution.
Senior follow-up 2, the scale and trade-off trap. You move to a bulk API to fetch 100 items in one call. What is the payload timeout trade-off?
Answer, increased all or nothing failure risk. In sequential calls, if 1 out of 100 fails, you lose 1% of data. In a bulk call, if the processing for one item is extremely slow or causes an error, the entire large response may time out or fail, resulting in 100% data loss for that request. You must implement partial success responses in your bulk APIs.
Senior follow-up 3, the Day 2 migration reality. You are moving to GraphQL to solve this. Does GraphQL natively fix the N+1 problem?
Answer: no. GraphQL only fixes the overfetching on the front end. On the back end, a naive GraphQL resolver will still execute a separate database query for every item in a list. You must implement the data loader pattern, which batches and memoizes these requests at the execution layer to truly solve the N+1 issue.
Senior follow-up 4 Curveball. You have bulk APIs and parallel calls, yet the page is still slow. You check the traces and see that all 10 parallel calls are queuing behind each other in the browser. Why?
Answer: the HTTP/1.1 domain limit. Most browsers limit the number of concurrent TCP connections to a single domain to exactly 6. If you trigger 10 parallel API calls from the client, the browser will physically block the last 4 until the first ones finish. A senior engineer knows that you must upgrade to HTTP/2 or HTTP/3 to allow multiplexing over a single TCP connection, bypassing this client-side bottleneck.
Pro tip, the zero-hop architecture.
If you have two services that are so chatty they require hundreds of calls to finish a single user request, they are not actually two services. They are one service that has been incorrectly split. Do not be afraid to undistribute a system. Merging two microservices back into one can often solve latency problems that no amount of network tuning or parallelization ever could.
The Senior DevOps Incident 40, the SNAT port exhaustion.
It is a massive traffic spike during a holiday sale. Suddenly, your Kubernetes pods and Lambda functions start failing with connection timeout and temporary failure in name resolution when trying to reach external services like Stripe or S3. You check the destination. It is 100% healthy. You check your internal network. Bandwidth is fine. Your infrastructure is healthy, but your exit door to the internet is jammed. You are facing source network address translation, or SNAT port exhaustion.
Symptoms, the panic moment.
Here is the behavior of the outbound traffic during the port depletion. 1. Error pattern: random outbound connection failures that resolve themselves momentarily, then return. 2. CloudWatch metrics: the error port allocation metric for the AWS NAT gateway is spiking into the thousands. 3. Dependency impact: internal cluster communication is fine, but any call leaving the VPC is failing intermittently. 4. Connection state: application logs show cannot assign requested address or connection refused during the TCP handshake. The system cannot create a new outbound connection because it has run out of unique source ports to track the traffic.
Hypothesis, thinking like a senior.
A junior might try to scale up the application pods. As a senior, I analyze the outbound flow limits. Hypothesis 1, target API throttling, ruled out. The Stripe API dashboard shows 0,429 errors and low latency. Hypothesis 2, DNS resolver failure, ruled out. Internal DNS is fast and external DNS lookups succeed occasionally. Hypothesis 3, SNAT port exhaustion. The NAT gateway has a hard limit of 64,512 concurrent connections per IP address. Our high concurrency microservices are opening too many unique outbound TCP connections simultaneously. Decision tree signal: if internal traffic is healthy but all external API calls are failing with timeouts, and NAT gateway metrics show allocation errors, then always suspect SNAT port exhaustion. Investigation: the 6-step debugging masterclass.
Step-by-step port forensics.
We must prove that we have reached the physical limits of the NAT gateway. We execute these steps. 1. Inspect CloudWatch metrics. We query AWS/NAT gateway for active connection count. We see it hovering near 64,000. 2. Identify the heavy talker. We use VPC flow logs and Athena to find the source private IP making the most outbound calls. 3. Check connection reuse. We inspect the application code and find it is creating a new HTTP client instance for every single request, rather than using a singleton connection pool. 4. Measure connection lifecycle. we see thousands of connections stuck in the time_wait state, hogging ports for 60 seconds after they are closed. 5. Audit VPC endpoints. We realize the app is talking to AWS S3 and DynamoDB through the NAT gateway, wasting outbound ports on internal AWS services. 6. Root cause identified, port scarcity. The NAT gateway is limited to 64K ports per IP. Because the app was not reusing connections and was routing internal AWS traffic through the public gateway, it consumed the entire port pool during the traffic spike. Let us look at the CloudWatch metrics that prove the exhaustion. The evidence: NAT gateway allocation failures. This is the smoking gun. It explicitly tells us that the NAT gateway refused to create a new connection because no source ports were available for the translation.
The fix: connection pooling and multi-IP scaling.
We must implement aggressive connection reuse and scale the NAT gateway's capacity horizontally. Senior warning: do not just add more NAT gateways. This requires changing your VPC route tables, which can cause a momentary routing blip. Instead, add secondary IP addresses to your existing NAT gateway to expand its port pool without changing infrastructure paths. Here is the CLI implementation for expanding NAT gateway port capacity via secondary IP addresses. Disclaimer: always test code in a non-production environment. This modern AWS feature allows you to attach up to 8 IP addresses to a single NAT gateway. This increases your total outbound connection limit to over 500,000 without needing to modify route tables or subnets.
Prevention and guardrails: the post-mortem.
To protect our outbound exit paths forever, we implement these guardrails. 1. VPC gateway endpoints. We implement S3 and DynamoDB gateway endpoints. This traffic now stays within the AWS private network and never uses a NAT gateway port, freeing up 40% of our capacity. 2. Mandatory connection pooling. We update our internal SDKs to enforce HTTP keep alive and connection pooling. We set a Datadog monitor for active connections per pod. 3. SNAT alarm. We set a proactive CloudWatch alarm on NAT gateway error port allocation at any value greater than 0, triggering an immediate scale out of the port pool. A senior engineer knows that the NAT gateway is a shared bottleneck that must be bypassed whenever possible. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why does a NAT gateway only have 64,512 ports? Can we not just use more?
Answer: this is a fundamental limit of the 16-bit field in the TCP and UDP headers. A single IP address can only have 65,535 ports. The first 1,024 are reserved. Therefore, the NAT gateway can only map one unique internal connection to one of its 64K external ports. To get more ports, you mathematically must add more IP addresses.
Senior follow-up 2, the scale and trade-off trap. You moved all traffic to VPC endpoints. What is the trade-off regarding multi-region communication?
Answer: reachability. VPC gateway endpoints for S3/Dynamo are not transitive. If you have a paired VPC or a VPN connection, those remote networks cannot use your gateway endpoint to reach S3. You must either use interface endpoints, which cost more, or manage separate endpoints in every VPC.
Senior follow-up 3, the day 2 migration reality. You are using IPv6-only subnets for your EKS pods. Do you still need a NAT gateway for outbound traffic?
Answer: no. In IPv6, every pod has a globally unique public IP address. Instead of a NAT gateway, we use an egress-only internet gateway. This allows outbound traffic while blocking inbound connections, entirely eliminating the SNAT port exhaustion problem by design.
Senior follow-up 4 curveball. You have multiple IPs and VPC endpoints, yet you are still seeing allocation errors. You check the destination, and it is only one specific external API. Why can you not use all 500,000 ports for that one API?
Answer: the 5-tuple constraint. A senior engineer knows that a connection is defined by source IP, source port, dest IP, dest port, and protocol. If the destination is a single IP and a single port, like api.stripe.com 443, then your NAT gateway is limited to 64K connections per NAT IP to that specific destination. Adding more NAT IPs is the only solution to break this destination-specific bottleneck.
Pro tip, the time wait reuse rule.
On your Linux worker nodes, always set sysctl-wnet.ipv4.tcp_tw_reuse equals 1. This allows the Linux kernel to immediately reuse a port in the time_wait state for a new outbound connection. This single line change can prevent your nodes from self-DDoSing their own port range before the traffic even reaches the NAT gateway.
The Senior Dev Ops Incident 41, the asymmetric routing ghost.
It is Thursday afternoon. You have just completed a complex VPC peering setup between your legacy data VPC and your new analytics VPC. You test the connectivity. Pings work perfectly. You can resolve the DNS. But when you try to perform a SQL query or a large file transfer, the connection hangs indefinitely and eventually times out. The network is alive for tiny packets but is selectively killing your data transfers. You have entered the world of asymmetric routing.
Symptoms, the panic moment.
Here is the behavior of the network during the partial connectivity failure. 1. ICMP success. You can ping from VPC A to VPC B with 100% success. 2. TCP failure. A telnet or NC connection to the database port connects, but the first data exchange hangs. 3. VPC flow logs. You see accept for SYN packets leaving VPC A, but you see reject or missing for the return traffic in the source subnet. 4. Configuration. You have multiple paths between the VPCs, such as both a direct connect and a VPC peering connection active simultaneously. The packet is taking the scenic route home. It enters through one door and tries to leave through another, triggering the network's self-defense mechanisms.
Hypothesis, thinking like a senior.
A junior might blame the database firewall. As a senior, I analyze the stateful nature of the network. Hypothesis 1, security group misconfiguration, ruled out. The SGs allow all traffic from the peer VPC CIDR range. Hypothesis 2, MTU mismatch, ruled out. Packet fragmentation is not occurring for these small initial handshakes. Hypothesis 3, asymmetric routing. The outbound packet leaves VPC A via the peering connection, but the return packet from VPC B is routed back via a transit gateway, or VPN, because of a higher priority route in the table. The stateful firewall in VPC A drops the return packet because it never saw the outbound request leave through that specific interface. Decision tree signal. If pings work but TCP data hangs and you have multiple network paths, peering, TGW, VPN, then always suspect asymmetric routing. Investigation, the 6-step debugging masterclass.
Step-by-step path forensics.
We must visualize the inbound versus outbound path. We execute these steps. 1. Tracepath analysis. We run mtr-t-p5432 to trace the TCP path. We see it reach the destination VPC successfully. 2. Audit route tables. We compare the route table of VPC A and VPC B. We find VPC A routes traffic to VPC B via PCX 123 peering. 3. Identify the divergence. We find VPC B routes traffic back to VPC A via TGW 456 transit gateway because of a broad 10.0.0.0/8 route entry. 4. VPC flow log correlation. We use CloudWatch Insights to find the interface ID for the outbound SYN and the inbound SYN ACK. They are different. 5. Verify firewall statefulness. We realize the AWS network firewall, or a third-party appliance in VPC, is stateful. Since it never saw the outbound SYN leave via the TGW, it rejects the SYN ACK arriving via the TGW as an invalid, unsolicited packet. 6. Root cause identified. Path non-symmetry. The return traffic is using a different logical path than the request traffic. The stateful security devices on the path are correctly identifying this as a potential spoofing attempt and dropping the data. Let us look at the route table conflict that created the asymmetric loop. The evidence, mismatched VPC route tables. The return path is using a different gateway. Because modern cloud networks and firewalls track the state of a connection, the return packet must arrive at the same logical interface where the connection originated, or it will be dropped.
The fix, route table alignment.
We must ensure that the specific VPC peering route is more specific than the broad transit gateway route to enforce path symmetry. Senior warning: do not fix this by turning off stateful firewalling. This exposes your network to massive security risks. You must fix the routing logic so that the network is deterministic and symmetric. Here is the HCL implementation for enforcing symmetric routing via longest prefix match. Disclaimer: always test code in a non-production environment. By adding a more specific route, longest prefix match, we force VPC-B to use the peering connection for traffic destined to VPC-A, overriding the broad transit gateway route. The path is now symmetric, and the firewall allows the traffic.
Prevention and guardrails, the post-mortem.
To prevent routing ghosts in the future, we implement these guardrails. 1. Route table linting. We use Terraform compliance or Checkov to verify that every VPC peering connection has matching reciprocal routes in both the source and destination route tables. 2. Reachability analyzer. We mandate that any new VPC connectivity must pass an AWS Reachability Analyzer test in both directions before it is considered production ready. 3. Hub and spoke standardization. We move away from manual VPC peering and move toward a centralized transit gateway architecture where all routing is managed in one central place, eliminating island route tables. A senior engineer knows that a network is not a line. It is a loop that must close perfectly. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why does ICMP ping usually work in asymmetric scenarios while TCP fails?
Answer: ICMP is a stateless protocol. Most firewalls and routers treat each ICMP packet independently and do not track a connection state. TCP, however, is stateful. It requires a three-way handshake. If the firewall sees a SYN ACK, the second step, without having seen the SYN, the first step, on that same interface, it must drop it to prevent TCP injection attacks.
Senior follow-up 2, the scale and trade-off trap. You decided to move everything to transit gateway to avoid asymmetry. What is the cost and performance trade-off?
Answer: data processing fees. VPC peering is free within the same region, but transit gateway charges a per gigabyte data processing fee. At high scale, for example, 500 terabytes per month, transit gateway can be significantly more expensive. Furthermore, transit gateway adds a small amount of latency, microseconds, and throughput limits that peering does not have.
Senior follow-up 3, the day 2 migration reality. You have a hybrid cloud setup with an on-premise data center. How do you handle BGP-induced asymmetry?
Answer: as path prepending or local preference. If you have two physical lines to your data center, BGP might send traffic out through line 1, but the ISP might send it back through line 2 because it has a shorter path. We must use BGP as path prepending to make one path look artificially longer, forcing the ISP to use the same line for return traffic that we used for outbound.
Senior follow-up 4 curveball. You have perfect route tables and symmetric paths. Yet a large 10 megabytes file transfer still hangs, while small JSON requests work. You check the route tables again, they are correct. What is the network layer 4 ghost here?
Answer: the PMTU, PathMTU discovery failure. In a VPC peering or VPN scenario, the MTU maximum transmission unit might be smaller than the standard 1,500 bytes. Small packets, JSON fit, but large packets, files, require the do not fragment bit. If an intermediate router drops the large packet but the ICMP needs fragmentation message is blocked by your firewall, the connection will hang forever. This is MTU black holing, and the fix is to enable MSS clamping on your gateway.
Pro tip, the traceroute T-flag.
When debugging asymmetric routing, standard traceroute is useless because it uses UDP. Always use traceroute-T, TCP, or MTR-T on the specific application port, for example, 5432. This forces the packets to traverse the same stateful path as your application traffic, revealing exactly where the firewall is dropping the connection.
Category 9 wrap-up, mastering the cloud network.
Category 9 has exposed the fragility of the network layer at scale. We have seen that senior engineering is not just about making a connection, but understanding the life cycle of that connection. We learned that blind copy-pasting of proxy configurations is a liability that breaks modern protocols like WebSockets. We uncovered how default Kubernetes settings can inadvertently DDoS your DNS control plane, and why path symmetry is non-negotiable in stateful cloud environments. A senior DevOps engineer knows that the network is never a dumb pipe. It is a complex, stateful system that requires precise tuning and protocol-level visibility to remain reliable under pressure.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
But what happens when your routing is perfect? Your DNS is cached, and your protocols are tuned, but the operating system itself starts dropping packets. We are now descending into the kernel abyss, where the physical and software limits of the Linux kernel become the ultimate ceiling for your scalability.
Category 10. The kernel abyss and interface scaling.
Focus when the Linux kernel and CNI reach their physical limits. This is the deepest level of systems engineering. In this section, we examine the failures that occur not because of your code, but because of the finite resources of the Linux kernel. We will explore the contract table exhaustion that silently kills traffic, the eBPF map limits that break security policies in high-density clusters, and the secondary IP address exhaustion that paralyzes pod scaling in the cloud. This is where you prove you are more than a cloud operator. You are a systems architect.
Category 10. Incident list.
We will perform reference-grade deep dives into these 3 kernel-level catastrophes. 42. Contract table exhaustion, solving silent packet drops in high-traffic microservices. 43. Cilium eBPF map exhaustion, when policy scale limits are hit at the kernel level. 44. CNI IP exhaustion, fixing scaling failures when the AWS VPC CNI runs out of secondary IPs for pods. Let us start with the most notorious silent killer in Linux networking, contract exhaustion.
The Senior DevOps Incident 42. The contract table exhaustion.
It is Black Friday. Traffic is peaking, and suddenly 15% of all checkout requests are failing with random timeouts. Users are clicking pay, but the request never reaches the application. You check the application pods, CPU is at 20%. You check the database, it is perfectly healthy. You check the load balancers, they are green. The network is silently swallowing traffic at the kernel level because your nodes have reached their physical limit for tracking connections.
Symptoms, the panic moment.
Here is the data from the node-level observability during the silent drop. 1. Infrastructure metrics, application CPU and memory are well below limits with zero throttling. 2. Alerts, synthetic monitoring triggers for /checkout timeouts, but no internal application alerts are firing. 3. Log behavior. Ingress controller logs show requests entering, but the downstream application pod logs show absolutely nothing for those specific requests. 4. TCP state. A packet capture shows SYN packets arriving at the host interface but never receiving a SYN ACK. Decision tree signal. If app CPU is normal, DB is normal, and logs are missing for a subset of traffic, then always suspect a kernel-level network packet drop.
Hypothesis, thinking like a senior.
A junior engineer might suspect a code bug and ask for a rollback. As a senior, I analyze the kernel state. Hypothesis 1, ingress worker connection limits, ruled out. Nginx metrics show active connections are at 30% of capacity. Hypothesis 2, pod network ghosting, ruled out. Pod-to-pod communication is functional for existing connections. Hypothesis 3, contract table full. The Linux kernel netfilter module has a fixed size table for tracking every TCP and UDP flow. Our high concurrency architecture has exhausted this table, causing the kernel to drop new packets in self-defense. To verify hypothesis 3, we must bypass the container abstraction and inspect the host kernel ring buffer. Investigation, the 6-step debugging masterclass.
Step-by-step kernel forensics.
We must prove the kernel is actively sabotaging our traffic. We execute these steps. 1. Check interface drops. We run IP-slink show and see the RX drop counter increasing in real time. 2. Query kernel logs. We run dmesg-t on the worker node to see if the kernel is complaining about the network. 3. Verify table capacity. We query sysctlnet.netfilter.nf_contract_max to see the hard limit. 4. Measure current usage. We check sysctlnet.netfilter.nf_contract_count to see the live connection count. 5. Identify traffic shape. We run contract-L to see if a specific microservice is creating a flood of short-lived connections. 6. Root cause identified. Contract table saturation. The system reached the 131,072 entry limit. Because the table was full, the kernel's per routing chain dropped every new connection attempt before it could reach the application layer. Let us look at the kernel logs that confirm the silent network assassination. The evidence, nf_contract table full. This log is the ultimate proof of a kernel-level failure. The kernel is physically unable to track more connections, so it drops incoming packets without notifying the sender.
The fix, dynamic kernel tuning.
We must immediately expand the contract table size and the underlying hash table buckets to restore network flow. Senior warning, increasing contract limits consumes unswappable kernel memory. Each entry takes about 300 bytes. If you set this too high on a small memory node, you risk a host-level out-of-memory event that could crash the entire worker node. Here is the bash implementation for tuning contract limits and hash size for high-traffic nodes. Disclaimer, always test code in a non-production environment. Crucially, you must increase the hash size when you increase the max. If you do not, the kernel must search longer linked lists for every packet, which will cause massive CPU spikes during packet processing.
Prevention and guardrails, the post-mortem.
To prevent kernel-level drops from recurring, we implement these guardrails. 1. Node bootstrap automation. We update our Terraform user data scripts to apply high concurrency sysctl settings automatically on every new node boot. 2. Prometheus node exporter. We add an alert for node_nf_contract_entries /node_nf_contract_entries _limit greater than 0.80, giving us a 20% warning before drops begin. 3. Connection pooling. We mandate that all microservices use HTTP keep alive and connection pooling to reduce the rate of new connection creation. A senior engineer knows that cloud scalability is limited by the kernel's ability to track state. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Why does contract fail silently instead of sending a TCP reset or an ICMP error?
Answer, the drop happens at the netfilter layer before the packet is passed to the TCP stack. Because the kernel has no space to record the connection state, it cannot determine if the packet is part of a valid handshake or an attack. Silently dropping is the most secure and performance-efficient way for the kernel to protect itself from resource exhaustion.
Senior follow-up 2, the scale and trade-off trap. You increase the limit to 1 million connections. What is the RAM trade-off?
Answer: kernel slab memory. A contract entry is about 300 bytes. 1 million entries will consume 300 megabytes of RAM that the Linux kernel marks as unreclaimable. On a 4 gigabytes node, you have just stolen nearly 10% of your application's available memory purely for the network state table.
Senior follow-up 3, the day 2 migration reality. You are moving to a stateless architecture using UDP. Does contract still matter?
Answer: yes, potentially more so. Even though UDP is stateless at the application layer, Linux still uses contract to manage pseudo-state for NAT and firewall rules. UDP entries typically time out faster, 30 seconds, but a high-volume UDP stream can fill the table just as easily as TCP.
Senior follow-up 4, curveball. You have plenty of contract space, but pings from one pod to another are still failing. You check the destination node and the contract table is empty. Where is the state being lost?
Answer: tool failure. Check the CNI configuration. If you are using a service mesh like Istio or a CNI like Cilium, they often use eBPF to bypass the standard Linux networking stack. In this case, the standard sysctl contract settings are ignored, and you must instead tune the eBPF map limits inside the CNI's own configuration.
Pro tip, the contract no-track rule.
For high-performance internal traffic that does not require firewalling or NAT, like internal pod-to-pod metrics, use the IP table's no-track target. This bypasses the contract table entirely for specific subnets, allowing you to scale internal communication infinitely without consuming a single entry in the kernel state table.
The Senior Dev Ops Incident 43, the Cilium eBPF map exhaustion.
It is Wednesday morning. You are scaling your cluster to 500 nodes and thousands of microservices. Suddenly, new pods are failing to start with a cryptic CNI error, failed to map policy. Worse, existing security policies are being ignored, and traffic that should be blocked is flowing freely. You check the Kubernetes network policies. They are correct. But your eBPF-based data plane has hit a hard limit in the kernel's memory maps. Your security is failing because your CNI can no longer remember its own rules.
Symptoms, the panic moment.
Here is the behavior of the eBPF-powered network during the map depletion. 1. Pod failures. Pod stuck in container creating with logs showing failed to update BPF map. 2. Security breach. Traffic that was previously blocked by a network policy is now reaching its destination. 3. Cilium metrics. The Cilium_BPF_map_ops_total metric shows a high rate of errors. 4. Node health. Worker nodes are ready, but the Cilium agent is reporting unhealthy or degraded status. Decision tree signal. If network policies are ignored, new pods fail to map, and Cilium agent reports BPF errors, then always suspect eBPF map exhaustion.
Hypothesis, thinking like a senior.
A junior might try to restart the Cilium pods. As a senior, I analyze the kernel data plane limits. Hypothesis 1, Linux kernel version mismatch, ruled out. All nodes are running the same verified kernel version. Hypothesis 2, cluster sitter conflict, ruled out. IP allocation is successful, proving the CNI can still assign addresses. Hypothesis 3, eBPF map saturation. The Cilium agent uses fixed-size eBPF maps to store security identities and routing rules. The number of unique pod identities has exceeded the max_entries defined in the kernel-level maps. To verify this, we must inspect the internal state of the Cilium agent's BPF maps. Investigation. The 6-step debugging masterclass.
Step-by-step eBPF forensics.
We must prove the eBPF maps are full. We execute these steps. 1. Check agent status. We run Cilium status inside a Cilium pod. It shows BPF maps, 1 error. 2. List map limits. We use Cilium BPF map list to see all active kernel maps and their current fill levels. 3. Identify the saturated map. We find that the Cilium_policy or Cilium_LXC map is at 100% capacity. 4. Count security identities. We run Cilium identity list and realize we have 16,000 unique security identities, while the map is limited to 16,384. 5. Analyze policy complexity. We see that the deny rules for 50 namespaces created a cross-product of rules that filled the policy underscore map. 6. Root cause identified, static BPF map sizing. Cilium uses pre-allocated kernel maps for efficiency. The default max underscore entries for security identities and endpoint mapping was too small for the scale of this cluster, causing the kernel to reject new entries and fail open on security rules. Let us look at the Cilium status that exposed the map exhaustion. The evidence, eBPF map failure. This is the physical ceiling. The kernel allocated exactly 16,384 slots for security rules. Because our cluster has exceeded this number of pod combinations, the CNI can no longer enforce new policies.
The fix dynamic map resizing.
We must increase the maximum entry limits for the critical eBPF maps in the Cilium configuration. Senior warning: increasing BPF map sizes requires the Cilium agent to reload its kernel programs. This can cause a microsecond blip in network connectivity. Always perform these changes as a rolling update to the Cilium daemon set to ensure the cluster maintains quorum. Here is the YAML implementation for tuning Cilium eBPF map, limits via Helm values. Disclaimer: always test code in a non-production environment. By doubling the policy map size, we allow the kernel to store more security identities. This immediately allows new pods to schedule and ensures that network policies are enforced correctly.
Prevention and guardrails, the post-mortem.
To prevent eBPF map exhaustion forever, we implement these guardrails. 1. Map monitoring. We set a Datadog alert on the metric Cilium underscore BPF underscore map underscore pressure. If any map reaches 75% capacity, the platform team is notified to scale the limits. 2. Identity consolidation. We work with developers to use more generic labels. Instead of version labels that create a unique identity for every pod, we use app labels to consolidate security groups. 3. Dynamic map sizing. We enable BPF map dynamic size ratio in Cilium, which allows the maps to scale based on the total RAM available on the worker node. A senior engineer knows that in the world of eBPF, memory is management. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Why does Cilium pre-allocate these maps instead of using dynamic memory allocation?
Answer: performance and safety. eBPF programs run inside the kernel's critical path for every packet. Dynamic memory allocation, like malloc, is too slow and can lead to fragmentation or deadlocks in the kernel. Pre-allocated maps ensure big O of 1 lookup time and guaranteed memory availability, which is essential for high-speed packet filtering.
Senior follow-up 2, the scale and trade-off trap. You increase the NAT map max to 1 million entries. What is the CPU trade-off?
Answer: garbage collection overhead. Cilium must run a background BPF LRU, least recently used, janitor to clean up old entries. If the map is massive and the connection rate is high, the CPU cost of scanning and evicting map entries can become a significant tax on the node's performance.
Senior follow-up 3, the day 2 migration reality. You are moving from IP tables mode to BPF host routing. How does this affect your map usage?
Answer: it increases it significantly. BPF host routing bypasses the standard Linux network stack entirely. This means more metadata must be stored in BPF maps, like contract and neighbor tables, that were previously handled by the OS kernel. You must re-audit all map limits before making this transition.
Senior follow-up 4, curveball. Your maps have 50% free space. Your identities are low. Yet, a specific pod still cannot communicate with another pod. Cilium logs say policy denied, but your network policy says allow. What is the hidden state bug here?
Answer: identity desync. A senior engineer knows that eBPF uses numerical identities, not pod names. If the Cilium agent on node A has a different numerical identity for pod times than the agent on node B, due to a cluster-wide KV store desync, the BPF program will correctly deny the traffic based on the wrong ID. You must verify the health of the Cilium operator and the etcd cluster that manages identities.
Pro tip, the Cilium dbg command.
When debugging CNI issues, stop using kubectl. Use Cilium DBG endpoint get ID. This provides the raw, low-level view of what the CNI thinks about a pod, including its BPF identity and exactly which policies are being applied at the kernel level. It is the only way to prove if the issue is in Kubernetes or the kernel.
The Senior Dev Ops Incident 44, the CNI IP exhaustion.
It is a Friday afternoon. You are performing a large-scale deployment of a new microservice with 100 replicas. The cluster has plenty of CPU and RAM. However, 40 of the pods are stuck in the container-creating state. You check the logs and see a terrifying error from the CNI, failed to assign an IP address. Your subnet has 5,000 free IPs, but your worker nodes are refusing to give them to the pods. You are facing the AWS VPC CNI IP address exhaustion trap.
Symptoms, the panic moment.
Here is the behavior of the network interface during the IP famine. 1. Pod status, hundreds of pods stuck in container creating across specific nodes. 2. Kubelet events failed create pod sandbox events appearing with CNI allocation errors. 3. Node health node metrics show 80% free CPU and RAM. The nodes are underutilized. 4. VPC status. The AWS console shows that the subnet has 4,000 available IP addresses. The IPs exist in the cloud, but the bridge between the cloud network and the Kubernetes pod is broken.
Hypothesis, thinking like a senior.
A junior might try to create a new subnet. As a senior, I analyze the ENI to IP density. Hypothesis 1, subnet IP exhaustion, ruled out. AWS console confirms 4,000 available IPs in the VPC sitter. Hypothesis 2, API rate limiting, ruled out. CloudTrail shows no 429 throttling errors for EC2 operations. Hypothesis 3, ENI limit reached. Every AWS instance type has a hard limit on the number of elastic network interfaces, ENIs, it can attach and how many IPs per ENI. Our pods have consumed all available slots on the currently attached interfaces. Decision tree signal. If pods are stuck in container creating, subnet IPs are free, but Kubelet says insufficient IPs, then always suspect ENI level IP limits. Investigation. The 6-step debugging masterclass.
Step-by-step IPAM forensics.
We must find the mismatch between the node capacity and the pod demand. We execute these steps. 1. Inspect node type. We find the worker nodes are T3. Medium instances. 2. Check EC2 limits. We look up the AWS documentation. A T3. Medium allows 3 ENIs with 6 IPs per ENI. Total pods per node equals 15. 3. Analyze pod density. We run kubectl get pods -- all namespaces -- field selector spec.node name equals node 01. We find exactly 15 pods. 4. Audit CNI configuration. We check the AWS node daemon set environment variables. We find warm_IP_target is set to 1. 5. Monitor IPAM logs. We check the Cilium or VPC CNI logs. We see failed to attach new ENI. Private IP address limit exceeded. 6. Root cause identified interface saturation. The instance type was too small for the pod density. Even though the subnet had thousands of IPs, the physical virtual hardware of the EC2 instance could only hold 15 of them at a time. The CNI tried to attach a 4th ENI to get more IPs, but AWS rejected it because the T3. Medium is limited to 3. Let us look at the AWS CLI output that proved the interface limit. The evidence, ENI and IP limits. This confirms the hardware bottleneck. The CNI is trying to give the pod an IP, but it has no more physical wires to attach to the VPC. The pod remains in limbo.
The fix, enabling IP prefix delegation.
We must move away from the 1 IP per pod model and move toward IP prefix delegation, which allows a single ENI to handle hundreds of pods. Senior warning. Enabling prefix delegation requires a rolling update of your entire worker node fleet. It also changes how you perform IP accounting in your VPC. Ensure your VPC flow logs and security groups are configured to handle /28 subnets rather than individual /32 IPs. Here is the CLI implementation for enabling IP prefix delegation. in the AWS VPC CNI. Disclaimer: always test code in a non-production environment. By enabling this, each ENI slot now receives a /28 prefix, 16 IPs, instead of a single IP. This increases the pod capacity of a T3 dot medium from 15 pods to 110 pods, instantly solving the exhaustion. We also configure the warm target. This ensures the CNI keeps at least one full /28 prefix ready in the buffer, allowing new pods to start instantly without waiting for an AWS API call to attach new resources.
Prevention and guardrails, the post-mortem.
To protect our pod scaling permanently, we implement these guardrails. 1. Right-sizing instance types. We mandate that any production node group must use instances with at least 8 ENIs, for example, M5 large or higher, to avoid low hardware ceilings. 2. Custom networking. We implement custom networking for the CNI, allowing pods to use a separate secondary VPC CIDR range. This prevents pods from stealing IPs from the primary subnet used by RDS and ELBs. 3. IPAM monitoring. We add a Grafana panel for AWS CNI_total_IP_ addresses versus AWS CNI_ assigned_IP_ addresses to alert us when a node reaches 90% of its ENI capacity. A senior engineer knows that the cloud's elastic nature is limited by the physical constraints of the hypervisor. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. How exactly does the AWS VPC CNI map a VPC IP directly to a container's ETH0 interface?
Answer: secondary IP addressing. The CNI talks to the AWS EC2 API to attach an ENI to the host. It then assigns a secondary private IP to that ENI. Inside the host, the CNI creates a VETH pair, moves one end into the pod's network namespace, and uses source routing IP rules to ensure traffic from that pod IP is routed through the correct ENI to the VPC gateway.
Senior follow-up 2, the scale and trade-off trap. You enabled prefix delegation to get 110 pods per node. What is the subnet fragmentation risk?
Answer: IP wastage. Each node now claims a full /28 prefix, 16 IPs, even if it only has one pod. If you have 100 small nodes, you have locked 1,600 IPs. In a small subnet, you will run out of IPs for the entire cluster much faster than you would with the individual IP model. You trade node capacity for subnet density.
Senior follow-up 3, the day 2 migration reality. You are using security groups for pods. How does this complicate the IP exhaustion issue?
Answer: ENI reservation. When you assign a unique security group to a pod, AWS must create a dedicated branch ENI. These branch interfaces do not support prefix delegation and count against the total ENI limit of the instance. Using this feature significantly reduces your pod density per node.
Senior follow-up 4, curveball. You have prefix delegation enabled and a massive subnet. Yet you still see failed to allocate errors for one specific pod. You check the node and it only has 5 pods. What is the namespace limit here?
Answer: hidden cause. This is the max pods constraint in the kubelet. Even if the network can handle 110 pods, the kubelet has a default configuration, usually --max pods equals 110 or lower based on instance size. If you use small instances, the kubelet calculates a very low pod limit to protect the node's CPU/RAM. You must manually override the kubelet configuration to allow higher density.
Pro tip: the warm_IP_target formula.
Never leave warm_IP_target at the default in high-velocity clusters. If you set it too high, you waste subnet IPs. If you set it to 0, every pod startup will be delayed by 10 seconds as the CNI calls the AWS API to fetch a new IP. A senior engineer sets minimum_IP_target to the average pod density of the cluster to ensure instance starts with 0 subnet wastage.
Category 10, wrap up, surviving the abyss.
Category 10 has taken us below the application and the orchestrator, into the very guts of the Linux kernel. We have seen that senior engineering requires a deep respect for the physical and software limits of the host operating system. We learned that contract tables and eBPF maps are finite resources that can silently cripple a cluster, and that cloud IP limits can stop scaling even when compute resources are free. A senior architect knows that a system is only as scalable as its lowest level bottleneck. Mastering the kernel abyss means ensuring your infrastructure does not just run, but thrives under the extreme pressure of the data plane.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
But even a perfectly tuned kernel cannot protect you if your data strategy is fundamentally flawed. We are now moving from the transport of packets to the storage of state. We are entering the highest stakes domain of DevOps, stateful survival.
Category 11, Data Strategy and Stateful Survival.
Focus: protecting the database and persistent state from destruction. This is where the most expensive outages occur. In this section, we move beyond stateless pods and look at the complex world of distributed data. We will explore how local disk assumptions break during scaling, why Postgres transaction IDs can force a read-only shutdown, and the nightmare of split brain in high-availability clusters. When data is involved, there are no easy rollbacks. This is where your survival skills as a senior engineer are truly measured.
Category 11, Incident List.
We will perform reference-grade deep dives into these 9 high-stakes data catastrophes. Scenario 45, the stateful upload crash local disk versus S3 object storage scaling failure. Scenario 46, the Midnight Assassin batch job data growth outstripping memory limits. Scenario 47, Postgres TXID wraparound, auto vacuum failures causing read-only shutdowns. Scenario 48, HA split brain, network blips causing dual primaries and data corruption. Scenario 49, database connection leaks, distributed pool exhaustion crushing DB engines. Scenario 50, gradual latency creep, query plan degradation, and database table bloat. Scenario 51, replica inconsistency, stale reads under heavy replication lag. Scenario 52, hot partition and shard, uneven key distribution crushing a single node. Scenario 53, EBS IOPS exhaustion, burst credit depletion on critical storage volumes. Let us begin with the classic scaling trap, the stateful upload crash.
The Senior DevOps Incident 45, the stateful upload crash.
Your company has successfully processed customer uploads for 2 years on a single large server. To handle growing traffic, you add a second server behind a load balancer. Suddenly, reports flood in. Users see an upload successful message, but when they refresh the page, they get a 404 file not found. The application is working, the disk has space, and the network is healthy. You have violated the primary rule of cloud scaling by treating local ephemeral storage as a persistent data store.
Symptoms, the panic moment.
Here is the behavior of the split-state architecture during the failure. 1. Inconsistent retrieval. A user uploads a receipt and sees it immediately, but on the next refresh it disappears with a 404 error. 2. Server state. Server contains the new file in /var/www/uploads, but server B is completely empty. 3. Load balancer pattern. The 404 errors correlate perfectly with the round-robin distribution of the load balancer. 4. Application logs. The logs on server A show a successful write, while the logs on server B show a file missing error for the same file ID. Decision tree signal. If an application works with one instance but returns 404s after scaling horizontally, then always suspect an unsynchronized local state or local file system dependency.
Hypothesis, thinking like a senior.
A junior might try to implement sticky sessions at the load balancer. As a senior, I analyze the system design flaw. Hypothesis 1, database desync, ruled out. The file metadata exists in the shared database, proving the upload reached the DB. Hypothesis 2, permission issue, ruled out. Both servers have identical UID and GID configurations for the upload directory. Hypothesis 3, stateful local disk. The application is using local POSIX file system calls to store binary data. Because the disk is not shared, the data is trapped on the specific server that handled the initial post request. To verify this, we must compare the directory contents across the entire server fleet. Investigation, the 6-step debugging masterclass.
Step-by-step state forensics.
We must prove the data is geographically isolated within the network. We execute these steps. 1. Audit source code. We search for the file writing logic. We find a hard-coded path to /var/www/upload/receipts. 2. Cross-server file check. We run in parallel SSH command to list files in that directory across all servers. 3. Map request path. We use a custom header to identify which server handled the upload. We confirm the file only exists on that specific host. 4. Inspect volume type. We run the mount command and find the root partition is a standard EBS volume, which is limited to a single instance. 5. Review scaling group. We check the auto scaling group and realize it is scheduled to terminate nodes tonight, which would permanently delete all uploads on those nodes. 6. Root cause identified, stateful application design. The system was built on the assumption of a pet server. By saving files to a local disk instead of a distributed object store like S3, the application became non-deterministic the moment a second server was introduced. Let us look at the code and shell output that prove the data isolation. The evidence, local disk data mismatch. This is the architectural failure. The application is using standard local I/O. In a distributed environment, the local disk must be treated as a temporary cache, never as a source of truth.
The fix, implementation of stateless object storage.
We must decouple the binary storage from the compute layer by migrating all uploads to a managed object storage service. Senior warning, do not fix this using NFS or EFS, Elastic File System, as a band-aid. While they provide a shared disk, they introduce massive latency and locking overhead for small files. The correct senior-level fix is to refactor the application to use the S3 API. Here is the JavaScript implementation for uploading files directly to AWS S3 using the SDK. Disclaimer, always test code in a non-production environment. By moving to S3, the file is now globally accessible to every server in the cluster. Server B can now serve the file even if server A handled the upload, making the application truly stateless.
Prevention and guardrails, the post-mortem.
To ensure we never build a stateful trap again, we implement these guardrails. 1. Stateless linting. We add a CI check that searches for fs.write file or similar local I/O calls in the codebase and flags them for architectural review. 2. Read-only root file system. We configure our Kubernetes pods and Docker containers to run with a read-only root file system. This physically prevents developers from saving files to the local disk in production. 3. Presigned URLs. We implement S3 presigned URLs so the application does not even have to handle the byte transfer. The client uploads directly to S3, reducing the load on our servers. A senior engineer knows that if a server is not replaceable, it is a liability. The senior follow-up stack.
Senior Follow-up 1 Mechanism Deep Dive. Why is Sticky Sessions considered a poor solution for this specific problem?
Answer: sticky sessions, session affinity, only masks the symptom. It binds a user to a specific server, but it does not solve data durability. If that specific server is terminated by an autoscaler or a hardware failure, all data stored on its local disk is permanently lost. It also prevents even load distribution, leading to hot nodes that can crash while others are idle.
Senior Follow-up 2 The Scale and Trade-off Trap. You moved everything to S3. Now, your list files operation that used to take 5 milliseconds on a local disk takes 500 milliseconds. How do you handle this latency?
Answer: metadata separation. You should never use the S3 list objects API to drive a user interface. Instead, you must store the file metadata name, URL, size in a high-speed database like PostgreSQL or DynamoDB. The app queries the DB for the list and only hits S3 for the physical binary download.
Senior Follow-up 3 The Day 2 Migration Reality. You have 20 terabytes of files trapped on server A. How do you migrate them to S3 without taking the site offline?
Answer: the dual read pattern. First, start writing all new uploads to S3. Second, modify the application to check S3 first for a file. If it is not found, check the local disk of server as a fallback. Third, run a background AWS S3 sync job. Once the sync is complete and the fallback is never triggered, you can decommission the local storage.
Senior Follow-up 4 Curveball. You have moved to S3 and everything is green. But your monthly AWS bill just jumped by $5,000 for S3 request costs. You realize your app checks for a file's existence 100 times per second. How do you fix the cost without reverting to local disk?
Answer: constraint scenario. This is a metadata overhead problem. You must implement a caching layer using Redis. Store the file existence as a Boolean in Redis with a 1-hour TTL. The application checks Redis first. If the key exists, it skips the expensive S3 head object call entirely. You trade a few megabytes of RAM for a 90% reduction in AWS request costs.
Pro tip: the lifecycle policy rule.
Never create an S3 bucket without a lifecycle policy. Many uploads, like temporary receipts or logs, are only needed for 30 days. By setting an automated rule to move old files to S3 intelligent tiering or deleting them after a retention period, you prevent your storage costs from growing infinitely over time.
The Senior Dev Ops Incident 46. The Midnight Assassin.
It is exactly 2:05 a.m. Your pager duty fires for the third night in a row. The backend processing service has crashed and restarted. By the time you log in at 2:10 a.m., the pods are green, CPU is at 5%, and the logs are completely empty. The developers swear the code is unchanged, and it works perfectly on their laptops. You are facing a data volume-induced execution, where a batch job has grown into a monster that is triggering a kernel-level assassination every single night.
Symptoms: the panic moment.
Here is the behavior of the silent crash during the night shift. 1. Perfect timing: the service crashes at the exact same minute every night, correlating with the start of a background cleanup job. 2. 0 logs: standard kubectl logs returns no error stack trace or exit message. 3. Memory spike: the Grafana dashboard shows a vertical line in memory usage that hits the limit and immediately drops to 0. 4. Pod state: kubectl get pods shows the pod has been restarted once with a non-zero exit code. Decision tree signal: if a pod crashes at a fixed time daily, application logs are empty and memory utilization was at the limit, then always suspect a kernel OOM kill triggered by a batch job.
Hypothesis: thinking like a senior.
A junior might try to double the RAM limit. As a senior, I analyze the data shape and memory allocation. Hypothesis 1: memory leak. Ruled out. The memory usage is flat for 23 hours and only spikes during the batch job. Hypothesis 2: liveness probe timeout. Ruled out. The crash happens too fast for a probe to fail. Hypothesis 3: dataset slurping. The batch job was designed to load all records into memory for processing. As the business grew from 5,000 to 180,000 records, the dataset physically exceeded the 2 GB RAM limit, causing the Linux kernel to sig-kill the process instantly. To verify this, we must inspect the container's termination reason and the kernel logs. Investigation, the 6-step debugging masterclass.
Step-by-step batch job forensics.
We must prove the crash is a volume-based resource exhaustion. We execute these steps. 1. Check exit code. We run kubectl get pod-o YAML and look at the last state section. We find exit code 137 and reason killed. 2. Inspect kernel ring buffer. We SSH into the node and run dmesg-t. We find the kernel message memory cgroup out of memory killed process. 3. Trace batch start. We identify the code entry point for the 2 AM task. It is a find to array database call. 4. Verify data volume. We query the database for the current record count. We find it has reached 180,000 rows, a 30 times increase from when the code was written. 5. Measure object size. We calculate that each JSON object in the array is 12 kilobytes. 180,000 multiplied by 12 kilobytes equals 2.1 gigabytes, exceeding our 2 gigabytes container limit. 6. Root cause identified, non-streaming data processing. The application was designed with laboratory logic, loading the entire dataset into memory, RAM, before processing. This created a vertical limit where success was tied to data volume. Once the volume crossed the 2 gigabytes threshold, the kernel acted in self-defense to protect the node. Let us look at the Kubernetes state and the kernel logs that confirm the execution. The evidence, pod termination state. Exit code 137 is the universal Linux signal that the process was killed by a sig-kill, 9 plus 128. Because the reason is killed, we know the kernel terminated the process because it exceeded its cgroup memory limit.
The fix, implementing cursor-based streaming.
We must refactor the batch job to use streams or cursors, ensuring the memory usage remains constant regardless of the dataset size. Senior warning, do not simply increase the RAM limit to 4 gigabytes. That is a linear patch that will fail again in 6 months when the data hits 400,000 records. You must implement an architecture where memory consumption is decoupled from data volume. Here is the JavaScript implementation for streaming database records to maintain constant memory usage. Disclaimer, always test code in a non-production environment. By using a stream instead of an array, the application only holds one record in memory at a time. The memory usage will now stay at 50 megabytes whether you have 10,000 or 10 million records.
Prevention and guardrails, the post-mortem.
To prevent assassins from returning, we implement these guardrails. 1. Memory slope alerting. We set a Datadog alert for derivative of memory usage. If memory climbs more than 500 megabytes in under 60 seconds, it triggers a warning for potential non-streaming logic. 2. Mandatory pagination. We update our internal API standards to forbid any list operation that does not require a limit and offset, or a cursor-based pagination. 3. Chaos engineering. We run a weekly volume stress test in staging where we inject 5 million dummy records into the database to verify that batch processes remain stable under extreme load. A senior engineer knows that code that does not scale with data is a ticking time bomb. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Why does the Java virtual machine often get killed even when the heap size is set correctly?
Answer, the JVM slop factor. The container limit cgroup applies to the entire process, not just the Java heap. The JVM also needs RAM for metaspace, code cache, and stack threads. If you set your heap to 2 gigabytes in a 2 gigabytes container, the extra JVM overhead will push the process over the limit, triggering the killer. You must set the heap to roughly 75% of the container limit.
Senior follow-up 2, the scale and trade-off trap. You move to streaming. Now your batch job takes 6 hours to finish because it processes one record at a time. How do you handle the RTO, recovery time objective trade-off?
Answer, parallel streaming. Instead of one stream, we use worker pools. We shard the data, for example, by user ID ranges, and run 10 parallel streams across 10 different pods. This keeps memory usage low on each pod but reduces the total processing time by 90%. We trade scheduling complexity for execution speed.
Senior follow-up 3, the day 2 migration reality. You are migrating this batch job to AWS Lambda. How does the memory management change?
Answer: strict enforcement. AWS Lambda is even more aggressive than Kubernetes. If you exceed the allocated memory, the execution is terminated instantly with a process exited before completing request error. Because Lambda charges based on memory multiplied by time, using streaming is not just an availability requirement. It is a direct cost optimization strategy.
Senior follow-up for Curveball. You have perfect streaming and low memory. Yet the 2 a.m. job still crashes. You check the node and find that a different pod on the same node spiked in memory, causing the kernel to kill your pod. Why did the kernel kill the innocent pod?
Answer: hidden cause. This is the score algorithm. When a node runs out of RAM, the Linux kernel looks for the process with the highest score. If your pod has no limits set but high usage, it is the first target. To prevent being the victim of a noisy neighbor, you must set your pod's quality of service to guaranteed by setting requests equal to limits, which lowers your priority score.
Pro tip: the garbage collection signal.
Before a process gets killed, it usually undergoes GC thrashing. The CPU will spike to 100% because the language runtime is desperately trying to free memory that does not exist. If you see high CPU and high memory simultaneously during a batch job, do not scale the CPU. Scale the RAM or, better yet, fix the streaming logic.
The Senior Dev Ops Incident 47. The Postgres Transaction ID Wraparound Panic.
It is a Tuesday morning during peak trading hours. Suddenly, your primary Postgres SQL database stops accepting any new writes. Every insert and update query fails with a terrifying error. Database is not accepting commands to avoid wraparound data loss. You check the disk space. It is 40% free. You check the CPU. It is near idle. The database has effectively committed suicide to protect itself from fundamental limitation of its own versioning engine. You are facing the Postgres Transaction ID wraparound.
Symptoms: the panic moment.
Here is the behavior of the database during the read-only shutdown. 1. Write failure. 100% of write transactions are rejected with the wraparound error message. 2. Read availability. Existing select queries still function perfectly, masking the issue from simple health checks. 3. Auto vacuum state. The PG_stat_activity view shows auto vacuum processes running, but they seem to be making zero progress. 4. System logs. The Postgres error log is flooded with warnings about database age that have been ignored for weeks. Decision tree signal. If writes are rejected with a wraparound error while disk and CPU are healthy, then always suspect a failure of the auto vacuum process and transaction ID age.
Hypothesis: thinking like a senior.
A junior might try to restart the database. As a senior, I analyze the MVCC lifecycle. Hypothesis 1: corrupted index. Ruled out. Reindexing does not allow writes to resume. Hypothesis 2: disk corruption. Ruled out. Hardware diagnostics show healthy NVMe performance. Hypothesis 3: TXID wraparound. Postgres uses a 32-bit transaction ID system because the auto vacuum process was blocked or misconfigured. The oldest transaction ID reached the 2 billion mark. The database goes read only to prevent data from wrapping and becoming invisible or overwritten. To verify this, we must query the internal Postgres metadata to find the age of the oldest transaction. Investigation: the 6-step debugging masterclass.
Step-by-step Postgres forensics.
We must prove the transaction ID exhaustion. We execute these steps. 1. Check transaction age. We run a query against PG_database using the age function. We find the age is 2.1 billion. 2. Identify blocked vacuum. We check PG_stat_activity for long-running transactions. We find an idle in transaction session that has been open for 14 days. 3. Analyze vacuum logs. We check the logs for skipping vacuum messages. We realize the 14-day transaction prevented vacuum from advancing the frozen ID. 4. Verify table bloat. We run an analysis and find that 60% of the table is dead tuples that have not been reclaimed. 5. Check configuration. We look at the auto vacuum _freeze_max_age setting and find it is set to the default of 200 million, but the system ignored it because of the blocking transaction. 6. Root cause identified. long-lived transaction blocking auto vacuum. A developer's data science notebook opened a transaction 2 weeks ago and never committed. This prevented Postgres from freezing old rows, causing the transaction ID counter to hit the hard safety limit of 2.1 billion. Let us look at the SQL queries that expose the transaction age. The evidence: transaction ID age in blocked sessions. The frozen transaction ID age is the most critical metric. When this number approaches 2 billion, the database will shut down. This proves we have reached the mathematical limit of the 32-bit transaction counter.
The fix: emergency vacuum and configuration tuning.
We must kill the blocking transaction and perform a manual, aggressive vacuum to freeze the old IDs. Senior warning: do not run a full vacuum full during this incident. It will lock the tables and take hours. Instead, perform a standard vacuum with high cost limit settings to allow it to finish as fast as possible without locking the entire database for reads. Here is the SQL implementation for aggressive manual vacuum and auto vacuum tuning. Disclaimer: always test code in a non-production environment. The freeze keyword is the key. It tells Postgres to rewrite the row metadata and mark the transactions as frozen in the past, allowing the database age to reset and the right lock to be lifted.
Prevention and guardrails: the post-mortem.
To prevent TXID wraparounds from threatening the business again, we implement these guardrails. 1. TXID age alerting. We set a Datadog alert on Postgres SQL.database.max_age. If the age exceeds 500 million, 25% of the limit, we trigger a high-priority engineering task. 2. Statement timeouts. We enforce a global statement underscore timeout of 60 seconds and an idle underscore in underscore transaction underscore session underscore timeout of 5 minutes to prevent abandoned sessions from blocking the vacuum. 3. Aggressive auto vacuum defaults. We update the RDS parameter group to increase auto vacuum underscore scale underscore factor to 0.01, ensuring vacuum runs frequently even on massive tables. A senior engineer knows that a database is only as good as its garbage collector. The senior follow-up stack.
Senior follow-up 1: mechanism deep dive. Why does Postgres use a 32-bit ID for transactions, and what is a frozen ID?
Answer: Postgres uses MVCC or multi-version concurrency control to handle parallel reads and writes. A 32-bit ID allows for 4 billion transactions, but because it is a circular buffer, only 2 billion can be active at once. Freezing a row replaces its transaction ID with a special identifier called frozen XID, which is considered older than all regular transactions, effectively removing it from the wraparound calculation.
Senior follow-up 2: the scale and trade-off trap. You increased auto vacuum underscore cost underscore limit to 2,000 to fix the problem. What is the disk I/O trade-off?
Answer: write saturation. Auto vacuum is normally throttled to avoid impacting user queries. By increasing the cost limit, you allow vacuum to consume more disk throughput. On a shared storage environment, this can cause a 20 to 30% spike in user-facing query latency. You trade database health for query performance.
Senior follow-up 3: the day 2 migration reality. You are running a massive migration from Postgres 11 to Postgres 15. Does this issue still exist in modern versions?
Answer: yes, but it is better managed. Modern Postgres versions, 13+, have significantly improved auto vacuum logic and better monitoring of fail-safe vacuuming. However, the fundamental 32-bit limit remains, so the senior principles of monitoring idle in transaction sessions are still mandatory.
Senior follow-up 4: curveball. You have killed all active sessions. You run the vacuum. It still makes 0 progress on the age. You check the logs and see transaction ID wraparound is still a risk. Why is vacuum still failing?
Answer: hidden cause, prepared transactions. A senior engineer checks PG underscore prepared underscore ZAX. If someone used two-phase commit 2PC and left a prepared transaction hanging, it behaves exactly like a long-running active transaction. It is stored on disk and persists even through database restarts. You must manually roll back or commit the prepared transaction using its GID to allow vacuum to proceed.
Pro tip: the zero downtime vacuum.
If you have a massive table that auto vacuum cannot finish, Do not wait for the panic. Use the PG_repack extension. It allows you to rebuild the table and indexes in the background without taking an exclusive lock, effectively performing a vacuum full while users are still writing to the table. It is the gold standard for maintaining high-write databases.
The Senior Dev Ops Incident 48, the High Availability Split Brain.
It is a Friday evening. A brief 3-second network flicker occurs in your primary cloud region. Your high availability manager, Patroni, detects that the master database is unreachable and promotes the replica to master. However, the old master did not actually die. It just lost its network path to the health check agent. Now, you have two master databases running simultaneously. Your application is writing half its data to Node and half to Node B. You are facing a split brain, the most dangerous state in distributed systems, where your data is silently diverging into an irreconcilable mess.
Symptoms: the panic moment.
Here is the behavior of the dual master catastrophe. 1. Data inconsistency. A user creates an account on Node A, but when they log in 5 minutes later, the request hits Node B and says account not found. 2. Dual primary state. Running show primary on both nodes returns true. 3. Replication failure. The replication lag metric is skyrocketing because neither node will accept the other as its superior. 4. Error pattern. Intermittent duplicate key errors as different users are assigned the same auto-increment ID on different nodes. Decision tree signal. If two database nodes both claim to be master and replication is stalled, then always suspect a split brain caused by a failed fencing mechanism.
Hypothesis: thinking like a senior.
A junior might try to restart replication. As a senior, I analyze the consensus and fencing logic. Hypothesis 1, false positive master, ruled out. Both nodes are actively accepting insert and update queries. Hypothesis 2, service discovery bug, ruled out. The application is correctly following the primary DNS record, but the record is flapping between the two nodes. Hypothesis 3, quorum and fencing failure. The network partition allowed the replica to win an election while the master was still alive. Because the Stanith shoot the other node in the head, agent failed to execute. The old master was never fenced off from the network. To verify this, we must check the failover manager logs and the consensus store state. Investigation, the 6-step debugging masterclass.
Step-by-step split brain forensics.
We must identify the point of divergence. We execute these steps. 1. Check consensus store. We query etcd or console to see who the cluster leader is. It says Node B. 2. Inspect failover logs. We see Node B detected a timeout for Node and initiated a leader election. 3. Analyze old master logs. We find Node tried to renew its leader lease but failed due to the network blip. However, it failed to trigger its demote script. 4. Identify fencing failure. We check the AWS IAM logs and find that the fencing agent failed to stop Node because of an access denied error on the EC2 stop instances API. 5. Measure data delta. We compare the maximum ID in the orders table on both nodes. Node A is at 50,000, Node B is at 50,050. We have 50 conflicting transactions. 6. Root cause identified, lack of hard fencing. The failover was triggered by a network partition, but because the automation lacked the permissions to physically kill the old master, the system entered a dual writer state. The application continued to talk to the zombie master because the network was only partitioned between the nodes, not between the app and Node A. Let us look at the logs from the failover manager that showed the election during the partition. The evidence: 2 primaries in the failover manager. Note the TL or timeline column. Node B has a higher timeline 11, meaning it promoted itself. But Node A is still running on timeline 10 and thinks it is still the leader. This is the definition of a split brain.
The fix: fencing and manual reconciliation.
We must immediately stop the old master and manually merge the missing data before resuming replication. Senior warning: do not just start replication from Node B to Node A. This will overwrite Node A's data, and you will permanently lose those transactions. You must export the missing rows from the old master first. Here is the Bash and SQL implementation for fencing the zombie master and reconciling data. Disclaimer: always test code in a non-production environment. By using the inserts flag, we create a script that can be manually edited to handle primary key collisions, before we import the lost data into the new source of truth.
Prevention and guardrails, the post-mortem.
To ensure Split Brain never corrupts our data again, we implement these guardrails. 1. Watchdog Timer. We enable the Linux kernel watchdog module. If Patroni cannot reach the consensus store for 30 seconds, the kernel will forcefully reboot the node, self-fencing. 2. IAM permission audit. We verify that the failover agent has EC2 stop instances and EC2 terminate instances permissions for its peer nodes. 3. Consensus quorum. We ensure the failover manager requires a strict majority, for example, 2 out of 3 votes to perform a promotion, preventing a single isolated node from crowning itself king. A senior engineer knows that in a distributed system, it is better to be dead than to be wrong. The Senior Follow-Up Stack.
Senior Follow-Up 1 Mechanism Deep Dive. What is the Raft or Paxos protocol, and how does it prevent split brain in modern databases?
Answer: these are consensus algorithms. They rely on the concept of a quorum. A leader is only valid if a majority of nodes, for example, 2 out of 3, agree on its leadership. If a network partition occurs, the side with the minority of nodes will automatically stop accepting rights because they cannot reach a majority agreement, mathematically preventing 2 nodes from ever being master at the same time.
Senior Follow-Up 2 The Scale and Trade-Off Trap. You decided to move from 2 nodes to 5 nodes to increase reliability. How does this affect your write latency?
Answer: latency inflation. In a synchronous HA setup, every write must be acknowledged by a quorum, 3 out of 5. As you add more nodes across more availability zones, the network round-trip time between those nodes increases, adding milliseconds of overhead to every single user transaction. You trade speed for durability.
Senior Follow-Up 3 The Day 2 Migration Reality. You are moving to a multi-region database setup. How does the split brain risk change?
Answer: it becomes an eventual consistency problem. Across regions, network latency is too high for synchronous quorum. We move to asynchronous replication where data lost during failover is an accepted risk. To prevent split brain here, you must use a global traffic manager like Route 53 that enforces a strict single-region primary policy.
Senior Follow-Up 4 Curveball. You have perfect fencing and quorum, yet you still see conflicting rights. You realize that Node A and Node B are in different regions, and both regions are currently master because of a global BGP failure that isolated the continents. How do you merge the data?
Answer: the CRDT, or conflict-free replicated data type strategy. A senior architect knows that if a global split happens, manual merging is impossible at scale. You must design your database schema to use UUIDs instead of auto-incrementing IDs, and use last write wins or vector clocks to allow the system to automatically heal and resolve conflicts once connectivity is restored.
Pro tip, the Stoneth Principle.
In high availability design, the acronym Stoneth stands for shoot the other node in the head. If your failover script cannot guarantee that the old master is physically powered off or isolated at the network level, it is not a safe failover script. In a choice between cluster downtime and data corruption, a senior engineer always chooses downtime.
The Senior Dev Ops Incident 49, the Distributed Connection Leak.
It is Monday morning. You are scaling your microservices fleet from 100 to 500 pods to handle a successful marketing launch. Suddenly, all services, including those you didn't scale, start failing with fatal "sorry, too many clients already." You check the database. CPU is at 10%, but it is refusing every new connection. Your database engine is being crushed not by load, but by the sheer volume of idle zombie connections held by a distributed fleet. You are facing distributed pool exhaustion.
Symptoms, the panic moment.
Here is what the observability stack showed during the connection lockout. 1. Global error. Every microservice reports connection pool exhausted or database connection refused. 2. Database metrics. The active connections graph is a flat line hitting the max_connection ceiling. 3. Resource paradox. Database CPU, memory, and IOPS are extremely low. The server is essentially doing nothing. 4. Pod state. New pods fail to start because their readiness probes, which check the DB, are failing. Decision tree signal. If the DB is idle but connections are full, and the issue scales with the number of pods means, then always suspect a distributed connection leak or a lack of connection multiplexing.
Hypothesis, thinking like a senior.
A junior might try to increase max underscore connections on the DB. As a senior, I analyze the connection lifecycle across the fleet. Hypothesis 1, database throughput limit, ruled out. Queries are finishing in sub-milliseconds when a connection is actually obtained. Hypothesis 2, network latency during handshake, ruled out. VPC latency is stable at 0.5 milliseconds. Hypothesis 3, zombie connection leak. Each of the 500 pods is opening a minimum of 10 connections. 500 pods multiplied by 10 connections equals 5,000, exceeding the database's 2,000 connection limit. Many of these connections are idle because the application is not releasing them back to the pool correctly. To verify this, we must inspect the internal process table of the database engine. Investigation, the 6-step debugging masterclass.
Step-by-step connection forensics.
We must prove the leak is distributed across the fleet. We execute these steps. 1. Audit backend stats. We query pg_stat_activity or process list to see the state of all connections. 2. Identify state. We find that 90% of the connections are in idle or idle in transaction state for over 30 minutes. 3. Map connections to pods. We group connections by client IP. We find that every pod in the order service is holding exactly 20 connections, but only using one. 4. Inspect application code. We find a background thread that opens a connection to check health but never calls .close in the finally block. 5. Calculate total overhead. We realize that at 500 pods, the minimum idle setting in the app's pooler is itself exceeding the DB's total capacity. 6. Root cause identified. Distributed connection bloat. The combination of a logical leak in an error path and an aggressive minimum idle pool setting meant that, as the cluster scaled, it effectively DDoSed the database's connection limit before a single real user request was even processed. Let us look at the Postgres metadata that exposed the zombie connection flood. The evidence, idle connection metadata. This is the smoking gun. The database has allocated memory and a process for these connections, but they have been sitting doing nothing for hours. The application has forgotten to give them back.
The fix, implementation of sidecar proxy and pool refactoring.
We must move the connection management out of the application and into a specialized multiplexing proxy. Senior warning. Do not simply increase the max underscore connections on the database. Each connection on a database like Postgres consumes about 10 megabytes of RAM. Increasing the limit to 10,000 to accommodate a leaky fleet will cause the database server to suffer a hardware OOM kill. Here is the YAML implementation for deploying PG Bouncer as a multiplexing sidecar to reduce connection overhead. Disclaimer. Always test code in a non-production environment. This is the senior level fix. In transaction mode, PG Bouncer allows hundreds of client connections to share a tiny pool of server connections. The moment a transaction finishes, the server connection is freed for another pod, even if the client pod stays connected to the proxy.
Prevention and guardrails, the post-mortem.
To prevent distributed connection exhaustion forever, we implement these guardrails. 1. Client-side timeouts. We enforce idle underscore and underscore transaction underscore session underscore timeout at the database level to automatically kill any connection that is holding locks while idle. 2. Pool sizing calculator. We mandate that every service's max pool size must be documented in the service catalog. The sum of all max pools across all services must be less than 80% of the database capacity. 3. Centralized pooling. For massive clusters, we move from sidecar pooling to a centralized PG Bouncer cluster, which provides a single point of truth for connection counting. A senior engineer knows that database connections are a finite, expensive resource that must be multiplexed, not hoarded. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. What is the difference between session pooling and transaction pooling in a proxy like PG Bouncer?
Answer. Session pooling keeps a one-to-one mapping between a client and a server connection for the entire life of the client's session. It only saves on the cost of the TCP handshake. Transaction pooling, senior standard, releases the server connection back to the pool as soon as a single commit or rollback is received. This allows 1,000 pods to operate comfortably using only 50 physical database connections.
Senior follow-up 2, the scale and trade-off trap. You move to transaction pooling. Which common application feature will now break?
Answer: prepared statements and session-level variables, like SCT search_path. Because the next statement in your application might be executed on a different physical database connection, any state you set in the previous transaction will be lost. You must either disable these features in the app or use session mode with its higher resource cost.
Senior follow-up 3, the day 2 migration reality. You are using a cloud-native database like AWS Aurora. Does it handle this problem for you?
Answer: partially. AWS Aurora has a RDS proxy service that performs transaction-level multiplexing natively. It is the recommended path for serverless architectures, like Lambda, where hundreds of short-lived executions would otherwise overwhelm the database's connection limits.
Senior follow-up 4, Curveball. Your connection count is low, your pool is perfect, but the app still fails with could not get connection. You check the logs and see too many open files. Why did your DB fix fail to solve the app error?
Answer: constraint scenario. This is a Linux file descriptor limit. Even if the DB has space, each network connection uses a file descriptor on the application node. If your pod's ULIMit or the node's file max is set too low, the OS will refuse to open the network socket for the connection. You must tune the kernel limits in the pod security context.
Pro tip, the Hikari CP leak detection.
If you are using Java, always set leak detection threshold in your Hikari CP pool configuration. Setting this to 2,000 milliseconds will cause the pool to log a stack trace of any code that holds a connection for longer than 2 seconds without using it. It is the most effective way to find logical leaks in your code before they reach production scale.
The Senior Dev Ops Incident 50, the gradual latency creep.
It is Monday morning. Your P99 latency dashboard shows a slow, upward trend that has been climbing for 3 months. What used to take 50 milliseconds now takes 400 milliseconds. No new code was deployed this morning, and the CPU is stable. You check the database. The volume of data has doubled, but you have indexes in place. Suddenly, the latency jumps from 400 milliseconds to 5 seconds in a single hour. Your query plans have just flipped, and your database has decided that its once trusted indexes are now useless.
Symptoms, the panic moment.
Here is the behavior of the database during the performance collapse. 1. P99 latency, slow increase over months, followed by a vertical cliff where performance falls apart. 2. Database load, disk I/O weight, and CPU usage on the database nodes have suddenly spiked to 90%. 3. Query pattern, the exact same SQL query that was fast yesterday is now timing out today. 4. Storage state, pg_stat_user_tables shows that the n_dead_tup count is in the millions for the primary table. Decision tree signal, if latency increases gradually with data volume, and then spikes suddenly without code changes, then always suspect a query plan flip or table bloat.
Hypothesis, thinking like a senior.
A junior might try to add more RAM to the database. As a senior, I analyze the query execution plan and the table statistics. Hypothesis 1, missing index, ruled out. The index scan was confirmed in the logs last week. Hypothesis 2, hardware degradation, ruled out. Synthetic I/O tests show the NVMe drives are operating at peak performance. Hypothesis 3, plan degradation. The database optimizer has decided that because the table has grown so large or because the data distribution has shifted, a sequential scan is now cheaper than an index scan, even if that decision is catastrophically wrong. To verify this, we must use the explain analyze command to see the reality of the execution. Investigation, the 6-step debugging masterclass.
Step-by-step performance forensics.
We must prove the database is taking the wrong path. We execute these steps. 1. Execute explain analyze. We run the slow query with the explain prefix. We see sec_scan instead of the expected index scan. 2. Inspect table statistics. We check pg_stats and realize the last _analyzed timestamp was 3 days ago. The database is making decisions based on old data. 3. Check table bloat. We query pg_stat_user_tables for dead_tuples. We find that 40% of the table consists of deleted rows that haven't been vacuumed. 4. Verify data distribution. We find that the status column, which used to have 10% pending, now has 99% pending, making the index useless for that specific value. 5. Trace auto vacuum. We check the logs and find that auto vacuum was being canceled every night by a heavy backup job, preventing it from finishing. 6. Root cause identified. Stale statistics leading to plan flip. Because auto vacuum never finished, the database didn't know the table had grown or that the data was bloated. It reached a tipping point where the optimizer mathematically determined that reading the whole disk was faster than using the fragmented index. Let us look at the explain output that revealed the sub-optimal execution plan. The evidence, the query plan flip. This is the disaster. A sequential scan means the database is reading every single block on the disk for this query. The index exists, but the database is ignoring it because its internal statistics are stale.
The fix: manual statistics refresh and index rebuild.
We must force the database to re-evaluate its reality and reclaim the bloated space. Senior warning: do not run vacuum full on a live production table. It takes an exclusive lock and will effectively take your entire application offline for the duration of the rebuild. Use non-blocking maintenance tools instead. Here is the SQL implementation for forcing a plan refresh and non-blocking index optimization. Disclaimer: always test code in a non-production environment. This is the immediate fix. It updates the database's internal histogram of data distribution. Once the database realizes the index is actually efficient, it will flip the plan back to index scan and latency will drop instantly. This is the senior grade way to fix index fragmentation. It builds the new index in the background while users are still writing to the table, ensuring zero downtime for the application.
Prevention and guardrails: the post-mortem.
To prevent gradual latency creep from becoming a crisis, we implement these guardrails. 1. Auto vacuum tuning. We decrease auto vacuum _vacuum _scale _factor to 0.01, forcing the database to clean up dead tuples much earlier before bloat accumulates. 2. Index monitoring. We add a Datadog alert for index usage versus table scans. If the ratio of sequential scans on a large table increases, the team is alerted to check for plan flip. 3. Weekly analyze jobs. We schedule a weekly maintenance job that runs a manual analyze on all tables during low traffic windows to ensure the optimizer always has fresh data. A senior engineer knows that database performance is not static. It is a decaying asset that requires constant maintenance. The senior follow-up stack.
Senior follow-up 1: mechanism deep dive. What is the tipping point in a database optimizer, and why does it cause a sudden performance cliff?
Answer: the tipping point is the mathematical threshold, where the optimizer calculates that the cost of reading an index plus the cost of random I/O to fetch the rows is higher than the cost of a single sequential read of the whole table. This typically happens when a query returns more than 5 to 10% of the total rows in a table.
Senior follow-up 2: the scale and trade-off trap. You move to create index concurrently to avoid downtime. What is the resource trade-off during the build?
Answer: CPU and I/O saturation. A concurrent index build requires 2 full table scans and keeps an open transaction for a long time. While it does not lock the table, it can significantly slow down existing user queries due to disk contention. You trade availability for throughput during the maintenance window.
Senior follow-up 3: the day 2 migration reality. You are moving from a relational DB to a NoSQL DB like DynamoDB to avoid plan flips. Do you still face latency creep?
Answer: yes, but the cause shifts. In NoSQL, latency creep is usually caused by hot partitions or large items. As your data grows, if your partition key is not distributed evenly, you will hit I/O limits on a single physical shard, leading to throttling regardless of your total provision capacity.
Senior follow-up 4: curveball. You have fresh statistics and a perfect index. Yet the query is still slow and using a sec scan. You realize the query uses where upper email equals, but the index is on the email column. How do you fix this without changing the application code?
Answer: hidden cause, expression mismatch. A standard index cannot be used if the column is wrapped in a function. As a senior architect, You do not wait for a code fix. You deploy a functional index using create index on user's upper email. This allows the database to match the expression directly to the index, restoring performance instantly without a single line of application code change.
Pro tip: the PG_stat_statements extension.
Always enable PG_stat_ statements in your production Postgres clusters. It records a history of every query plan, total execution time, and memory usage. It allows you to find the top 10 most expensive queries across your entire history, making it trivial to identify latency creep before it turns into a vertical spike.
The Senior Dev Ops Incident 51. The mirror of the past, replica inconsistency.
It is a high-traffic Monday. You receive reports that users are updating their shipping addresses, receiving a success message, but when the page refreshes, they see their old address. The developers are baffled because the data is correctly saved in the primary database. You check the architecture and realize the front end is reading from a pool of read replicas to save costs. You are facing the nightmare of distributed stale reads, where your replicas are trapped in the past while your primary lives in the future.
Symptoms: the panic moment.
Here is the behavior of the inconsistent data layer during the lag event. 1. Read after write failure. Users see old data immediately after a successful update. 2. Metric mismatch. The primary DB shows 0% error rate, but the read replicas are lagging by 30 seconds. 3. Replication lag. CloudWatch or Prometheus shows a linear climb in the replication lag metric. 4. Resource load. The primary DB is under heavy write load due to a large-scale data migration running in the background. Decision tree signal. If data is correct in the primary but old in the replicas, and the lag metric is non-zero means, then always suspect replication lag, inducing stale reads.
Hypothesis: thinking like a senior.
A junior might try to restart the replicas. As a senior, I analyze the streaming integrity. Hypothesis 1, network partition, ruled out. The primary can still ping all replicas, the connection is open. Hypothesis 2, disk full on replica, ruled out. Replicas have 40% free storage. Hypothesis 3, wall saturation. A massive background update job on the primary is generating more write-ahead logs than the network or the replica's apply thread can handle, creating a backlog of state changes. To verify this, we must inspect the replication slots and the wall streaming rate. Investigation, the 6-step debugging masterclass.
Step-by-step consistency forensics.
We must prove the apply thread is the bottleneck. We execute these steps. 1. Query replication stats. We run PG_stat_replication on the primary. We see the write_lag is low, but flush_lag and replay_lag are massive. 2. Identify the volume. We check the size of the wall directory. It has grown from 1 GB to 50 GB in 1 hour. 3. Inspect primary activity. We find a batch update script running without a sleep interval, updating 5 million rows. 4. Check replica CPU. We see the replica CPU is at 100% on a single core. This is the single-threaded replay bottleneck. 5. Validate front-end logic. We find the front-end performs a redirect to a GET request immediately after a post without any consistency token. 6. Root cause identified. Asynchronous replication bottleneck. The primary is generating data changes faster than the replica's single-threaded replay engine can process them. Because the application uses a naive read from replica strategy, users are served data from a point in time before their own update. Let us look at the SQL metadata that exposed the replay bottleneck. The evidence, replay lag versus write lag. We query the internal replication view to compare the time data was written versus the time it was actually replayed into the database files. This is the smoking gun. While the write lag is low, the replay lag is over 35 seconds. The user is physically looking 35 seconds into the past because the replica cannot keep up with the primary.
The fix: implementation of causal consistency.
We must move critical read after write requests to the primary or implement a consistency-aware routing layer. Senior warning: do not switch all reads to the primary. This will immediately crash your primary DB under the combined load. You must only route freshness-sensitive traffic to the primary or implement a version check at the application layer. Here is the JavaScript implementation for consistency, Aware database routing. Disclaimer: always test code in a non-production environment. This is the senior grade fix. By tracking the last write timestamp in a fast cache like RIDIS, we only send at-risk users to the primary. The other 99% of users continue to use the replicas, preserving your scale.
Prevention and guardrails, the post-mortem.
To prevent distributed stale reads from recurring, we implement these guardrails. 1. Throttled batch jobs. We mandate that any data migration script must include a sleep interval to ensure wall generation does not exceed the replication bandwidth. 2. Lag-aware load balancing. We configure our DB proxy, like Proxy SQL or PG Pool, to automatically remove a replica from the pool if its lag exceeds 2 seconds. 3. Application consistency tokens. We implement LSN, log sequence number tracking. The client receives the LSN of their write, and the replica refuses to serve the read until it has replayed up to that LSN. A senior engineer understands that eventual consistency is a promise that requires architectural enforcement. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why is Postgres replication replay single-threaded, and why does this cause a bottleneck?
Answer: consistency and sequencing. Wall logs represent a linear history of changes. To ensure data integrity, changes must be applied in the exact order they occurred. Parallelizing this is extremely complex because 2 different transactions might modify the same row. While modern versions have parallel replay for different databases, a single high write table remains bound by the speed of a single CPU core.
Senior follow-up 2, the scale and trade-off trap. You decided to move to synchronous replication to solve the lag. What is the impact on your write availability?
Answer: increased outage risk. In synchronous mode, the primary will block every write until at least one replica confirms it has received the data. If your network blips or your replicas go down, your primary will stop accepting all writes, turning a lag problem into a total outage problem.
Senior follow-up 3, the day 2 migration reality. You are moving to a multi-cloud database. How do you handle global stale reads across continents?
Answer: regional pinning. We use a global primary in US East 1 and replicas globally. For users in Asia, we implement session pinning. Once a user performs a write, we pin their session to the US East 1 primary for 60 seconds before allowing them to read from the local Singapore replica again. This trades cross-continental latency for data correctness.
Senior follow-up 4 Curveball. You have 0 replication lag. Replicas are caught up. Yet the user still sees old data. You check the DB and the data is correct. Where is the state hidden?
Answer: the L3 cache trap. A senior engineer looks at the browser or the CDN. If your API responses have cache control headers that allow the browser to cache the shipping address for 5 minutes, the browser will never even hit your database. You must ensure that post requests trigger a cache invalidation or use cache control. No store for sensitive profile data.
Pro tip, the PG_while_inspect rule.
If you see replication lag spiking, run select star from PG_LS_Waldir. If you see hundreds of small files being generated every second, you have a micro update problem. Converting many small updates into a single batch transaction will reduce the wall metadata overhead and allow the replica to catch up significantly faster.
The Senior Dev Ops Incident 52, the hot partition shard crash.
You are managing a 10-node NoSQL cluster. Your global monitoring says CPU usage is at a comfortable 15%. However, the checkout service is timing out for your largest customer, a global retail giant. You look at the node metrics and find a nightmare. 9 nodes are completely idle, while node number 7 is pegged at 100% CPU and dropping every request. You have a hot partition where your data distribution logic has accidentally funneled an entire continent's traffic into a single physical server.
Symptoms, the panic moment.
Here is the behavior of the unbalanced cluster during the hotspot event. 1. Skewed utilization. Node 7 is at 100% CPU. Nodes 1 to 6 and 8 to 10 are at 2% CPU. 2. Selective outage. Only users belonging to organization_ID_99 are experiencing errors. Everyone else is fast. 3. Database throttling. The database engine is throwing provisioned throughput exceeded errors despite the cluster having 90% idle capacity. 4. Latency spikes. Read/write latency on Node 7 has jumped from 5 milliseconds to 2000 milliseconds. Decision tree signal. If cluster-wide CPU is low but one node is on fire, and the errors are isolated to a specific key means, then always suspect a hot partition.
Hypothesis, thinking like a senior.
A junior might try to scale the whole cluster to 20 nodes. As a senior, I analyze the partition key entropy. Hypothesis 1, hardware failure on node 7, ruled out. Moving the data to a different node results in that new node immediately hitting 100% CPU. Hypothesis 2, malformed query, ruled out. The query structure is identical for all organizations. Hypothesis 3, low entropy partition key. The database uses organization_ID as the shard key. Because one organization is 1,000 times larger than the others, all of their data and traffic are physically locked to the same shard, creating a bottleneck that no amount of cluster scaling can fix. To verify this, we must perform a key distribution analysis on the live traffic. Investigation, the 6-step debugging masterclass.
Step-by-step shard forensics.
We must prove the traffic is mathematically unbalanced. We execute these steps. 1. Identify the shard key. We check the schema and find the partition key is tenant_ID. 2. Capture traffic samples. We use TCP dump or database audit logs to count requests per tenant_ID. 3. Map keys to nodes. We query the database's internal routing table to see which shard node 7 is responsible for. 4. Analyze data density. We find that tenant 99 has 10 million records, while the average tenant has 500. 5. Identify large item pattern. We realize that tenant 99 is also performing a scan operation on their partition, which requires node 7 to read its entire local disk. 6. Root cause identified. Shard key skew. By choosing a business ID with highly variable volume as the partition key, we created logical hotspots. Node 7 became a single point of failure for the largest customer because the database's hashing algorithm cannot split a single key across multiple nodes. Let us look at the traffic distribution that proved the shard skew. The evidence, request distribution by key. The data is undeniable. A single key is responsible for 99% of the incoming traffic. Because this key cannot be divided, Node 7 is being DDoSed by a legitimate user.
The fix, implementation of key salting.
We must break the one key, one node limitation by adding a random suffix, a salt, to the partition key for large tenants. Senior warning, salting a key makes reads much harder. You can no longer query for tenant_99 in one call. You must now query for tenant_99_1, tenant_99_2, and so on, and merge the results. Only salt keys that have proven to be hotspots. Here is the JavaScript implementation for shard key salting to distribute hot data. Disclaimer, always test code in a non-production environment. By adding a random number to the key, we force the database to hash the data to different shards. Tenant 99 traffic is now spread across all 10 nodes in the cluster, restoring balance.
Prevention and guardrails, the post-mortem.
To prevent hotspots from taking down the platform again, we implement these guardrails. 1. Composite keys. We mandate using high-entropy composite keys, for example, tenant_ID plus user_ID, to ensure natural distribution of data. 2. Adaptive throttling. We implement per key rate limiting at the API gateway. If a single tenant ID exceeds 5,000 requests per second, we throttle them specifically to protect the underlying shard. 3. Shard density alerts. We set a Datadog alert for standard deviation of CPU across nodes. If the deviation is high, it indicates an imbalance that requires resharding. A senior engineer knows that a scalable system requires a perfectly uniform distribution of work. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. How does consistent hashing work in distributed databases, and why does it fail for hot keys?
Answer, consistent hashing maps keys to a logical circle. Nodes are assigned positions on that circle. A key is hashed to a number, and you travel clockwise to find the responsible node. It handles node additions/removals perfectly, but it fails for hot keys because a single key always hashes to the exact same point on the circle, and therefore the exact same node.
Senior follow-up 2, the scale and trade-off trap. You move to salting for Tenet 99. What is the impact on your search and aggregation performance?
Answer: the fan-out penalty. Before salting, a query for total sales for Tenet 99 was a single node operation. Now, it is a multi-node operation that requires gathering data from 10 different servers. This increases network overhead and the risk of tail latency. If one node is slow, the whole query is slow.
Senior follow-up 3, the Day 2 migration reality. You are using AWS DynamoDB. Can you use adaptive capacity to solve this instead of salting?
Answer: partially. DynamoDB adaptive capacity will automatically move the throughput from idle shards to node 7. However, even adaptive capacity cannot exceed the physical IOPS limit of a single physical partition, usually 3000 RCU/1000 WCU. If Tenet 99 exceeds that single partition hardware limit, salting is the only architectural solution.
Senior follow-up 4, Curveball. Your keys are uniform. CPU is balanced. Yet Node 7 is still slow. You find that Tenet 99 is storing 400 kilobytes items, while others store 2 kilobytes items. How does item size create a hotspot?
Answer: throughput skew. Even if the request count is equal, Node 7 is processing 200 times more data per request. In most distributed systems, I/O and network bandwidth are the real constraints. A senior engineer enforces max item size limits to ensure that one heavy user cannot saturate the node's I/O bus.
Pro tip, the UUID v4 rule.
Avoid using sequential IDs, like timestamps or auto-incrementing integers, as shard keys. Sequential IDs always target the latest shard, creating a permanent hotspot at the end of your cluster. Always use a high-entropy UUID v4 or a hash of the data as your primary partition key to ensure the data is naturally exploded across all available nodes from day one.
The Senior Dev Ops Incident 53, the EBS Burst Credit Time Bomb.
It is 2 p.m. on a Tuesday. Your database has been performing flawlessly for 4 hours after a heavy morning re-indexing job. Suddenly, without any increase in traffic, the P99 latency jumps from 2 milliseconds to 800 milliseconds. The application logs are flooded with database timeout. You check the CPU, it is idle. You check the network, it is empty. Your database is healthy, but its storage has just hit a performance wall. You have exhausted your EBS burst credits.
Symptoms, the panic moment.
Here is the data from the storage observability during the performance collapse. 1. Sudden latency cliff. Disk latency increases by 400 times in a single minute. 2. Throughput plateau. The disk read bytes and disk write bytes metrics are perfectly flat at suspiciously low number. 3. CPU I/O weight. The WA metric in Linux top is spiking to 80%, while user CPU is near 0. 4. Volume type. The database is running on an AWS GP2 volume with a size of 100 gigabytes. Decision tree signal. If disk latency spikes suddenly after a period of heavy load and throughput hits a flat ceiling, then always suspect EBS burst credit exhaustion.
Hypothesis, thinking like a senior.
A junior might try to reboot the server. As a senior, I analyze the storage credit balance. Hypothesis 1, hardware failure in the cloud. Ruled out. AWS personal health dashboard shows 0 issues in the region. Hypothesis 2, file system corruption. Ruled out. Read-only tests show data integrity is fine. Hypothesis 3, burst credit exhaustion. AWS GP2 volumes use a bucket and token system. The morning re-index job consumed all the tokens. The volume has now been throttled to its baseline performance, which is insufficient for the current database traffic. To verify this, we must check the specific CloudWatch metric for burst balance. Investigation, the 6-step debugging masterclass.
Step-by-step IOPS forensics.
We must prove the storage is being artificially throttled. We execute these steps. 1. Check volume type. We confirm the volume is GP2. We know that GP2 baseline IOPS is 3 per GB. 2. Calculate baseline. Our 100 gigabytes volume has a baseline of only 300 IOPS. Our app requires 2000 IOPS. 3. Query CloudWatch. We pull the burst balance metric for the volume ID. It is sitting at exactly 0%. 4. Trace I/O spikes. We look at the history and see the morning re-index job sustained 3,000 IOPS for 2 hours, draining the 5.4 million credit bucket. 5. Analyze I/O wait. We run IOstat-DX1 and see a wait times of 500 milliseconds and util at 100%. 6. Root cause identified. Hidden resource depletion. The team chose GP2 storage to save money, not realizing that performance was temporary. Once the credit bucket was empty, the volume's throughput was slashed by 90%, causing a cascading failure in the application thread pool. Let us look at the CloudWatch metrics that prove the credit bankruptcy. The evidence: EBS burst balance at 0. The CloudWatch metric for burst balance is the primary health indicator for GP2 volumes. A value of 0 means the volume has no more high-performance tokens and is now being throttled to its baseline. The IOstat output confirms the hardware-level bottleneck. Even though the application is requesting more, the read operations per second are capped exactly at the 300 IOPS baseline of this 100 gigabytes volume.
The fix: migrating to provision throughput.
We must immediately upgrade the volume type to GP3 or IO2 to provide a guaranteed performance baseline. Senior warning: do not just increase the size of the GP2 volume to 1 terabytes to get more IOPS. This is an expensive and permanent change. The correct senior fix is to migrate to GP3, which allows you to provision IOPS and throughput independently of the disk size. Here is the CLI implementation for a zero downtime EBS volume upgrade from GP2 to GP3. Disclaimer: always test code in a non-production environment. By switching to GP3, you immediately break out of the burst credit system. The volume now has a guaranteed 3,000 IOPS regardless of its size. Latency will drop back to 1 milliseconds within seconds.
Prevention and guardrails: the post-mortem.
To ensure our storage performance is permanent, we implement these guardrails. 1. GP3 standardization. We update our Terraform modules to forbid the use of GP2 for any production workload, enforcing GP3 with a minimum of 3,000 provision IOPS. 2. Burst balance alerting. We set a Datadog alert on aws.ebs.burst_balance. If it drops below 50%, the team is alerted to perform a proactive volume upgrade. 3. I/O detachment. We move heavy temporary workloads like log processing or build artifacts to local instance store NVMe, which has no IOPS limits, protecting our networked EBS volumes. A senior engineer knows that in the cloud you do not just pay for space, you pay for the speed of access. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. What is the difference between IOPS and throughput, megabytes per second, in EBS performance?
Answer: IOPS measures the number of read per write operations per second, small random access, like a database. Throughput measures the total volume of data moved per second, large sequential access, like a backup. A volume can be limited by either. If you have high IOPS but low throughput, your large database queries will still be slow.
Senior follow-up 2, the scale and trade-off trap. You move to IO2 volumes for maximum performance. What is the cost trade-off for a 10 terabytes database?
Answer: extreme cost. IO2 volumes charge significantly more per provisioned IOPS than GP3. If you provision 50,000 IOPS, your storage bill could easily exceed your compute bill. You must use storage tiering to move cold data to cheaper S3 volumes to balance cost and performance.
Senior follow-up 3, the day 2 migration reality. You are using Kubernetes. How do you handle volume throttling when multiple pods share the same underlying node storage?
Answer: I/O isolation. In standard Kubernetes, pods share the node's disk bandwidth. If one pod saturates the I/O, every other pod on that node suffers. A senior engineer uses storage classes with IOPS limits or implements cgroup v2-based I/O throttling to ensure no single container can starve the rest of the cluster's storage.
Senior follow-up 4 curveball. Your burst balance is at 100%. Your IOPS are low. Yet disk latency is still 500 milliseconds. You check the node and find CPU is high. How can CPU cause disk latency?
Answer: the Nitro hypervisor limit. A senior engineer knows that EC2 instances have instance-level storage limits in addition to volume-level limits. If you have 5 fast volumes but a small instance type, like T3.micro, the physical network interface of the instance will saturate. The bottleneck is the small pipe between the CPU and the EBS network.
Pro tip, the micro-bursting trap.
Standard 1-minute CloudWatch metrics often hide micro-bursting. A database might saturate the disk for 500 milliseconds and then be idle for 500 milliseconds. CloudWatch will show 50% utilization, but your users will experience high latency. Always use node-level metrics, like Prometheus node_exporter, with 1-second resolution to find the hidden I/O bursts that kill application performance.
Category 11, wrap up, protecting the source of truth.
Category 11 has exposed the high-stakes reality of stateful workloads. We have seen that senior engineering is not just about writing data, but about guaranteeing its integrity across distributed boundaries. We learned that treating local storage as persistent is a scaling death sentence, and that the Postgres transaction engine has hard mathematical limits that can force a total shutdown. We uncovered how network blips can shatter database consensus, leading to the nightmare of split brain and data divergence. A senior DevOps engineer knows that while containers are ephemeral, data is permanent. Mastering stateful survival means building architectures where consistency is not a hope, but a mathematical certainty enforced by fencing, quorum, and rigorous resource management.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
Now that we have secured the data at rest, we must address the data in motion. We are moving from the storage engines to the communication highways of distributed systems. We are entering the domain of distributed messaging and consensus.
Category 12, distributed messaging and consensus.
Focus, managing consistency and flow in distributed architectures. In this section, we examine the failures that occur when microservices talk to each other across asynchronous queues and stateful brokers. We will explore the cascading failures that turn a small blip into a system-wide outage, the Kafka rebalance storms that paralyze event processing, and the consensus loss in Vault that can lock you out of your own secrets. When components communicate asynchronously, the order of operations becomes your biggest enemy. This is where you prove you can manage the complexity of the distributed swarm.
Category 12, incident list.
We will perform reference-grade deep dives into these 6 critical distributed system failures. Scenario 54, cascading failure, how fragile dependency chains and aggressive health checks take down the entire ecosystem. Scenario 55, queue backlog storm, solving consumer lag and partition rebalance storms in Kafka. Scenario 56, idempotency failure, fixing duplicate message processing that leads to data corruption. Scenario 57, out-of-order events, managing timing and sequence issues in distributed event streams. Scenario 58, circuit breaker failure, when misconfigured thresholds provide zero protection during an outage. Scenario 59, Vault Raft consensus loss, recovering when network partitions take your global secret store offline. Let us start with the most dangerous domino effect in microservices, the cascading failure.
The Senior Dev Ops Incident 54, the cascading death spiral.
It is 10 a.m. A minor latency spike occurs in your legacy inventory database. Within 60 seconds, the inventory service starts failing health checks and Kubernetes restarts the pods. Suddenly, the order service, the checkout service, and the shipping service all start crashing and restarting in a synchronized loop. You have 500 pods in a permanent crash loop back off. The database is now healthy, but your entire microservice ecosystem has entered a self-reinforcing death spiral that no amount of scaling can stop.
Symptoms, the panic moment.
Here is the behavior of the collapsing service graph during the spiral. 1. Synchronized restarts. Every service in the dependency chain is restarting at the same time. 2. Resource exhaustion. Kubernetes API server is struggling to handle thousands of pod scheduled and pod terminated events per minute. 3. Database impact. The database CPU is at 100% despite zero user traffic, crushed by the connection surge from 500 pods booting simultaneously. 4. Log pattern. Application logs show connection refused followed by an immediate sigterm. Decision tree signal. If a minor dependency blip causes multiple unrelated services to restart in a loop, then always suspect a cascading failure triggered by tight health check coupling.
Hypothesis, thinking like a senior.
A junior might try to scale the pods or the database. As a senior, I analyze the control loop feedback. Hypothesis 1, global network outage, ruled out. VPC internal connectivity is verified as healthy. Hypothesis 2, malformed deployment, ruled out. No deployments have occurred in the last 4 hours. Hypothesis 3, health check contagion. The microservices are using deep health checks where service A fails its liveness probe if its dependency service B is slow. This creates a recursive failure where the entire cluster kills itself because one low-level component is latent. To verify this, we must inspect the pod liveness probe definitions across the fleet. Investigation. The 6-step debugging masterclass.
Step-by-step cascade forensics.
We must find the trigger for the mass execution. We execute these steps. 1. Audit pod events. We run kubectl get events and find that liveness probes are failing across all tiers simultaneously. 2. Analyze probe logic. We check the /health endpoint code. We find it performs a ping to every downstream dependency before returning 200. 3. Measure boot surge. We see that when a pod restarts, it opens 50 database connections during initialization. With 500 pods restarting, we see 25,000 connection requests per minute. 4. Check database state. The DB is now healthy, but it cannot handle the connection storm from the booting pods, causing the new pods to fail their health check and restart again. 5. Identify the liveness trap. We realize the liveness probe is killing pods for a problem that is external to the pod, which is a violation of Kubernetes best practices. 6. Root cause identified, recursive dependency coupling. By making liveness dependent on downstream availability, the team created a system where a transient database slowdown was translated into a permanent cluster-wide restart loop. The thundering herd of booting pods ensured the database could never recover. Let us look at the toxic health check code that triggered the domino effect. The evidence, the recursive health check trap. This is the architectural violation. Liveness probes should only check things local to the pod. By checking the database, you are telling Kubernetes, if the database is slow, kill me. This guarantees a cascading failure.
The fix, decoupling liveness from readiness.
We must refactor the health checks to separate internal vitality from external readiness and implement exponential backoff on startup. Senior warning, do not just delete your health checks. A pod without a liveness probe can become a zombie that accepts traffic but does nothing. You must use readiness probes for dependencies and liveness probes purely for local process health. Here is the JavaScript implementation for decoupled and resilient health check logic. Disclaimer: always test code in a non-production environment. The liveness probe now only checks if the process is physically running. If the database goes down, the pod stays alive but stops being ready. Kubernetes stops sending it traffic but does not restart it, preventing the connection storm.
Prevention and guardrails, the post-mortem.
Prevent cascading death spirals in the future. We implement these guardrails. 1. Circuit breakers. We implement Resilience 4J or Istio outlier detection. If service B is slow, service A opens the circuit and returns a cached response rather than failing its own health check. 2. Startup probes. We use startup probes in Kubernetes to give pods a long window, for example, 5 minutes, to initialize without being killed by a premature liveness check. 3. Gradual rollouts. We use max unavailable, 10% in our deployment specs to ensure that even during a bad update, the majority of the fleet stays online to absorb the load. A senior engineer knows that the goal of a health check is to manage traffic, not to execute pods. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. What is the physical difference between how Kubernetes handles a liveness failure versus a readiness failure?
Answer: a liveness failure causes the kubelet to physically sig-kill the container and restart it. This is destructive and clears local state. A readiness failure simply removes the pod IP from the service endpoint list. The pod stays running but stops receiving new traffic. Readiness is for I am busy. Liveness is for I am broken beyond repair.
Senior follow-up 2, the scale and trade-off trap. You move dependency checks to the readiness probe. During a total database outage, all 500 pods will report not ready simultaneously. What happens to your ingress layer?
Answer: empty load balancer. If every pod is not ready, the Kubernetes service has 0 endpoints. The ingress, like Nginx, will have nowhere to send traffic and will return 502 bad gateway to 100% of users. This is actually better than a cascade because it preserves the cluster state and allows the database to recover without being DDoSed by pod restarts.
Senior follow-up 3, the day 2 migration reality. You are moving to a service mesh. Does the service mesh solve cascading failures for you?
Answer: yes, through outlier detection. The mesh monitors the success rate of requests to individual pods. If one pod starts returning 500 level errors, the mesh ejects it from the load balancing pool temporarily without needing a Kubernetes health check. This provides a faster, more granular response to partial failures before they can cascade.
Senior follow-up 4 curveball. You have perfect decoupled probes. Yet, during a database blip, your CPU across the cluster still spikes to 100%, and the app becomes unresponsive. Why did the probes fail to protect you?
Answer: hidden cause, the retry storm. Even if the pods are not restarting, your application code or your load balancer might have an aggressive retry on failure policy with no backoff. If 1,000 clients retry a failed request 3 times every second, they create a virtual DDoS that saturates the CPU and network, regardless of pod health. You must implement jitter and exponential backoff in your client libraries.
Pro tip, the fail-fast initialization.
If your application requires a database to boot, perform the connection check in the main function, not the liveness probe. If the DB is down, the app should exit with code 1 immediately. This allows Kubernetes to see the crash loop, but prevents the liveness controller from killing a pod that has already successfully initialized and is merely waiting for a dependency to return.
The Senior Dev Ops Incident 55, the Kafka Consumer Rebalance Storm.
It is Monday morning. You are processing millions of payment events through a Kafka cluster with 50 partitions. Suddenly, the message processing rate drops to 0. You check the consumer pods. They are running, but they are not doing any work. Every few minutes they stop, wait for 30 seconds, and then start again, only to stop once more. Your consumer group has entered a rebalance storm, where the cluster is spending 100% of its time arguing about who owns which data, and 0% of its time actually processing it.
Symptoms, the panic moment.
Here is the behavior of the paralyzed event pipeline during the storm. 1. Processing stalls. The records per second metric for the consumer group is a flat 0. 2. Consumer lag. The Kafka consumer lag metric is increasing vertically as millions of new messages arrive. 3. Log pattern: consumer logs are flooded with revoking partitions, followed by successfully joined group, followed by group coordinator rebalanced. 4. Pod state: pods are healthy and running, but CPU usage is fluctuating wildly as they constantly connect and disconnect from Kafka. Decision tree signal: if processing drops to 0 and logs show constant partition revocation, while pods are alive, then always suspect a Kafka rebalance storm.
Hypothesis: thinking like a senior.
A junior might try to scale the number of consumers. As a senior, I analyze the heartbeat and processing timers. Hypothesis 1: Kafka broker failure, ruled out. The brokers are green and other consumer groups are working perfectly. Hypothesis 2: network latency between consumer and broker, ruled out. Ping times are under 1 milliseconds within the VPC. Hypothesis 3: processing timeout. A specific set of poison pill messages is taking longer to process than the max.poll.interval.ms. Kafka thinks the consumer has died because it hasn't asked for more data, so it kicks it out of the group, triggering a global rebalance. To verify this, we must compare the processing time of a single message against the Kafka client configuration. Investigation: the 6-step debugging masterclass.
Step-by-step messaging forensics.
We must find the message that is stalling the world. We execute these steps. 1. Monitor consumer logs. We find the last message successfully processed before a revocation. It is always a specific heavy report request. 2. Measure processing time. We trace the execution of that specific request. It takes 305 seconds to complete. 3. Check Kafka config. We inspect the application properties. We find max.poll.interval.ms is set to the default of 300,005 minutes. 4. Verify the kickout. We see that at 301 seconds, Kafka marks the consumer as dead because it hasn't called .poll again. 5. Identify the storm. When that consumer is kicked, its 5 partitions are reassigned. This forces all other 49 consumers to stop and wait for a new assignment. When the dead consumer finishes its 305-second task, it tries to rejoin, triggering yet another rebalance. 6. Root cause identified: poll interval violation. The application was performing synchronous heavy lifting inside the main Kafka consumer thread. Because the processing time exceeded the poll timeout, the consumer group entered an infinite loop of rebalancing, effectively locking the entire pipeline. Let us look at the Kafka metrics that expose the rebalance frequency. The evidence: rebalance frequency spikes. This is the keep alive for the logic, not the network. If your code takes longer than this to process one batch of messages, Kafka assumes your application has hung and forcefully redistributes your work to someone else.
The fix: decoupling polling from processing.
We must move the heavy business logic to a separate worker thread pool, allowing the Kafka thread to continue calling .poll and maintaining its group membership. Senior warning: do not simply increase max.poll.interval.ms to 1 hour. This will make the system extremely slow to react to real consumer failures. If a consumer actually crashes, Kafka will wait the full hour before reassigning its partitions, causing a massive processing gap. Here is the Java implementation for an asynchronous Kafka consumer with background processing. Disclaimer: always test code in a non-production environment. By offloading the work to a separate thread pool, the main loop can immediately return to the top and call poll again. This signals to Kafka that the consumer is healthy and active, regardless of how long the background work takes.
Prevention and guardrails: the post-mortem.
To ensure messaging stability at scale, we implement these guardrails. 1. Static group membership. We upgrade to Kafka 2.3+ and implement group.instance.id. This allows a consumer pod to restart and reclaim its specific partitions without triggering a global rebalance for the rest of the fleet. 2. Poison pill detection. We implement a dead letter queue (DLQ). If a message fails or times out twice, we move it to a separate topic for manual review rather than letting it stall the primary pipeline. 3. Rebalance latency alerting. We set an alert on Kafka_consumer group_rebalance_latency_AVG. If a rebalance takes longer than 10 seconds, it indicates the cluster is over-partitioned or consumers are failing to close cleanly. A senior engineer knows that the consumer thread's only job is to communicate, not to compute. The senior follow-up stack.
Senior follow-up 1: mechanism deep dive. What is the difference between session.timeout.ms and max.poll.interval.ms in Kafka?
Answer: session.timeout.ms is a heartbeat at the network level. It detects if the pod crashed or the network died. Max.poll.interval.ms is a liveness check at the application level. It detects if the application logic is stuck or blocked. You can have a healthy heartbeat but still be kicked from the group if you fail to poll.
Senior follow-up 2, the scale and trade-off trap. You move to background worker threads. What is the risk regarding message ordering?
Answer: loss of sequentiality. Within a Kafka partition, messages are guaranteed to be in order. If you offload them to a multi-threaded pool, message 2 might finish processing before message 1. If your data is order-sensitive, like an account ledger, you cannot use a simple thread pool. You must use key-based sharding within your worker pool to ensure messages for the same user ID are handled by the same thread.
Senior follow-up 3, the day 2 migration reality. You are migrating to incremental cooperative rebalancing. How does this solve the storm problem?
Answer: partial rebalancing. In the old eager protocol, everyone stops for every change. In the cooperative protocol, only the specific partitions that need to move are revoked. The other 45 consumers can keep processing while the 5 partitions are being moved, significantly reducing the stop-the-world latency.
Senior follow-up 4 curveball. You have static membership and cooperative rebalancing, yet processing is still slow. You check consumer lag and it is only on 1 out of 50 partitions. Why?
Answer: the skewed key scenario. A senior engineer knows that Kafka routes messages to partitions based on the message key hash. If you have a hot key, like one massive customer generating 50% of the events, all of their data will go to the same partition. One consumer pod will be at 100% load, while 49 are idle. You must either change your partition key or implement sub-partitioning in your application.
Pro tip, the consumer group ID naming rule.
Never reuse a consumer group ID across different versions of your application logic. If you are deploying a breaking change in how you process data, append a version suffix to the group ID. This ensures that the new deployment starts fresh with its own offsets and prevents metadata poisoning where 2 different versions of the code are trying to coordinate on the same partition state.
The Senior Dev Ops Incident 56. The idempotency failure, the double charge disaster.
It is Monday morning. The finance team reports a catastrophic surge in support tickets. Customers are being billed twice for a single transaction. You check the billing microservice. It is healthy. You check the database. There are duplicate rows with the same metadata. You are using an asynchronous message queue to trigger payments, and your system has just learned the hard way that in distributed systems, at least once delivery means you must prepare for the second arrival. You are facing an idempotency failure.
Symptoms, the panic moment.
Here is the evidence of the duplicate processing event. 1. Data corruption. The transactions table shows 2 unique primary keys for the exact same order reference and timestamp. 2. Consumer metrics. The message consumer shows a spike in acknowledged messages that exceeds the number of published messages. 3. Log pattern. Application logs show processing payment for order 101 appearing twice, 3 seconds apart on 2 different pods. 4. Downstream impact. The Payment Gateway API dashboard confirms 2 separate successful charges for the same customer. Decision tree signal. If business logic executes twice for the same unique event, and the network had a transient blip, then always suspect an idempotency failure.
Hypothesis, thinking like a senior.
A junior might blame the user for clicking submit twice. As a senior, I analyze the delivery guarantees. Hypothesis 1, front-end double submit, ruled out. Ingress logs show only one post request from the user's IP. Hypothesis 2, message broker loop, ruled out. The broker is healthy and shows no message re-queuing. Hypothesis 3, producer retry or consumer timeout. The producer sent the message but didn't receive an ACK due to a network blip, so it retried. Or the consumer processed the message but crashed before ACKing, causing the broker to redeliver it. To verify this, we must inspect the message ID and the business key correlation in our logs. Investigation, the 6-step debugging masterclass.
Step by step, distributed deduplication forensics.
We must prove the system processed the same logical event twice. We execute these steps. 1. Isolate duplicate IDs. We query the logs for the specific order ID. we find two different internal message IDs linked to the same order ID. 2. Trace producer timeline. We see the producer sent the first message, waited 2 seconds, timed out, and sent a second message. 3. Audit consumer logic. We examine the code and find that it performs an insert without checking if the order ID already exists. 4. Verify transactional integrity. We check if the payment call and the DB update are in the same atomic block. They are not. 5. Check external API state. We query the payment gateway and find two distinct transaction IDs for the same idempotency key we failed to provide. 6. Root cause identified. Non-idempotent consumer logic. The system relied on the network being perfect. When a retry occurred at either the producer or broker level, the consumer treated the second message as a brand new request, triggering a second financial transaction. Let us look at the vulnerable code that allowed the double charge to happen. The evidence: vulnerable non-idempotent logic. This is a non-idempotent external side effect. If this function runs twice, the customer is charged twice. There is no unique key being passed to the gateway to prevent duplicates.
The fix: implementation of a deduplication table.
We must implement a distributed lock or a deduplication table that tracks processed message IDs before executing side effects. Senior warning: do not rely on Upsert alone. You must ensure that the check for the ID and the execution of the business logic are part of a guarded critical section to prevent race conditions where two pods process the same duplicate simultaneously. Here is the JavaScript implementation for idempotent message processing using a deduplication table. Disclaimer: always test code in a non-production environment. By using a database unique constraint as a distributed lock, we ensure that only one pod can win the right to process this order. The second pod will fail the insert and exit safely without charging the user.
Prevention and guardrails: the post-mortem.
Prevent duplicate processing from recurring. We implement these guardrails. 1. Mandatory idempotency keys. We update our SDK to require an idempotency key header for all outbound post requests to third-party APIs. 2. Database constraints. We add a unique index on the order_ID column in the transactions table, making it mathematically impossible to have two successful rows for one order. 3. Producer fingerprinting. We configure our message producers to attach a deterministic MSG_hash based on the payload, which consumers use for high-speed cache-based deduplication. A senior engineer assumes that every message will be delivered at least twice. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. What is the difference between at most once, at least once, and exactly once delivery in distributed systems?
Answer: at most once means messages can be lost but never duplicated. At least once, standard, means messages are never lost but can be duplicated. Exactly once is an abstraction achieved by combining at least once delivery with an idempotent consumer that filters out duplicates at the destination.
Senior follow-up 2, the scale and trade-off trap. You added a deduplication table in Redis for speed. What is the TTL trade-off?
Answer: memory bloat versus data integrity. If the TTL is too short, for example, 5 minutes, a delayed duplicate arriving after 6 minutes will be processed as new. If the TTL is too long, for example, 30 days, your Redis memory costs will skyrocket. You must match the TTL to the maximum possible network delay of your message broker.
Senior follow-up 3, the day 2 migration reality. You are moving to a serverless architecture. How do you handle idempotency in AWS Lambda without a persistent database connection?
Answer: we use DynamoDB with condition expressions. We attempt to put item with an attribute not exists, ID, condition. Lambda's scaling nature makes race conditions more likely, so the atomic nature of DynamoDB's check and set is the only reliable way to ensure idempotency at that scale.
Senior follow-up 4 curveball, your deduplication check passed. Your code is idempotent, yet you still see 2 charges. You realize the user refreshed the page, and the front-end generated 2 different order IDs for the same intention. How do you fix idempotency at the intent level?
Answer: constraint scenario. This is a client-side identity failure. A senior engineer knows that the idempotency key must be generated as early as possible. We should generate a draft ID the moment the user opens the checkout page and use that ID for all retries. The backend then deduplicates based on the user intent rather than the message ID.
Pro tip, the post redirect get pattern.
To prevent users from manually causing idempotency issues by clicking the refresh button on a browser, always implement the post redirect get pattern. After a successful payment, the server should never return HTML. It should return a 302 redirect to a success page. This moves the browser's state to a safe GET request, ensuring that a refresh does not resubmit the payment form.
The Senior Dev Ops Incident 57, the out-of-order event chaos.
It is Thursday afternoon. Your e-commerce platform is processing a flash sale. Suddenly, thousands of orders are stuck in a pending state, even though the payment was successful. You check the logs and see a series of errors, cannot cancel order that does not exist. You realize that the order canceled events are arriving at your microservices before the order created events. The timeline of your business has been shattered by the parallel nature of your own infrastructure.
Symptoms, the panic moment.
Here is the behavior of the chronological logic failure. 1. Logic deadlock. Microservices are rejecting valid state changes because the prerequisite state has not arrived yet. 2. Error pattern. High volume of not found errors for resources that eventually appear in the database a few seconds later. 3. Trace data. Distributed tracing shows that the order deleted timestamp is 50 milliseconds after order created, but the deleted event was processed 2 seconds before. 4. Queue behavior. The message queue has a massive backlog, and consumers are processing messages from multiple partitions in parallel. Decision tree signal. If business logic fails due to missing data that appears shortly after, then always suspect out of order event delivery.
Hypothesis, thinking like a senior.
A junior might try to add a sleep command to the consumer. As a senior, I analyze the sequential consistency of the pipeline. Hypothesis 1, database replication lag, ruled out. The created row is missing from the primary DB, not just the replica. Hypothesis 2, clock skew, ruled out. All servers are synced via NTP and the event timestamps are correct. Hypothesis 3, partition misalignment. The create and cancel events for the same order ID were sent to different Kafka partitions or handled by different consumer pods with different processing speeds, losing the original sequence of time. To verify this, we must check the partition key logic in the message producer. Investigation. The 6-step debugging masterclass.
Step-by-step sequence forensics.
We must find where the arrow of time was bent. We execute these steps. 1. Audit producer code. We find the code uses a random UUID as the Kafka partition key for every event. 2. Analyze event mapping. We realize this causes the create event to go to partition 1 and the cancel event to partition 5. 3. Measure consumer speed. Consumer pod A partition 1 is under heavy load and lagging. Consumer pod B, partition 5, is idle and lightning fast. 4. Trace the race. Pod B finishes the cancel event while the create event is still sitting in pod A's memory buffer. 5. Check state machine. We find the database schema requires an existing row before an update can occur, causing the cancel to fail hard. 6. Root cause identified. Lack of affinity. By using a random key, the system destroyed the causal relationship between events. In distributed systems, order is only guaranteed within a single stream. By splitting related events into different streams, the system became a race condition by design. Let us look at the producer code that broke the sequence of events. The evidence, randomized partition keys. Using a random UUID for the key tells Kafka to distribute these messages evenly across all partitions. While this balances load, it completely ignores the fact that a cancel cannot happen before a create.
The fix, implementation of partition affinity.
We must ensure that all events related to the same business entity are routed to the exact same partition, where Kafka guarantees sequential processing. Senior warning, moving to a specific key, like order ID, can create hot partitions if one customer is significantly more active than others. You must balance the need for order with the need for even load distribution. Here is the JavaScript implementation for enforcing event ordering via business key hashing. Disclaimer: always test code in a non-production environment. By using the order ID as the key, Kafka's internal hashing algorithm will always send every event for a specific order to the same partition. Since partitions are processed sequentially by a single consumer thread, the cancel will now mathematically always happen after the create.
Prevention and guardrails, the post-mortem.
To prevent timeline chaos in the future, we implement these guardrails. 1. State machine versioning. We add a version column to our database. We only allow an update if the incoming event underscore version is exactly current underscore version plus 1. 2. Out of order buffering, we implement a retry later queue for messages that arrive too early. If a cancel arrives for a missing order, we put it back in the queue with a 5-second delay rather than failing. 3. Sequence validation in CI. We add a contract test that intentionally reorders messages in a staging environment to ensure the application logic can self-heal from out-of-order delivery. A senior engineer never assumes that the world arrives in the order it was created. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. How does Kafka physically guarantee order within a partition, and why is it not guaranteed across the whole topic?
Answer: sequential append and single consumer. A partition is an immutable append-only log on disk. Kafka ensures messages are written in the order they arrive. Because each partition is assigned to exactly one consumer within a group at any time, that consumer reads the log from top to bottom. Across partitions, there is no shared clock or coordinator, so pod can read partition 1 faster than pod B reads partition 2.
Senior follow-up 2, the scale and trade-off trap. You move to order ID keys. Suddenly, one consumer pod hits 100% CPU while others are at 5%. How do you find the hotkey?
Answer: the skewed distribution problem. We must query the broker metrics for bytes in per partition. If partition 4 is 10 times larger than others, we have a large tenant problem. The trade-off fix is sub-partitioning, using a key like order ID plus hour bucket to spread the load while still maintaining order within small time windows.
Senior follow-up 3, the day 2 migration reality. You are using a serverless event bus like AWS Event Bridge. Can you still guarantee order?
Answer: order is harder in serverless. Event Bridge does not guarantee order by default. To solve this, you must use FIFO SQSQs as targets. SQS FIFO uses a message group ID which behaves like a Kafka partition key, ensuring that AWS Lambda processes messages for the same group sequentially.
Senior follow-up 4, Curveball. You have perfect partition affinity, yet you still see create arriving after cancel in the logs. You check the producer and find it has max dot in dot flight dot requests dot per dot connection set to 5. Why did the producer lie to you?
Answer: hidden cause, the in-flight race. If the producer sends message 1 and message 2 in parallel, and message 1 fails but message 2 succeeds, the producer will retry message 1. Now message 1 is behind message 2 on the broker. A senior engineer knows that for strict ordering, you must set enable.idempotence equals true or set max dot in dot flight dot requests dot per dot connection equals 1 to prevent the producer from getting ahead of itself.
Pro tip, the version-based state machine.
In high-scale distributed systems, stop checking for existence and start checking for versions. Every event should include a sequence number. Your database logic should be update balance set value equals new underscore value, where ID equals user underscore ID and version incoming underscore version. This optimistic locking approach makes your system naturally resilient to out-of-order events without needing complex queue tuning.
The Senior Dev Ops Incident 58, the circuit breaker failure.
It is Friday at 3 p.m. A third-party payment gateway starts experiencing 10% latency spikes. Suddenly, your own internal order service, which uses a circuit breaker, crashes completely. You expected the circuit breaker to trip and protect your system, but instead, your service continued to hammer the failing gateway until your internal thread pools were exhausted. The safety net was in place, but it was woven so loosely that your entire application fell through it. You are facing a circuit breaker threshold mismatch.
Symptoms, the panic moment.
Here is how the protected service behaved during the dependency failure. 1. Thread exhaustion. The order service shows 100% thread pool utilization and is refusing new requests. 2. Latent failures. P99 latency for the order service matches the 30-second timeout of the downstream payment gateway. 3. Circuit state, the Resilience 4J or Istio metrics show the circuit breaker remains in the closed state, despite thousands of errors. 4. Resource leak, POD memory is climbing as thousands of requests sit in the waiting state, holding onto allocated buffers. Decision tree signal, if a downstream failure causes upstream thread exhaustion while the circuit breaker stays closed, then always suspect misconfigured trip thresholds or timeout mismatches.
Hypothesis, thinking like a senior.
A junior engineer might suggest increasing the thread pool size. As a senior, I analyze the resilience logic. Hypothesis 1, incorrect error classification, ruled out. The gateway is returning 503 errors which are explicitly included in the record exceptions list. Hypothesis 2, sliding window too small, ruled out. The window is set to 100 requests and we have seen 5,000 failures. Hypothesis 3, threshold and timeout mismatch. The failure rate threshold is set too high, for example, 90%, or the minimum number of calls to evaluate the window was never reached because the threads were already dead. To verify this, we must compare the application's internal state machine with the volume of incoming traffic. Investigation, the 6-step debugging masterclass.
Step-by-step resilience forensics.
We must find why the safety switch failed to flip. We execute these steps. 1. Inspect circuit configuration. We check the application.yaml and find failure rate threshold is set to 50%. 2. Analyze traffic volume. We realize the payment gateway is only failing for 40% of requests, only those over $100. 3. Verify trip logic because 40% is less than the 50% threshold. The circuit never opens, allowing the failure to continue indefinitely. 4. Compare timeouts. We find the order service call timeout is 35 seconds, while the Tomcat thread timeout is 30 seconds. 5. Identify the deadlock. The threads die waiting for a response before the circuit breaker can even record the call as a failure. 6. Root cause identified, failure sensitivity gap. The threshold was tuned for total outages rather than partial degradation. By setting the threshold higher than the actual failure rate and having a timeout that exceeded the server's thread capacity, the circuit breaker became a passive observer of the system's destruction. Let us look at the Resilience 4J configuration that failed to trip. The evidence, the loose safety net. This is too high. If your dependency is failing for 40% of your users, your business is already in crisis. A senior engineer sets this to 10 or 15% to fail fast and protect the remaining 60% of users.
The fix, implementing fail-fast thresholds.
We must tighten the failure thresholds and ensure the circuit breaker timeout is significantly shorter than the infrastructure's thread limits. Senior warning, do not set thresholds to 1%. In a distributed system, noise network blips is normal. If your circuit is too sensitive, it will flap open and closed constantly, causing more downtime than the actual bugs. You must find the ambient error rate of your network and set the threshold just above it. Here is the YAML implementation for a hardened Resilience 4J configuration with conservative thresholds. Disclaimer, always test code in a non-production environment. By lowering the threshold to 15%, we ensure the circuit trips early. This stops the service from wasting threads on a struggling dependency and allows us to return a service unavailable or cached response immediately.
Prevention and guardrails, the post-mortem.
To ensure our resilience patterns are effective, we implement these guardrails. 1. Chaos testing. We integrate chaos mesh into our staging pipeline to simulate a 40% failure rate and verify that the circuit breaker trips within 30 seconds. 2. Adaptive timeouts. We move away from static 30-second timeouts and implement P99 plus margin timeouts based on historical service performance. 3. Bulkhead pattern. We implement the bulkhead pattern to isolate the payment gateway threads from the rest of the order service, ensuring a failure in one cannot starve the other. A senior engineer knows that a circuit breaker is not a fix. It is a fuse that protects the house from burning down. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. What is the difference between account-based and time-based sliding window in a circuit breaker?
Answer, account-based window evaluates the last-in requests, for example, 100 calls, regardless of how long they took. A time-based window evaluates all requests within the last n seconds, for example, 60 seconds. Time-based is better for low-traffic services where 100 calls might take an hour, while count-based is better for high-throughput APIs where you need an instant response to a burst of errors.
Senior follow-up to the scale and trade-off trap. You implemented fallback methods, for example, return cached data, for when the circuit is open. What is the data freshness trade-off?
Answer: the stale data versus availability trade-off. If the circuit is open for 10 minutes, your users are seeing 10-minute-old data. For a product catalog, this is fine. For account balance or stock inventory, this can lead to massive financial loss. You must categorize your services by fallability and decide where a hard error is better than a stale success.
Senior follow-up 3, the Day 2 migration reality. You are moving to Istio Service Mesh. Should you keep your application-level resilience for J circuit breakers?
Answer: ideally, no. The mesh should handle the network-level resilience, retries, timeouts, and outlier detection. This allows developers to focus on business logic and gives the platform team a single place to tune resilience across all languages: Java, Go, Python. However, app-level breakers are still needed if you require custom fallback logic that the mesh cannot provide.
Senior follow-up 4 Curveball, your circuit tripped. It is now open. You fixed the downstream gateway. Yet the circuit stays open for an hour even though the gateway is 100% healthy. Why is it not closing?
Answer: the half-open state failure. A senior engineer knows the circuit breaker needs probe traffic. If you have no users hitting the endpoint, the breaker cannot perform the trial calls needed to move from half-open back to closed. You must ensure your wait duration is reasonable and that you have synthetic probes to wake up the circuit after a fix.
Pro tip, the observability of the state.
Always alert on the state of the circuit breaker, not just the error rate. An open circuit is a Tier 1 incident event. If your circuit trips, it means your application has officially given up on a dependency. You should have a dashboard showing circuit state for every service so you can instantly see where the logical wall is during a cascading failure.
The Senior DevOps Incident 59, the Vault Raft consensus loss.
It is Monday morning. A minor network partition occurs between your availability zones. Suddenly, your global HashiCorp Vault cluster stops responding. Every application in your company starts failing because they cannot fetch secrets, database credentials, or TLS certificates. You check the Vault pods and they are all reporting error no leader found. Your secret store, the foundation of your security, has lost its ability to reach consensus. You are locked out of your own infrastructure.
Symptoms, the panic moment.
Here is the behavior of the paralyzed security layer. 1. API failure: calls to /v1/sys/health return 500 internal server error or 503 service unavailable. 2. Consensus state: Vault operator Raft list peers returns a network error or shows all nodes as follower with no leader. 3. Pod logs: Vault logs are flooded with failed to make request to peer and error heartbeat timeout. 4. Blast radius: the entire company is paralyzed. No new pods can start, and existing pods are failing as their credentials expire. Decision tree signal: if Vault is alive but reports no leader and the network recently flickered, then always suspect a Raft consensus loss.
Hypothesis, thinking like a senior.
A junior might try to delete the Vault pods to force a restart. As a senior, I analyze the quorum state. Hypothesis 1: storage corruption. Ruled out. The underlying NVMe volumes are healthy and readable. Hypothesis 2: seal key loss. Ruled out. The HSM or cloud KMS used for auto unseal is reachable and healthy. Hypothesis 3: quorum bankruptcy. A 3-node cluster suffered a 1-node failure, but during the network blip, the remaining 2 nodes could not agree on a leader. The Raft log has diverged, and the cluster is now read-only or offline because it cannot guarantee a majority quorum. To verify this, we must inspect the internal Raft peers list from a standalone node. Investigation, the 6-step debugging masterclass.
Step-by-step consensus forensics.
We must identify why the voters are not voting. We execute these steps. 1. Access Vault standalone. We SSH into a Vault pod and run Vault status to confirm it is unsealed but leaderless. 2. Identify the majority. We find that out of a 5-node cluster, 3 nodes are in US East 1A and 2 are in US East 1B. The AZ failure killed the majority. 3. Check Raft peer logs. We see term numbers increasing rapidly as nodes try and fail to elect themselves. 4. Verify network latency. We find that the inter-AZ latency has spiked to 500 milliseconds, causing Raft heartbeats to time out. 5. Identify the dead peer. We realize one node was removed from the auto-scaling group, but Vault still has it in the peer list as a voter. 6. Root cause identified, dead peer quorum drag. Vault was trying to get a vote from a node that no longer exists. During the network blip, the loss of one more node meant the cluster could no longer reach a majority of its registered peers. The ghost node in the config broke the math of the consensus. Let us look at the peer list that revealed the ghost in the consensus machine. The evidence, the quorum deadlock. This is the most dangerous state for Vault. If there is no leader, Vault cannot accept any writes or process any requests. The Raft algorithm is waiting for a majority that will never arrive because one of the voters is physically gone.
The fix, forcing a new quorum.
We must surgically remove the dead peer from the consensus log to allow the remaining nodes to form a majority. Senior warning, manually editing Raft peers is a nuclear option. If you remove the wrong node or do this while the cluster is healthy, you will cause split brain data corruption. Always take a snapshot of the underlying storage before attempting a Raft recovery. Here is the CLI implementation for forcing a Raft recovery by removing a dead peer. Disclaimer, always test code in a non-production environment. By removing the dead node, we change the cluster math. Instead of needing 2 out of 3 votes, the cluster now only needs 2 out of 2. The remaining nodes can immediately elect a leader and resume service.
Prevention and guardrails, the post-mortem.
To protect our global secret store forever, we implement these guardrails. 1. Autopilot configuration. We enable the Raft autopilot feature in Vault, which automatically removes dead or unhealthy nodes from the peer list after a specific timeout. 2. Cross-AZ distribution. We update our Terraform to ensure an odd number of nodes, for example, 5. Are distributed perfectly across 3 availability zones, ensuring we can survive the loss of an entire AZ. 3. Raft snapshot backups. We schedule an hourly Vault operator Raft snapshot to an air-gapped S3 bucket, allowing us to rebuild the cluster from 0 in case of total consensus failure. A senior engineer knows that in distributed consensus, the configuration is just as important as the data. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. How does the term and log index in Raft prevent stale data from being promoted to leader?
Answer, Raft uses a minutonic clock called a term. When a node becomes leader, it increments the term. During an election, a node will only vote for a candidate if the candidate's log is at least as up-to-date as its own. If a node was partitioned and has an older term or a shorter log, it can never be elected leader, preventing old data from overriding new data.
Senior follow-up 2, the scale and trade-off trap. You moved from 3 nodes to 7 nodes to increase AZ resilience. What is the impact on Vault write latency?
Answer, latency penalty. Raft is a strongly consistent protocol. Every write must be acknowledged by a majority, 4 out of 7 nodes. As you add more nodes, the leader has to wait for more network round trips and more disk F-syncs before it can return success to the client. You trade write performance for extreme fault tolerance.
Senior follow-up 3, the day 2 migration reality. You are migrating from console backend Vault to integrated Raft Vault. What is the primary operational benefit?
Answer, reduced dependency complexity. With console, you have 2 separate distributed systems to maintain, both of which can lose quorum. With integrated Raft, Vault manages its own storage and consensus. This reduces the surface area of failure and makes disaster recovery significantly simpler.
Senior follow-up 4, curveball. You have 5 healthy nodes and a leader. Yet one specific microservice still gets 503 no-leader errors while everyone else is fine. You check the network and it is green. What is the L7 ghost here?
Answer, hidden cause, the stale read header. A senior engineer knows that Vault clients can send an X-Vault inconsistent header. If the client hits a follower node, and that follower hasn't yet replayed the latest log from the leader, it may return a stale or error response. This often happens if your load balancer is performing round-robin across all nodes instead of pinning to the active leader.
Pro tip, the performance standby.
In high-traffic vault clusters, use performance standby nodes. These are enterprise-only nodes that can handle read requests locally without forwarding them to the leader. This allows you to scale your read-heavy secret fetching traffic horizontally across multiple availability zones without putting any extra pressure on the Raft leader node.
Category 12 wrap up, the orchestration of consensus.
Category 12 has proven that in distributed systems, the speed of your code is secondary to the reliability of your communication. We have seen that cascading failures are often a self-inflicted wound caused by tight health check coupling, and that Kafka performance is bound by the logic of your poll intervals rather than the bandwidth of your network. We learned that idempotency is not a feature, but a requirement for survival in an at least once world, and that Raft consensus is a fragile mathematical balance that can be shattered by a single ghost node in your configuration. A senior engineer knows that distributed systems are constantly trying to descend into chaos. Your job is to build the guardrails, timeouts, and state machines that force the system back into a predictable order.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
But even a perfectly consistent distributed system can be brought to its knees by the raw physics of compute and memory. We are now moving from the logic of messaging to the mechanics of high-performance execution. We are entering the domain of high-scale performance engineering.
Category 13, high-scale performance engineering.
Focus, advanced compute bottlenecks, and observability at scale. In this section, we tackle the invisible bottlenecks that metrics often hide. We will explore the CFS quota trap that throttles your CPU even when you have capacity, the cache stampedes that turn a single expiration into a database execution, and the cardinality explosions that can crash your entire monitoring stack. This is where you move beyond looking at dashboards and start looking at kernel scheduling, memory leak forensics, and the limits of your own observability tools. This is the category that separates high-performance architects from standard operators.
Category 13, incident list.
We will perform reference-grade deep dives into these 7 elite performance failures. Scenario 60, the CFS quota trap, aggressive CPU throttling occurring even at low utilization. Scenario 61, cache stampede, managing massive backend load caused by hot key expiration. Scenario 62, memory leak, distributed, diagnosing slow, multi-service gradual out-of-memory events. Scenario 63, retry storm and thundering herd, how bad backoff logic amplifies minor failures into total outages. Scenario 64, cardinality explosion, when high-label metrics crash the Prometheus monitoring stack. Scenario 65, serverless cold start stampede, managing Lambda concurrency exhaustion under sudden event floods. Scenario 66, Cube API memory leak, solving long-lived watches causing control plane during load. Let us begin with the most deceptive bottleneck in Kubernetes, the CFS quota trap.
The Senior Dev Ops Incident 60, the CFS quota CPU throttling trap.
It is Monday morning. Your Node.js API is struggling with high latency. You check the Grafana dashboard and see that CPU utilization is only at 20%. You check the node load. It is low. You check the database. It is fast. Yet your application is processing requests like it is running on a Pentium 2. You are trapped in the completely fair scheduler or CFS quota trap, where the Linux kernel is aggressively throttling your process, while your CPU sits idle.
Symptoms, the panic moment.
Here is the behavior of the throttled application during the performance crisis. 1. Utilization paradox. Prometheus shows CPU usage at 0.2 cores, while the limit is set to 1.0 core. 2. Latency spikes. P99 latency is 10 times higher than P50, with random requests taking 2 seconds instead of 50 milliseconds. 3. Metric clue. The metric container underscore CPU underscore CFS underscore throttled underscore seconds underscore total is increasing rapidly every minute. 4. Context switched. Application logs show no errors, but execution times for simple logic are unusually high. Decision tree signal. If P99 latency is high, but CPU utilization is low, and the throttling metric is non-zero, then always suspect a CFS quota period mismatch.
Hypothesis, thinking like a senior.
A junior engineer might try to increase the CPU limit to 4 cores. As a senior, I analyze the scheduling period. Hypothesis 1, noisy neighbor on the node, ruled out. Other pods on the same node are not experiencing latency. Hypothesis 2, application event loop block, ruled out. Monitoring shows the Node.js event loop lag is within normal bounds. Hypothesis 3, CFS quota micro-throttling. The application is multi-threaded or performs short bursts of work that exhaust the CPU quota at the start of the 100 millisecond CFS period, causing it to be benched for the remainder of the interval. To verify this, we must inspect the raw cgroup statistics on the host machine. Investigation, the 6-step debugging masterclass.
Step-by-step scheduler forensics.
We must prove the kernel is forcefully pausing our application. We execute these steps. 1. Query throttling metrics. We run a PromQL query for container underscore CPU underscore CFS underscore throttled underscore periods underscore total and find it is at 40%. 2. SSH into the node. We locate the pod cgroup path in /sys/fs/cgroup/cpu/cubepod/. 3. Inspect quota settings. We check cpu.cfs underscore quota underscore us and cpu.cfs underscore period underscore us. We find a 100 milliseconds period with a 100 milliseconds quota. 4. Analyze burst behavior. We use top with a high refresh rate and see the app uses 100% of a core for 10 milliseconds, then stops. 5. Identify multi-core leakage. We realize that because the app has 8 threads, it consumes 100 milliseconds of CPU time in only 12.5 milliseconds of real time. 6. Root cause identified, CFS period exhaustion. The application was bursting its entire 100 millisecond CPU quota within the first 15 milliseconds of every 100 milliseconds period. The Linux kernel then paused the process for the remaining 85 milliseconds, creating a mandatory latency floor that metrics averaged out as low utilization. Let us look at the cgroup metrics that expose the scheduler's intervention. The evidence, cgroup throttling statistics. This is the smoking gun. Out of 15,200 time slices, the kernel had to forcefully stop the application 6,100 times because it exceeded its allocated time. This causes massive latency jitter.
The fix, implementation of quota, less scheduling or period tuning.
We must align the scheduler's precision with the application's burstiness. Senior warning, do not blindly remove CPU limits across the cluster. While it solves throttling, it allows a single leaky application to consume 100% of a node, causing a cluster-wide outage. The correct senior fix is to either increase the limits to match burst potential or tune the CFS period. Here is the YAML implementation for configuring CPU limits to avoid micro-throttling. Disclaimer: always test code in a non-production environment. By increasing the limit while keeping the request low, we give the application room to burst across multiple cores for short durations without hitting the CFS ceiling. This preserves the 100 milliseconds latency window.
Prevention and guardrails, the post-mortem.
To prevent the CFS trap from returning, we implement these guardrails. 1. Throttling alerts. We set a Datadog alert on container_CPU_CFS_throttled_periods_total. If throttling exceeds 5% of total periods, the team is notified to resize the limits. 2. Runtime awareness. We update our application startup flags, like --max old space size or --max procs, to ensure the language runtime knows it is restricted to fewer cores than the host has. 3. Kernel upgrades. We upgrade to Linux kernel 5.4+, which contains several bug fixes for the CFS quota burst bug that caused unnecessary throttling. A senior engineer knows that 100% of one core is not the same as 10% of 10 cores. The senior follow-up stack.
Senior follow-up 1, mechanism deep dive. Why does a single-threaded Node.js app still get throttled when its limit is set to 1.0 CPU core?
Answer: internal worker threads. Even if your code is single-threaded, the Node.js runtime has internal threads for garbage collection, lib-of-io, and crypto. These threads can run in parallel on different host cores. If 4 internal threads run for 25 milliseconds each, they consume the full 100 milliseconds quota in only 25 milliseconds of wall clock time, causing the main event loop to be throttled for the remaining 75 milliseconds.
Senior follow-up 2, the scale and trade-off trap. You decided to remove CPU limits entirely to solve throttling. What is the CPU starvation trade-off?
Answer: noisy neighbor risk. Without limits, a pod with a while true bug can consume 100% of the host CPU. Kubernetes uses CPU shares requests to weigh priority, but during a spike, the kernel might starve critical system processes like the kubelet or the CNI, leading to node not ready status and cluster instability.
Senior follow-up 3, the day 2 migration reality. You are using the static CPU manager policy in Kubernetes. How does this eliminate the CFS trap?
Answer: core pinning. The static policy allows pods in the guaranteed QoS class to have exclusive access to specific physical CPU cores. Since the pod is pinned to a core and the CFS quota is set to the same amount, there is no shared pool and no bench time. This is the gold standard for low latency trading and database workloads.
Senior follow-up 4, curveball. You have no CPU limits set. You have no noisy neighbors. Yet your app is still being throttled at the kernel level. You check DMESG and CPU clock frequency limited. What is the hardware bottleneck here?
Answer: thermal throttling. A senior engineer knows that cloud instances are shared hardware. If the physical rack in the data center is overheating, or if the cloud provider is over-provisioning the physical CPU die, the hardware will lower its clock speed, P states. Your app is throttled not by software quota, but by the raw physics of the silicon.
Pro tip, the Go-Max Procs rule.
In Go or Java, always use a library like ubergo/automaxprocs. These libraries automatically read the cgroup CPU quota and set the runtime's thread count accordingly. This prevents the runtime from spawning 64 threads on a 64-core machine when your Kubernetes limit is only 2 cores, which is the #1 cause of excessive context switching and CFS throttling.
The Senior Dev Ops Incident 61. The cache stampede the thundering herd.
It is 12 p.m., your peak traffic hour. Your website is serving 50,000 requests per second. Suddenly, the primary database CPU jumps from 20% to 100% and stays there. The site becomes unresponsive. You check Redis, it is perfectly healthy. You check the network, it is clear. You realize that a single hotkey, the one that stores your homepage configuration, just expired. Now, 50,000 concurrent requests are all trying to rebuild that one key at the exact same millisecond. You are facing a cache stampede.
Symptoms, the panic moment.
Here is the behavior of the system during the thundering herd event. 1. Cache performance. The RIDI's hit rate drops from 99% to 80% for just 5 seconds, but the DB never recovers. 2. Database impact. SQL slow query logs show thousands of identical queries for the same config ID executing simultaneously. 3. Cascading failure. The application's database connection pool is exhausted, causing health checks to fail and pods to restart. 4. Resource paradox. Redis is idling with low memory and low CPU, while the downstream SQL server is melting. Decision tree signal. If a database crash is preceded by a minor cache hit rate dip and characterized by thousands of identical queries, then always suspect a cache stampede.
Hypothesis, thinking like a senior.
A junior might try to increase the database size. As a senior, I analyze the recomputation logic. Hypothesis 1, Redis network partition. Ruled out. The application can successfully read other keys from the same Redis node. Hypothesis 2, massive traffic spike. Ruled out. Ingress metrics show traffic is constant, only the internal load changed. Hypothesis 3, cache stampede. The application uses a get or compute pattern without locking. When the hotkey expired, every incoming request failed the get and proceeded to compute the same result, bypassing the cache safety layer. To verify this, we must look for identical, concurrent queries in the database process list. Investigation, the 6-step debugging masterclass.
Step-by-step stampede forensics.
We must prove the redundant work being forced upon the database. We execute these steps. 1. Monitor database queries. We run show process list in MySQL or pg_stat_activity in Postgres. We see 500 sessions running the exact same SQL statement. 2. Identify the key. We check the application logs for cache misses. We find that homepage_config_v2 is the common factor. 3. Check key TTL. We query Redis TTL homepage_config_v2 and see it was recently set to 3600 seconds, meaning it just expired. 4. Analyze app code. We find the pattern if not exists data equals db.query redis.set with data. 5. Trace the synchronization. We realize there is no lock or semaphore. Every pod independently decides to hit the DB. 6. Root cause identified. Lack of mutual exclusion in cache recomputation. The architecture failed to account for massive concurrency at the moment of expiration. This created a feedback loop where the DB became so slow it could not finish the first recomputation before 10,000 more requests arrived. Let us look at the process list that revealed the thundering herd of identical queries. The evidence, identical query storm. This is the proof of the stampede. Multiple workers are performing the same expensive work simultaneously. Only the first one should be allowed to query the DB, the others should wait.
The fix, implementation of distributed locking or probabilistic early recompute.
We must ensure that only one worker is allowed to rebuild the cache key at a time. Senior warning, do not fix this by setting TTL infinite. This leads to stale data that can never be updated. The correct senior fix is to implement a distributed mutex using Redis or a probabilistic early recomputation algorithm. Here is the JavaScript implementation for cache stampede protection using distributed locking. Disclaimer, always test code in a non-production environment. The NX flag ensures the lock is only set if it does not already exist. This forces the thundering herd to stop. Only one pod gets the success signal to hit the database, while the others enter a retry loop.
Prevention and guardrails, the post-mortem.
To prevent cache stampedes from recurring, we implement these guardrails. 1. Jittered TTLs. We never set the same TTL for all keys. We add a random jitter, for example, 3600 seconds plus or minus 300 seconds to ensure that even if keys are created at the same time, they expire at different times. 2. Xfetch algorithm. We implement probabilistic early expiration. The app calculates the probability of recomputing the key before it expires based on the current request rate. 3. Background recomputation. We move the computation of hot keys to a separate cron job or worker that updates Redis every 5 minutes, ensuring the user request path only ever performs a read operation. A senior engineer knows that the best way to handle a cache miss is to never have one. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. What is soft TTL or stale while revalidate, and how does it solve this without locking?
Answer: in this pattern, you store 2 timestamps in the cache, the hard expiration and a soft expiration. When the soft expiration passes, the first user to hit the key triggers an asynchronous background update but is immediately served the stale data. This ensures the user never waits and the database never sees a surge, at the cost of the user seeing slightly old data for a few seconds.
Senior follow-up to the scale and trade-off trap. You implemented the Redis NX lock. What happens if the pod that acquired the lock crashes before it can write the new data and delete the lock?
Answer: deadlock. The lock will stay in Redis until its 10-second EX expiry time passes. During those 10 seconds, all other 50,000 requests will be stuck in a retry loop, effectively causing a mini outage. This is why the lock timeout must be extremely short, just long enough for the DB query to finish.
Senior follow-up 3 the day 2 migration reality. You are using a CDN like CloudFront in front of your API. Does the CDN protect you from a cache stampede?
Answer: yes, if configured with Origin Shield or request collapsing. Modern CDNs can detect multiple requests for the same URL and collapse them into a single request to your origin. However, this only works for GET requests at the edge. Internal microservice-to-microservice calls still require application-level protection.
Senior follow-up 4 Curveball. You have perfect locks and jitter, yet your database still spikes when a key expires. You realize the key is not expired. It was evicted by Redis because it ran out of memory. How do you prevent eviction stampedes?
Answer: constraint scenario. A senior engineer monitors Redis eviction metrics. If Redis is full, it will delete keys based on the LRU policy regardless of their TTL. To prevent this, you must either scale the Redis RAM or, more importantly, use separate Redis clusters for critical config data, which should never be evicted, and transient session data.
Pro tip: the permissive TTL rule.
Never set a cache TTL to an exact round number like 60. Use 60 plus rand with 10. By staggering the expiration times of your hot keys by even a few seconds, you naturally distribute the recomputation load over time, turning a stampede into a manageable walk for your database.
The Senior Dev Ops Incident 62, the distributed memory leak.
It is Thursday morning. Your cluster health looks stable, but you notice a pattern. Every 48 hours, a random microservice crashes with an out-of-memory error. Today it was the order service. 2 days ago it was the catalog service. The services share zero business logic, but they all share the same gradual, linear memory climb. You are not facing a simple coding bug. You are facing a distributed memory leak, where a common infrastructure library is slowly poisoning every container in your fleet.
Symptoms: the panic moment.
Here is the data from the long-term observability of the leaking fleet. 1. Predictable failure. Memory usage across 10 different microservices shows an identical upward slope over a 48-hour window. 2. Restart recovery. Manual pod restarts temporarily fix the issue, but the climb begins again instantly. 3. Garbage collection stress. JVM or Node.js metrics show GC duration increasing over time as the heap fills with uncollectible objects. 4. Global correlation. The leak began exactly when the platform team mandated a new shared logging and tracing library update. Decision tree signal. If memory climbs gradually and identically across multiple unrelated services, then always suspect a shared internal library or sidecar.
Hypothesis: thinking like a senior.
A junior engineer might try to increase the memory limits for each service individually. As a senior, I analyze the shared context. Hypothesis 1: influx of large payloads. Ruled out. Traffic volume and payload sizes have remained constant. Hypothesis 2: container image bloat. Ruled out. The base image size is stable and the leak happens at runtime. Hypothesis 3: shared resource leak. A standardized internal library used for open telemetry tracing or logging is failing to close its spans or flush its buffers, causing a slow accumulation of objects in the global heap. To verify this, we must perform a heap dump analysis on a pod that is nearing its memory limit. Investigation: the 6-step debugging masterclass.
Step-by-step memory forensics.
We must identify the object king that is consuming the RAM. We execute these steps. 1. Trigger heap dump. We use JMap for Java or heap dump for Node.js to capture the memory state of a pod at 90% utilization. 2. Analyze with MAT. We open the dump in the Memory Analyzer tool. We find that 70% of the heap is occupied by millions of span objects. 3. Inspect object references. We see the spans are held by a global tracer instance that was supposed to flush every 5 seconds. 4. Audit shared library. We examine the internal platform SDK v2 code used by all microservices. 5. Identify the bug. We find an error handler that suppresses exceptions during the trace export phase. If the tracing backend is slow, the SDK stops flushing but continues accumulating spans in memory. 6. Root cause identified. Silent buffer accumulation in shared SDK. The platform team's new tracing library had a bug where failed exports led to an infinite, uncapped in-memory queue. Because every microservice imported this library, the entire cluster became a ticking time bomb. Let us look at the heap analysis results that pointed to the shared library. The evidence heap dump analysis. The heap dump reveals that over 1.2 gigabytes of memory is being held by millions of trace spans. These are not business objects. They are infrastructure metadata that failed to clear.
The fix, implementing capped buffers and circuit breakers.
We must fix the shared library to enforce hard limits on internal buffers and ensure it drops data rather than crashing the application. Senior warning: never use an uncapped queue for logging or tracing. It is better to lose a few telemetry spans than to lose the entire production service. Your infrastructure components must always fail safe by protecting the host process's resources. Here is the Java implementation for a memory-safe telemetry buffer with a hard drop policy. Disclaimer: always test code in a non-production environment. By using a fixed capacity array blocking queue, we create a physical ceiling for memory usage. The library can now only ever consume a few megabytes of RAM, regardless of how slow the backend is. The offer method returns false if the queue is full. This allows the application to discard telemetry data under pressure, which is the senior-grade way to preserve application availability.
Prevention and guardrails, the post-mortem.
To prevent distributed leaks from returning, we implement these guardrails. 1. SDK performance testing. We add a longevity test to our shared library CI pipeline that runs the SDK for 24 hours under high load to verify memory stability. 2. Anomaly detection. We implement a Prometheus alert using the predict_linear function to notify us if a pod is projected to hit its memory limit within the next 4 hours based on current trends. 3. Library versioning. We enforce a lock file policy for all microservices, ensuring that platform library updates are intentional and can be rolled back globally if a leak is detected. A senior engineer knows that the more a library is shared, the more dangerous its bugs become. The senior follow-up stack.
Senior follow-up one mechanism deep dive. What is the difference between a shallow heap and a retained heap in a memory dump?
Answer: shallow heap is the memory consumed by the object itself, for example, the pointer and primitive fields. Retained heap is the total memory that would be freed if that object was garbage collected, including all other objects it holds references to. For leaks, the retained heap is the most important metric because it shows the true cost of the leak path.
Senior follow-up to the scale and trade-off trap. You implemented a hard cap on the tracing buffer. What is the impact on your observability during a network spike?
Answer: data loss. During a spike, the buffer will fill up and new spans will be dropped. You will have gaps in your distributed traces exactly when you need them most during high load. The trade-off is total system failure versus partial data blindness. A senior engineer always chooses to keep the site alive.
Senior follow-up 3 the day 2 migration reality. You are using sidecars like Envoy or Jaeger Agent for tracing. Does this eliminate the memory leak risk in the app?
Answer: mostly yes. By moving the queuing and sending logic to a separate container, a leak in the tracing agent only crashes the sidecar, not the application. However, the application-level SDK still needs a small buffer to send data to the sidecar over localhost. It moves the complexity to the platform layer.
Senior follow-up 4 Curveball, you fix the SDK leak. Memory is stable. Yet, after 7 days, your pods are still being killed. You check the heap, it is nearly empty. Where is the memory hiding?
Answer: off-heap/native memory. A senior engineer knows that killed refers to the container limit. If your application uses native libraries like compression, cryptography, or NetI, memory can be allocated outside the language runtime's heap. You must use tools like native memory tracking in Java to find leaks in the C++ or Rust-based extensions of your application.
Pro tip, the leak suspect report.
Most heap analysis tools have a leak suspect report. Do not ignore the thread section. Often, a memory leak is actually a thread leak where thousands of threads are created but never terminated. Each thread allocates a 1 megabyte stack. 1,000 leaked threads equals 1 gigabytes of leaked RAM. Always verify your thread pools are using fixed sizes and naming conventions.
The Senior Dev Ops Incident 63, the retry storm and thundering herd.
It is Monday morning at 9 a.m. A tiny sub-second blip occurs in your core database. Under normal conditions, this would be a non-event, but today, it triggers a system-wide collapse. Your load balancer traffic jumps from 10,000 requests per second to 150,000 within 1 minute. Your microservices are healthy, but they are drowning in a sea of their own creation. You are facing a retry storm, where your own resilience logic has turned into a self-inflicted DDoS attack.
Symptoms, the panic moment.
Here is the behavior of the amplified failure during the traffic surge. 1. Traffic disparity. The API gateway shows 15 times more traffic than the actual number of active users on the site. 2. Error amplification. A 1% database error rate is amplified into a 100% front-end timeout rate. 3. Resource saturation. The network bandwidth between your web tier and app tier is at 100% capacity. 4. Log pattern. Logs are flooded with retrying request 1 of 3, retrying request 2 of 3, all happening at the exact same millisecond across 500 pods. Decision tree signal. If a minor dependency error results in an immediate, massive spike in internal request volume, then always suspect aggressive retry logic without backoff.
Hypothesis, thinking like a senior.
A junior engineer might try to scale the pods to handle the new traffic. As a senior, I analyze the retry density. Hypothesis 1, external bot attack, ruled out. Ingress WAF logs show the requests are coming from our own internal microservice IP range. Hypothesis 2, service discovery loop, ruled out. DNS resolution is stable and pointing to healthy endpoints. Hypothesis 3, retry synchronization. All 500 pods are configured with a standard retry 3 times immediately policy. When the DB flickered, all pods failed, and all pods retried at the exact same instant, creating a thundering herd that ensured the DB could never recover. To verify this, we must inspect the timestamps of the retries across the distributed logs. Investigation, the 6-step debugging masterclass.
Step-by-step traffic forensic work.
We must prove the system is DDoSing itself. We execute these steps. 1. Analyze request logs. We use an awk script to count requests per millisecond. We see spikes of 50,000 requests followed by 900 milliseconds of silence. 2. Audit client configuration. We check the common HTTP client library used by the team, for example, Axios or Feign. 3. Verify retry logic. We find a global config. Retry 3, retry delay 0. 4. Identify synchronization. We realize that because the delay is 0, the retries are synchronized with the failure. If the failure happens at T0, the retries happen at T plus 1 milliseconds. 5. Check downstream impact. We see the downstream service attempted to handle the surge, but its connection pool was instantly exhausted, leading to more failures and more retries. 6. Root cause identified. 0 delay retry storm. The system lacked exponential backoff and jitter. Instead of spreading the load out over time to give the dependency room to breathe, the system compressed a day's worth of traffic into a few seconds of synchronized retry pulses. Let us look at the trace data that exposed the synchronized pulses of traffic. The evidence, synchronized traffic pulses. The request pattern is not random. It is pulsing. This proves that all pods are reacting to the same event at the same time and retrying without any randomization. which effectively deduces the target.
The fix, implementation of exponential backoff and jitter.
We must break the synchronization of the distributed fleet by introducing randomness into our retry intervals. Senior warning, do not just add a sleep with 1,000 to your retries. If every pod sleeps for exactly 1 second, they will still remain synchronized and hit the database again at t plus 1,000 milliseconds. You must use jitter to spread the requests across a time window. Here is the JavaScript implementation for resilient retries using exponential backoff and jitter. Disclaimer, always test code in a non-production environment. This is the most important setting. By adding jitter, you ensure that pod A retries at 1.1 seconds while pod B retries at 0.9 seconds. This flattens the curve of the traffic spike and allows the database to recover.
Prevention and guardrails, the post-mortem.
To protect our infrastructure from retry storms forever, we implement these guardrails. 1. Retry budgets. We implement a global retry budget where a service is only allowed to retry if its total retry to request ratio is below 10%. This prevents a failing service from doubling the cluster load. 2. Adaptive concurrency. We use Vegas or gradient concurrency limiters. If the downstream service slows down, our client automatically reduces the number of concurrent outbound calls, protecting the target. 3. Circuit breakers. We mandate that any outbound client must be wrapped in a circuit breaker that opens after 5 failures, stopping all retries until the service is proven healthy again. A senior engineer knows that more work is not the solution to a system that is already full. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. What is the difference between full jitter and equal jitter in retry algorithms?
Answer, equal jitter keeps a portion of the exponential backoff constant and adds a small random amount. Full jitter picks a completely random number between 0 and the current exponential maximum. At high scale, full jitter is superior because it provides the maximum possible spread of requests, minimizing the probability of collisions.
Senior follow-up to the scale and trade-off trap. You implemented a 10% retry budget. What happens during a cold start where the first 10 requests all fail?
Answer, initialization failure. If your first requests fail, your ratio is 100%, which is above the 10% budget, so the service will stop retrying immediately. You must implement a minimum request floor, for example. Allow unlimited retries for the first 100 requests to allow the system to stabilize during startup.
Senior follow-up 3 the day 2 migration reality. You are using an AWS application load balancer. Can the ALB handle retries and jitter for you?
Answer, no. The ALB only performs a very basic retry on 502 or 504 errors if it has another target available. It does not support exponential backoff or jitter. This logic must be implemented in your application code or in a service mesh like Istio, which has native support for complex retry policies.
Senior follow-up 4 curveball. You have perfect jitter and backoff, yet your database is still crushed during a blip. You check the logs and see that the retries are working, but the cleanup tasks are also retrying at the same time. How do you prioritize retries?
Answer, tiered priority. A senior engineer knows that not all requests are equal. We should only retry critical user path requests like checkouts. Background tasks, analytics pings, and cleanup jobs should have a 0 retry or a sync-only policy during incidents to save resource capacity for the paying customers.
Pro tip, the wait and jitter header.
When designing an API, if you are overloaded, return an HTTP 4292 many requests with a retry after header. But here is the senior trick. Include the jitter in the header itself. Instead of telling everyone to retry in 5 seconds, tell one client retry in 4.8 and another retry in 5.2. This forces the jitter at the source, preventing the next wave from being synchronized.
The Senior Dev Ops Incident 64, the cardinality explosion.
It is Tuesday at 3 p.m. You are in the middle of a production outage. You go to your Grafana dashboard to see which microservice is failing, but the dashboard is blank. You try to query Prometheus directly, but the web UI hangs and then returns a 503 service unavailable. You check the monitoring namespace and find your Prometheus pods are in a permanent crash loop back off with an killed status. Your entire observability stack has collapsed exactly when you need it most because Someone added a single new label to a high-traffic metric.
Symptoms, the panic moment.
Here is the behavior of the blind monitoring stack during the collapse. 1. Infrastructure state: Prometheus pods are consuming 64 gigabytes of RAM and crashing every 5 minutes. 2. Query performance: any attempt to graph a simple metric results in a context deadline exceeded error. 3. Storage metrics: the wall or write-ahead log size is growing at 10 times the normal rate. 4. Developer reports: a recent release added user_ID and session_ID as labels to the HTTP_ requests_total metric. Decision tree signal: if Prometheus memory usage is parabolic and query performance is dead after a release, then always suspect a high cardinality label explosion.
Hypothesis, thinking like a senior.
A junior might try to give Prometheus more RAM. As a senior, I analyze the TSDB index structure. Hypothesis 1, scrape target timeout, ruled out. The discovery manager shows all targets are up until Prometheus crashes. Hypothesis 2, disk I/O bottleneck, ruled out. Persistent volumes show low latency and high IOPS availability. Hypothesis 3, multi-dimensional explosion. A developer added a label with unbounded values, such as a unique ID. This forced Prometheus to create a new time series for every single user, resulting in millions of unique series that saturated the in-memory index. To verify this, we must inspect the Prometheus TSDB status or use an out-of-band metrics tool. Investigation, the 6-step debugging masterclass.
Step-by-step observability forensics.
We must identify the metric that is DDoSing our index. We execute these steps. 1. Analyze pod termination. We run kubectl describe pod and confirm the pods are dying with exit code 137. 2. Bypass the UI. We use curl to hit the /API/v1/status/tsdb endpoint during the brief window Prometheus is up. 3. Identify the metric. We look at the top label names with character usage and series count by metric name sections. 4. Quantify the growth. We find that HTTP_requests_total has jumped from 5,000 series to 4 million series in 1 hour. 5. Pinpoint the label. We see that the user_ID label has 3.8 million unique values. 6. Root cause identified: cardinality mismanagement. A developer instrumented the code to track individual user performance using Prometheus labels. Prometheus is a metrics tool, not a logging tool. By adding a unique ID to a label, they created a unique time series for every user, which physically cannot fit into the Prometheus index memory map. Let us look at the TSDB status report that exposed the label explosion. The evidence: TSDB cardinality statistics. This is the smoking gun. A single label name has nearly 4 million unique values. Prometheus is designed for low cardinality data like region or method. Adding millions of user IDs makes the index too large to stay in RAM.
The fix, emergency metric relabeling.
We must immediately stop Prometheus from ingesting the toxic labels to restore the monitoring stack. Senior warning: do not just delete the metric from the app and wait for a CI/CD build. Prometheus will continue to try and scrape the existing pods. You must apply an emergency drop rule in the Prometheus configuration to stop the bleeding at the ingestion layer. Here is the YAML configuration for Prometheus metric relabeling to drop high cardinality labels. Disclaimer: always test code in a non-production environment. The label drop action removes the user_ID label during the scrape process. Prometheus will now aggregate all those millions of unique series into 5 simple series based on the remaining low cardinality labels, instantly dropping RAM usage.
Prevention and guardrails, the post-mortem.
To protect our observability stack from future explosions, we implement these guardrails. 1. Enforced metric limits. We configure sample_limit in our Prometheus scrape configs to automatically drop any target that exposes more than 10,000 series. 2. CI/CD metric linting. We add a PromTool check to our pipeline that scans new instrumentation for potential high cardinality labels. 3. Separation of concerns. We mandate that user-level tracing and high cardinality data must go to a logging or distributed tracing tool like ELK or Jaeger, never to the metrics platform. A senior engineer knows that labels are for grouping and logs are for identifying. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why does high cardinality cause an kill rather than just slow queries?
Answer: Prometheus maintains an inverted index of all label pairs in memory to provide sub-second query speeds. Each unique label value requires a set of pointers to every time series where that value appears. When cardinality explodes, the size of this index grows exponentially, exhausting the pod's RAM before it can even write the data to disk.
Senior follow-up to the scale and trade-off trap. You moved high cardinality data to logs. What is the retention trade-off?
Answer: cost and queryability. Prometheus metrics are cheap to store for months, but logs are expensive. By moving the data to ELK, you might be forced to reduce your retention from 90 days to 7 days to control costs. You trade long-term trend analysis for short-term forensic detail.
Senior follow-up 3 the day 2 migration reality. You are moving to Mimir or Victoria metrics. Do these tools solve the cardinality problem?
Answer: they handle it better, but they do not solve it. These systems use horizontal scaling and aggressive disk-backed indexing to handle hundreds of millions of series. However, they are still limited by the physics of RAM and storage. A poorly designed metric will eventually bankrupt your observability budget regardless of the tool.
Senior follow-up 4 Curveball. Your cardinality is low. Your RAM is free. Yet queries spanning 30 days still timeout. You check the logs and see too many chunks touched. What is the temporal cardinality issue here?
Answer: high churn rate. A senior engineer knows that cardinality is not just about unique values at one time, but unique values over the whole time range. If you have pods that restart 100 times a day and use the pod_name as a label, you are creating thousands of dead series that the engine must still scan during a 30-day query. You must remove ephemeral pod labels from long-term dashboards.
Pro tip: the label value ceiling.
A good rule of thumb for senior DevOps is the rule of 100. If a label is likely to have more than 100 unique values like user ID, request ID, or precise latency numbers, it does not belong in Prometheus. Convert that data into a log field or an open telemetry span attribute instead.
The Senior DevOps Incident 65. The serverless cold start stampede.
It is 9 a.m. on a Monday. Your company sends a push notification to 2 million users. Traffic hits your serverless API, and you expect AWS Lambda to scale infinitely. Instead, your API gateway starts returning 504 gateway timeouts for 40% of requests. You check the Lambda metrics. Concurrent executions are high, but the duration has jumped from 200 milliseconds to 8 seconds. Your infrastructure is struggling to wake up fast enough to handle the flood. You are facing a cold start stampede.
Symptoms: the panic moment.
Here is the behavior of the serverless tier during the burst. 1. Latency spikes. Total request duration is dominated by initialization time. 2. Error pattern. API gateway is timing out at 29 seconds while Lambda is still booting. 3. Throttling errors. Too many requests exception appears in the logs as you hit your regional concurrency limit. 4. Success rate. Only requests that hit warm containers are succeeding. All new capacity is failing. Decision tree signal. If latency is high only during a traffic surge and CloudWatch shows high init duration, then always suspect a cold start bottleneck.
Hypothesis: thinking like a senior.
A junior might try to increase the Lambda memory. As a senior, I analyze the runtime lifecycle. Hypothesis 1, database connection exhaustion, ruled out. The DB shows 0 too many connections errors. Hypothesis 2, API gateway throttling, ruled out. Gateway metrics show we are well within the 10,000 RPS limit. Hypothesis 3, cold start latency. The application is written in Java or uses heavy Node.js dependencies. Every time Lambda creates a new container to handle the burst, it takes 7 seconds to initialize the runtime before the first line of code executes. To verify this, we must perform a CloudWatch logs insights query to isolate the initialization cost. Investigation, the 6-step debugging masterclass.
Step-by-step serverless forensics.
We must prove the infrastructure boot is the cause of the user delay. We execute these steps. 1. Query CloudWatch logs. We use insights to parse the report lines of the failing Lambda functions. 2. Measure init duration, we find that for failing requests, init duration is 500 milliseconds, while duration is only 150 milliseconds. 3. Check concurrency metrics. We compare concurrent executions against provisioned concurrency. We find we have 0 provisioned capacity. 4. Verify cold start rate. We see that during the 9 a.m. burst, 80% of requests triggered a new execution environment. 5. Analyze dependency size. We inspect the deployment package and find a 150 megabytes jar file with hundreds of unused libraries. 6. Root cause identified, initialization overhead. The application was too heavy to be serverless. Because the startup time exceeded the API gateway timeout window, the user received an error while the cloud was still preparing the environment. The burst was so vertical that the system could not warm itself fast enough. Let us look at the log insights query that exposed the boot latency. The evidence, Cloud Watch init duration analysis. This is the smoking gun. If average initialization is 7.5 seconds, any burst of traffic will cause a massive queue. AWS only bills you for execution, but the user pays the price for initialization.
The fix, implementing provisioned concurrency.
We must force the cloud provider to keep a pool of warm containers ready before the traffic arrives. Senior warning, provisioned concurrency is expensive. It is effectively turning serverless into a fixed server cost. You must only apply it to the specific functions that are on the critical user path, and use scheduled scaling to turn it off during low traffic hours. Here is the HCL implementation for configuring Lambda provisioned concurrency with auto scaling. Disclaimer, always test code in a non-production environment. By setting this to 100, AWS ensures that 100 containers are always pre-initialized and ready. The 7-second cold start is eliminated for the first 100 simultaneous users.
Prevention and guardrails, the post-mortem.
To prevent cold start stampedes in the future, we implement these guardrails. 1. Runtime optimization. We migrate from Java to Go or Node.js for low latency APIs. We also implement tree shaking to reduce the deployment package size from 150 megabytes to 5 megabytes. 2. Global variable persistence. We move database connection logic outside the handler function, so that warm containers can reuse connections without reinitializing. 3. Tiered provisioning. We implement scheduled PC to scale our warm pool to 500 instances at 8:55 a.m., 5 minutes before the daily marketing push. A senior engineer knows that serverless is only 0 ops until you hit the scaling vertical. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. What is the difference between a cold start and a warm start at the micro VM level?
Answer: a warm start reuses an existing execution environment that has already downloaded the code and initialized the runtime. A cold start occurs when AWS Firecracker must provision a new micro VM. Download your code from S3, start the language runtime like JVM or Node.js, and execute your global initialization code. This boot sequence is the source of the latency.
Senior follow-up to the scale and trade-off trap. You move to provisioned concurrency. What is the impact on your burst capacity?
Answer: AWS account quota. Every account has a total concurrent executions limit, for example, 1,000. Provisioned concurrency counts against this total limit 24/7. If you provision 900 warm Lambdas for one service, you only have 100 slots left for the rest of your entire company's serverless infrastructure. You trade regional capacity for service stability.
Senior follow-up 3 the day 2 migration reality. You are using VPC-enabled Lambda. How did the recent AWS updates solve the VPC cold start problem?
Answer: AWS now uses Hyperplane ENIs. In the past, Lambda had to attach an ENI to the VPC during every cold start, which took 10 to 30 seconds. Now, AWS pre-provisions the network interfaces. The network setup is now near instant, but the application boot time remains your primary concern.
Senior follow-up 4 Curveball. You have perfect provisioned concurrency and warm containers. Yet during a burst, you still see 504 errors. You realize the Lambda is fast, but the database is failing. Why did the warm pool crash your DB?
Answer: the connection storm. A senior engineer knows that when 500 warm lambdas start processing traffic at the exact same millisecond, they all try to open database connections simultaneously. This can exceed the DB's max connections, or IOPS. You must use an RDS proxy, or a serverless-friendly connection manager, to buffer this surge.
Pro tip, the Lambda layers rule.
Keep your Lambda code separate from your dependencies using Lambda layers. By moving heavy libraries like the AWS SDK or internal shared code into a layer, AWS can cache the layer across different functions on the same physical host, reducing the disk I/O required during a cold start and making your deployments significantly faster.
The Senior Dev Ops Incident 66, the Kube API server memory leak.
It is Thursday afternoon. You notice that the Kubernetes control plane is becoming sluggish. Commands like kubectl get pods are taking 10 seconds to respond. You check the master nodes and find that the Kube API server process is consuming 28 gigabytes of RAM on a 32 gigabyte node and is swapping to disk. You restart the process, and it works fine for 2 days. Then the climb begins again. You are facing a resource leak in the API server, caused by a poorly written internal script or a third-party operator that has forgotten how to stop watching.
Symptoms, the panic moment.
Here is the behavior of the degrading control plane. 1. API latency, substantial increase in response times for all kubectl and API operations. 2. Memory trend, Kube API server RAM usage shows a perfect upward diagonal line over a 48-hour window. 3. Swap activity, the master node shows high major page faults as the kernel tries to reclaim memory. 4. Resource saturation, the etcd cluster is healthy, but the API server is struggling to serialize responses. Decision tree signal, if the API server RAM increases linearly over days and a restart temporarily fixes, it then always suspect a watch leak or stale API caches.
Hypothesis, thinking like a senior.
A junior might try to add more master nodes. As a senior, I analyze the subscription model of the API. Hypothesis 1, etcd bloat, ruled out. Etcd storage metrics show the database size is stable at 500 megabytes. Hypothesis 2, audit logging buffer, ruled out. The audit policy is set to metadata only and the buffer is limited. Hypothesis 3, orphaned watches. A client, likely a custom CI/CD script or a poorly written operator, is opening thousands of watch streams but failing to close them, forcing the API server to maintain thousands of state tracking buffers in memory. To verify this, we must inspect the API server metrics or perform a heap profile. Investigation, the 6-step debugging masterclass.
Step-by-step API forensics.
We must find the client that is bleeding our memory. We execute these steps. 1. Query API metrics. We hit the /metrics endpoint of the API server and look for APIserver_registered_watchers. 2. Identify the spike. We find the watcher count has grown from 500 to 45,000 in 2 days. 3. Trace the client. We use the APIserver_audit_event_total metric grouped by user_agent to find the top callers. 4. Identify the villain. We find a custom deployment notifier script is running every minute, opening a watch on all pods and then exiting without closing the connection. 5. Analyze heap dump. We use GoTool PPROF on the API server to confirm that watch objects and serialization buffers are consuming 80% of the RAM. 6. Root cause identified. Improper watch lifecycle management. The automation script was creating long-lived watches but treating them like short-lived list calls. Because the script process died, but the TCP connection remained in a half-open state on the API server. The server continued to allocate memory to track changes for a dead client. Let us look at the metrics that expose the watcher explosion. The evidence, API server watcher counts. This metric is the smoking gun. A healthy cluster should have a stable number of watchers matching your operators. 42,500 watchers on a single resource type indicates a massive leak.
The fix, implementation of API priority and fairness.
We must restrict the number of concurrent requests and watches a single user agent can perform to protect the control plane. Senior warning, do not just block the user agent at the load balancer. This can cause the script to retry even harder, DDoSing your network. Instead, use the native Kubernetes API Priority and Fairness APF feature to throttle the specific client within the API server itself. Here is the YAML implementation for a Kubernetes priority level configuration to throttle aggressive clients. Disclaimer: always test code in a non-production environment. We define a specific priority bucket with a very small share of the API server's total concurrency. This acts as a sandbox to contain potentially toxic automation. By setting the limit response to reject, the API server will immediately drop excessive requests from the offending service account once the small concurrency share is full, preventing the memory leak from crashing the control plane.
Prevention and guardrails, the post-mortem.
To protect our control plane permanently, we implement these guardrails. 1. Watch timeout enforcement. We set the --min request timeout flag on the API server to ensure that idle watch connections are forcefully closed by the server after a reasonable duration. 2. Operator vetting process. We mandate that any new custom operator must be profiled for memory stability in a staging cluster before it is granted access to production. 3. Master health alerting. We set a high priority alert on apaserver_registered_watchers. A 20% increase in watchers over 1 hour triggers an automatic ticket for the platform team. A senior engineer knows that the API server is a shared resource that must be defended against its own users. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why do watches consume so much more memory than list requests in the API server?
Answer: a list request is a one-time database query that is discarded after the response is sent. A watch request is a persistent TCP connection where the API server must maintain an in-memory watcher object and a serialization buffer for every event. If thousands of watches are open, the server must duplicate every pod update event into thousands of individual buffers, leading to rapid memory exhaustion.
Senior follow-up to the scale and trade-off trap. You moved from watch to polling every 30 seconds to save memory. What is the trade-off?
Answer: latency and etcd load. Polling introduces a 30-second delay in reacting to changes, which can break fast-moving CI/CD pipelines. Furthermore, 1,000 clients polling every 30 seconds creates a massive number of full-list queries, which can saturate the etcd database CPU more than a few healthy watches would.
Senior follow-up 3 the day 2 migration reality. You are running a multi-master cluster. Does the memory leak stay local to one master?
Answer: no. Most clients use a load balancer to talk to the API servers. If the script is leaking connections, it will spread those leaks across all 3 master nodes proportionally. This can lead to a simultaneous failure of all control plane nodes, resulting in a total cluster outage.
Senior follow-up 4 curveball. Your watcher count is low. Your RAM is still climbing. You realize the leak is only happening when secrets are updated. What is the secret bottleneck?
Answer: secret encryption at rest. A senior engineer knows that if you enable encryption config, the API server must perform expensive AES encryption for every write. If a controller is rapidly updating secrets and the API server's KMS cache is misconfigured, the server will leak memory trying to store the cryptographic context for every transaction.
Pro tip: the field selector rule.
Never allow your scripts to run a watch on all resources in a namespace. Always enforce the use of field selectors, for example, status.phase equals running. This reduces the number of events the API server has to process for that client, significantly lowering the CPU and RAM overhead of the watch stream.
Category 13 wrap-up. The mechanics of high performance.
Category 13 has revealed that at extreme scale, the greatest bottlenecks are often invisible to standard metrics. We have seen that the Linux kernel can throttle your CPU while it sits idle, and that a single expired cache key can trigger a thundering herd that destroys a database. We learned that the very tools we use for observability can become the cause of an outage through cardinality explosions or API memory leaks. A senior performance engineer knows that efficiency is not about doing more with more. It is about understanding the raw physics of context switching, memory pressure, and cold start latency. Mastering high-scale execution means building systems that fail safe by protecting their own resource boundaries.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
But technical performance is only one side of the coin. In the world of enterprise DevOps, every millisecond and every byte has a financial cost, and every cloud region has its breaking point. We are now moving from the performance of the pod to the economics and resilience of the entire cloud footprint.
Category 14. Cloud Economics and Regional Resilience.
Focus: managing the cost of scale and provider-level failures. In this section, we address the financial and regional traps of the cloud. We will explore the cross-availability zone traffic spikes that can bankrupt a company overnight, the cloud provider rate limits that paralyze your automation during a disaster, and the regional gray failures where a cloud service is neither up nor down. This is where you prove you understand the business of DevOps, balancing high availability against the brutal reality of cloud billing and regional constraints.
Category 14. Incident List.
We will perform reference-grade deep dives into these 6 critical resilience and economic failures. Scenario 67, cross a Z cost explosion, solving the financial fallout of inter-zone traffic chatter. Scenario 68, cloud provider rate limit, managing throttling of infrastructure as code and automation controllers. Scenario 69, partial region degradation, strategies for surviving gray failures in a cloud provider. Scenario 70, misleading health checks, when load balancers report 200 OK for functionally dead applications. Scenario 71, cross a Z latency spike, diagnosing physical network layer degradation between availability zones. Scenario 72, orphan resource accumulation, fixing lifecycle failures that cause silent billing spikes. Let us begin with the silent killer of cloud budgets, the cross-a-Z cost explosion.
The Senior DevOps Incident 67. The cross-a-Z cost explosion.
It is the first day of the month. Your CFO calls an emergency meeting because the AWS bill for inter-a-Z data transfer has jumped from $5,000 to $30,000 in 30 days. User traffic has only increased by 5%. You check the cluster. It is healthy. You check the deployments. No major changes. You are facing a cross-availability zone cost explosion, where your microservice chatter is generating thousands of dollars in hidden fees because your traffic is crossing zone boundaries unnecessarily.
Symptoms: the panic moment.
Here is the data from the Billing and Network Observability Stack. 1. Billing anomaly. Cost Explorer shows a vertical spike in data transfer regional bytes for the EKS cluster VPC. 2. Network profile. Total egress from the cluster remains the same, but internal VPC traffic volume has doubled. 3. Resource distribution. Kubernetes pods are perfectly distributed across 3 availability zones for high availability. 4. Architecture pattern. A new centralized logging sidecar was recently added to every pod in the fleet. Decision tree signal. If cloud costs spike vertically while user traffic is flat and the cluster is multi-AZ, then always suspect a lack of topology-aware routing.
Hypothesis, thinking like a senior.
A junior might try to reduce logging levels. As a senior, I analyze the network topology of the service mesh. Hypothesis 1, duplicate data transmission. Ruled out. Log volume in the storage backend matches the application output. Hypothesis 2, external egress via NAT gateway. Ruled out. Costs are strictly regional internal transfer fees, not internet egress. Hypothesis 3, cross-AZ service chatter. The new sidecars and microservices are communicating with dependencies in different availability zones. Because AWS and GCP charge per gigabyte for data crossing a zone boundary, every internal request is now being taxed twice. To verify this, we must inspect the VPC flow logs to see the source and destination zones. Investigation, the 6-step debugging masterclass.
Step-by-step topology forensics.
We must prove the network paths are inefficient. We execute these steps. 1. Query Cost Explorer. We isolate the cost to data transfer regional bytes and confirm it originates from our primary EKS-VPC. 2. Analyze VPC flow logs. We use CloudWatch Insights to find the top talkers. We see massive traffic between 10.0.1.x zone and 10.0.2.x zone B. 3. Map service endpoints. We run kubectl get endpoints for our logging aggregator. We find it has 3 pods, 1 in each AZ. 4. Observe traffic distribution. We realize the Kubernetes service uses round robin. A pod in zone A has a 66% chance of sending its logs to a server in zone B or C. 5. Calculate the tax at 100 terabytes of logs per month. A 66% cross-zone rate at 2 cents per gigabyte equals exactly $13,000 in unnecessary tax. 6. Root cause identified. Topology blind routing. The internal platform was designed for high availability, but ignored the financial cost of the network distance. The system was optimized for uptime, but defaulted to the most expensive network path for high-volume internal telemetry. Let us look at the VPC flow log query that exposed the cross-zone hemorrhage. The evidence, inter-AZ traffic volume. This query proves that terabytes of data are moving between private subnets in different zones. Since this is internal traffic, it should ideally be 0 if the data stayed in the same AZ.
The fix, implementing topology-aware hints.
We must configure the Kubernetes orchestrator to prefer same-zone routing for internal service traffic. Senior warning, do not enforce strict same-zone routing for critical business services if you only have 1 replica per zone. If that one pod fails, your service will be unreachable in that AZ even if pods are healthy elsewhere. Only apply this to high-volume, resilient services like logging, metrics, or caches. Here is the YAML implementation for enabling topology-aware routing in Kubernetes services. Disclaimer, always test code in a non-production environment. By adding this annotation, the endpoint slice controller will assign hints to the endpoints. kubeproxy will then prefer routing traffic to pods in the same availability zone as the sender, reducing cross-AZ traffic by nearly 90%, and slashing the bill instantly.
Prevention and guardrails, the post-mortem.
To prevent future cost explosions, we implement these guardrails. 1. Cost anomaly detection. We set an AWS budget alert that triggers if data transfer costs increase by more than 10% in a single day. 2. Service mesh locality. We configure Istio locality load balancing for our entire service mesh, ensuring failover only happens to other zones if the local zone is 100% dead. 3. Zonal deployment affinity. We mandate that high-volume batch workers must be co-located in the same AZ as their primary data source like a specific read replica using pod affinity rules. A senior engineer knows that in the cloud, proximity is a financial strategy. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why do cloud providers charge for traffic between availability zones, but not within the same zone?
Answer, physical infrastructure. Traffic within a zone typically stays within a single data center building or campus on a local low-latency backplane. Traffic between zones must traverse the provider's regional metropolitan fiber network. This requires more expensive optical equipment and consumes inter-building bandwidth, which the provider monetizes as a premium service.
Senior follow-up to the scale and trade-off trap. You moved all traffic to same zone routing. What is the resource imbalance risk?
Answer: skewed load. If 80% of your users hit Zone A, but your pods are distributed 33% per zone, the pods in Zone A will be crushed, while pods in Zone B and C are idle. Topology-aware routing can lead to hotspots if your ingress load balancing is not perfectly symmetrical with your internal pod distribution.
Senior follow-up 3 the Day 2 migration reality. You are using private link VPC endpoints for S3. How does the cross-a-Z cost apply to managed services?
Answer: the endpoint tax. If you have an S3 interface endpoint in Zone A, but your pods in Zone B use it, you are charged for the inter-a-Z transfer and the private link processing fee. A senior engineer ensures that interface endpoints are created in every availability zone used by the cluster to keep traffic local.
Senior follow-up 4 Curveball. You have perfect topology hints. Yet 30% of traffic is still crossing zones. You check the pods and they are healthy. Why is Kubernetes ignoring your hints?
Answer: the threshold constraint. A senior engineer knows that Kubernetes topology mode will fall back to round robin if a zone becomes overloaded, or if the number of endpoints in one zone is significantly lower than others. The default threshold is roughly 20%. If you have 2 pods in zone and 10 pods in Zone B, the scheduler will ignore your topology hints to prevent the zone of pods from being overwhelmed.
Pro tip: the VPC peering cost trap.
Always remember that VPC peering is not a free bridge. While the peering connection itself has no cost, the data transfer across it is billed at the same rate as inter-a-Z traffic. If you peer a VPC in Zone A to a VPC in Zone B, every byte you send is taxed. Always check the zonal alignment of your peered VPCs before designing high-throughput data pipelines.
The Senior Dev Ops Incident 68. The Cloud Provider API Rate Limit.
It is Thursday afternoon. You are performing a large-scale disaster recovery drill, rebuilding your entire production environment from Terraform. Suddenly, the pipeline starts failing with request limit exceeded from the AWS API. You try to log into the AWS console to check the status, but the console is sluggish. Every kubectl command and every Terraform plan is now failing. You are being throttled by your own cloud provider. Your automation is so efficient that it has been classified as a DDoS attack against the AWS control plane.
Symptoms: the panic moment.
Here is the behavior of the paralyzed automation engine during the rate-limiting event. 1. API failures. Terraform reports HTTP 429 or 400 rate limit exceeded for standard describe operations. 2. Automation stalls. CI/CD runners are failing during the init phase because they cannot fetch the state of existing resources. 3. Kubernetes impact. The AWS load balancer controller is failing to update target groups, leaving new pods without traffic. 4. Global throttling. The issue affects all users in the account, including manual administrators trying to use the CLI. Decision tree signal. If infrastructure updates fail with 429 errors across multiple tools simultaneously, then always suspect cloud provider API rate limiting.
Hypothesis: thinking like a senior.
A junior might try to wait and retry manually. As a senior, I analyze the call volume of our controllers. Hypothesis 1: malicious actor in the account. Ruled out. CloudTrail shows all API calls are coming from our verified CI/CD and controller IAM roles. Hypothesis 2: regional outage. Ruled out. AWS Service Health Dashboard is green. This is an account-specific limit. Hypothesis 3: API call amplification. Our new multi-cluster GitOps setup is running Terraform plan every minute for 50 different microservices. Each plan makes hundreds of describe calls to AWS. The cumulative frequency has exceeded the regional token bucket for the EC2 and ELB APIs. To verify this, we must use CloudTrail to quantify the API call rate per second. Investigation: the 6-step debugging masterclass.
Step-by-step API forensics.
We must identify the aggressive caller. We execute these steps. 1. Query Cloud Trail, we use Athena to group API events by event name and user identity. 2. Identify the spike, we find that describe instances is being called 500 times per second. 3. Locate the source, we trace the calls to a new custom autoscaler script written by a developer to manage GPU nodes. 4. Verify retry logic, we examine the script and find it performs a busy loop. If an API call fails, it retries immediately with 0 delay. 5. Check AWS quotas, we check the service quotas console and find our described limit is 400 per second. We are 100 calls over the limit. 6. Root cause identified, lack of client-side throttling. The custom automation script created a retry storm because it lacked exponential backoff. Once it hit the limit, it retried so fast that it ensured the account remained throttled, effectively locking out Terraform and the Kubernetes controllers. Let us look at the Cloud Trail data that revealed the API saturation. The evidence: API call frequency analysis. This is a massive volume for read operations. The cloud provider control plane has a bucket of tokens. When the bucket is empty, every new request is rejected with a 429 error.
The fix: implementation of jittered backoff and API caching.
We must immediately stop the aggressive script and refactor all automation to use exponential backoff and localized caching. Senior warning: do not just ask AWS for a limit increase. They will ask for your justification. If your code is inefficient, they will reject the increase. You must first prove that your application is using best practices like caching results for 60 seconds rather than polling the API every second. Here is the Python implementation for a resilient AWS API caller with exponential backoff. Disclaimer: always test code in a non-production environment. The adaptive retry mode in Bodo 3 is the senior choice. It automatically slows down the request rate based on the throttling responses from AWS, preventing your script from making the lockout worse.
Prevention and guardrails: the post-mortem.
To protect our cloud control plane permanently, we implement these guardrails. 1. Terraform parallelism limits. We update our CI/CD pipelines to use Terraform apply parallelism equals 10 to reduce the number of simultaneous API requests per runner. 2. Centralized provider configuration. We mandate the use of the max_retries setting in the Terraform AWS provider block for all modules. 3. API usage monitoring. We create a Datadog dashboard for call count per IAM role, with an alert that fires if any role exceeds 50% of the account's API quota. A senior engineer knows that the cloud API is a shared resource that must be treated with respect. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. What is the token bucket algorithm used by cloud providers to enforce rate limits?
Answer: a token bucket is a metaphor for a counter. The bucket has a capacity, for example, 100 tokens and a refill rate, for example, 10 tokens per second. Every API call consumes a token. If the bucket is empty, the call is rejected. This allows for bursts of traffic while enforcing a long-term average rate of consumption.
Senior follow-up to the scale and trade-off trap. You increase the described cache to 5 minutes to save API tokens. What is the infrastructure drift risk?
Answer: state inaccuracy. If a server is terminated or a load balancer is deleted, your automation will not know for 5 minutes. During a rolling update, this can cause the CI/CD pipeline to attempt to deploy to a pod that no longer exists, leading to failures. You trade API budget for system precision.
Senior follow-up 3 the day 2 migration reality. You are managing 100 separate AWS accounts. Do rate limits span across accounts?
Answer: no. API limits are strictly per region, per account. This is the primary reason senior architects use a multi-account strategy. By splitting microservices into different accounts, you give each team their own dedicated token bucket, ensuring a bug in one team's script cannot throttle the entire company's infrastructure.
Senior follow-up 4 curveball. Your API call volume is low. Your cache is perfect. Yet you are still getting rate limit exceeded errors during a Terraform run. You check Cloud Trail and see no spikes. Where are the hidden API calls coming from?
Answer: resource exhaustion scenario. A senior engineer knows that resource creation, like creating an EC2 instance, often triggers dozens of internal API calls within the cloud provider, for example, creating ENIs, attaching volumes, checking quotas. These implicit calls count against your limit. If you are creating 1,000 resources at once, even a single Terraform command can trigger an internal API storm that AWS CloudTrail does not explicitly show as a separate user event.
Pro tip, the Terraform refresh rule.
In high-scale environments, run Terraform apply -refresh equals false. By default, Terraform queries the state of every resource before doing any work. For a 1,000 resource stack, this is 1,000 API calls per run. Using refresh false skips the discovery phase and relies on your local state file, saving your API quota for the actual changes you need to make.
Senior Dev Ops Incident 69, the regional gray failure.
It is Tuesday at 11 a.m. You notice a sharp increase in connection timeouts for services running in AWS US East 1. However, the AWS Service Health dashboard is completely green. Some pods can talk to the database, while others on the same node fail. 50% of your health checks are passing, but your users are experiencing 100% failure. You are trapped in a gray failure, where a cloud service is functionally broken, but the provider's automated monitoring hasn't detected it yet.
Symptoms, the panic moment.
Here is the non-deterministic behavior of the regional degradation. 1. Partial connectivity. Services can reach S3 but cannot reach RDS within the same VPC. 2. Zonal bias. 100% of traffic in Zone A is failing, while Zones B and C are perfectly healthy. 3. Dashboard disconnect. Cloud provider status pages report operational, but your internal P99 latency is at 30 seconds. 4. Inconsistent health. Pods are marked running by the kubelet because the control plane is in a different zone than the failing network backplane. Decision tree signal. If traffic fails in a specific zone, internal metrics show errors and provider status is green, then always suspect a regional gray failure.
Hypothesis, thinking like a senior.
A junior engineer might wait for an official provider update. As a senior, I analyze the zonal blast radius. Hypothesis 1, application bug, ruled out. The exact same container image is working perfectly in other availability zones. Hypothesis 2, direct connect failure, ruled out. VPN and public internet traffic are also experiencing the same zonal timeout. Hypothesis 3, zonal network partition. A specific set of routers or switches in Zone A has failed or is dropping packets at a high rate. The cloud provider's liveness check still passes, but the throughput is dead. To verify this, we must perform a cross-zone latency and packet loss test to prove the infrastructure is degraded. Investigation, the 6-step debugging masterclass.
Step-by-step regional forensics.
We must prove the provider is broken before they admit it. We execute these steps. 1. Isolate by availability zone. We group our error rates by the zone label in our monitoring system. 2. Confirm zonal correlation. We see Zone A has a 90% error rate, while Zone B has 0%. 3. Perform traceroute. We run MTR from a pod in Zone A to the RDS endpoint. We see 50% packet loss at a specific internal cloud hop. 4. Verify load balancer state. We see the load balancer is still sending 33% of traffic to the broken zone because the health checks are passing. 5. Check internal DNS. We find that DNS resolution for internal services is timing out only when the request hits a DNS pod in Zone A. 6. Root cause identified, subthreshold zonal degradation. A hardware failure in the zone, a networking fabric is dropping packets. Because the failure is not total, the provider's health checks are still intermittently succeeding, preventing an automated failover. Let us look at the zonal error distribution that exposed the cloud provider failure. The evidence, zonal error correlation and packet loss. This is the gray part of the failure. The network is working just enough to prevent a complete link down state, but failing enough to destroy performance. Standard provider health checks often miss this threshold.
The fix, implementation of zonal evacuation.
We must take manual control and evacuate all traffic from the degraded zone immediately. Senior warning, do not wait for the provider to update their status page. A gray failure can last for hours. You must have a pre-tested mechanism to stop the load balancer from sending traffic to the affected zone, even if instances report as healthy. Here is the CLI implementation for evacuating a degraded availability zone in AWS. Disclaimer: always test code in a non-production environment. By removing the affected zone from the configuration, we force the pods to be rescheduled in healthy zones. We combine this with a routing control shift to ensure external traffic follows the capacity move.
Prevention and guardrails, the post-mortem.
To protect our business from future gray failures, we implement these guardrails. 1. Zonal outlier detection. We configure our service mesh to perform consecutive gateway error ejection. If a pod in a specific zone fails multiple times, it is removed from the pool automatically. 2. Deep health checks. We update load balancer health checks to verify end-to-end paths, such as checking if the pod can reach the database, rather than just returning a static 200 OK. 3. Regional multi-primary. We initiate a project to move toward a multi-region active-active architecture, allowing us to evacuate an entire region if it enters a gray state. A senior engineer knows that cloud provider health is a suggestion, not a guaranteed fact. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why are gray failures harder to automate than black failures?
Answer: black failures are binary. The system is either up or down. Gray failures are characterized by differential observability. The client sees a failure, but the server and the provider's health check see success. Building an automated kill switch for gray failures is dangerous because it requires a high degree of confidence to avoid a false positive that accidentally takes a zone offline.
Senior follow-up to the scale and trade-off trap. You decided to run with N+1 capacity in each zone to handle an AZ failure. What is the financial trade-off?
Answer: infrastructure overhead. To survive the loss of 1 out of 3 zones, you must always run at 150% of your required capacity. This means 50% of your cloud bill is essentially insurance for a regional failure. You must decide if the cost of downtime exceeds the cost of redundant compute.
Senior follow-up 3 the day 2 migration reality. You are moving to AWS local zones or outposts. How does the regional resilience strategy change?
Answer: increased isolation. Local zones are extensions of a parent region but have independent power and networking. However, they are often single AZ. Your application must be designed to fail back to the parent region's primary zones automatically if the local zone experiences any latency or gray failure.
Senior follow-up 4 Curveball. You have evacuated Zone A. All pods are in Zone B and C. Yet, the 504 errors continue. You find the app is still trying to talk to a database primary in Zone A. Why did your evacuation fail?
Answer: the single AZ database primary. While the application is multi-AZ, the database primary usually lives in one zone. If the network failure in Zone A affects the database, all pods in Zone B and C will still fail. You must trigger a manual or automated database failover to move the primary out of the degraded zone.
Pro tip: the CloudWatch zonal dashboard.
Never look at aggregate metrics during an outage. Build a zonal health dashboard where every graph is segmented by availability zone. This is the only way to spot a gray failure in under 5 minutes. If 2 zones are flat and 1 zone is spiking, the problem is not your code, it is the cloud infrastructure.
The Senior DevOps Incident 70, the misleading health check.
It is Monday morning. Your website is serving a blank white screen to all users. You check the load balancer, it reports 100% of targets are healthy. You check the Kubernetes pods, they are all running. The monitoring dashboard shows a 100% success rate for health checks. To the infrastructure, everything is perfect. To the user, the site is dead. You are being lied to by your own health checks.
Symptoms: the panic moment.
Here is the behavior of the functionally dead but healthy fleet. 1. Health check paradox. Load balancer health checks return 200 OK every 30 seconds for all instances. 2. Application state. The main thread of the application is responsive, but all database and cache connections are closed. 3. Error pattern. Users are receiving a 200 OK status code, but the body of the response is an empty string or a generic error message. 4. Metric blindness. Availability metrics are at 100% even though 0 business transactions are completing. Decision tree signal. If infrastructure health checks are green but user experience is failing with 200 OK responses, then always suspect a shallow health check implementation.
Hypothesis, thinking like a senior.
A junior engineer might suspect a front-end bug. As a senior, I analyze the depth of the health signal. Hypothesis 1, CDN asset failure, ruled out. Bypassing the CDN and hitting the origin directly still returns a blank page. Hypothesis 2, pod readiness probe failure, ruled out. Kubernetes reports all pods are ready and in the rotation. Hypothesis 3, shallow health check. The health endpoint is a static file or a hard-coded string. It does not verify the application's ability to talk to its database or process a real request. The app is a zombie, the heartbeat is there, but the brain is gone. To verify this, we must inspect the source code of the health check endpoint to see what it actually validates. Investigation, the 6-step debugging masterclass.
Step-by-step health logic forensics.
We must prove the health check is a lie. We execute these steps. 1. Manual health probe. We run curl against the health endpoint. It returns HTTP 200 OK in 5 milliseconds. 2. Audit health code. We find the code for the endpoint. It is a static router that returns OK without any functional logic. 3. Check database state. We check the database and find it has exceeded its maximum connections limit. The app cannot connect. 4. Trace app errors. We see the app is catching the connection refused error and returning an empty response instead of a 500. 5. Analyze probe intervals. We realize the load balancer health check is succeeding, so it never removes the pods from the pool. 6. Root cause identified, decoupled health logic. The system was designed with shallow health checks to avoid putting load on the database. However, this created a massive blind spot. Because the app returned 200 OK regardless of its internal state, the load balancer continued to send traffic to pods that were unable to process it. Let us look at the code that gave us the false sense of security. The evidence, the shallow health check and silent failure. This is the liar's endpoint. It tells the world the application is healthy when it is actually just the web server that is responsive. It ignores the functional dependencies of the service.
The fix, implementing deep and tiered health checks.
We must refactor our health checks to verify connectivity to critical dependencies while ensuring we do not overload our own backend. Senior warning, do not perform a heavy query in your health check. If 1,000 pods run a complex SQL query every 5 seconds for health checks, they will crash the database. You must use a lightweight ping or check a cached health bit. Here is the JavaScript implementation for a deep health check with circuit-aware logic. Disclaimer, always test code in a non-production environment. By running a select one, we verify the network path and the database's ability to accept new connections without putting any significant load on the database engine. If this fails, the pod is correctly marked as unhealthy.
Prevention and guardrails, the post-mortem.
Prevent misleading health checks in the future. We implement these guardrails. 1. Readiness versus liveness. We use shallow checks for liveness, just to see if the process crashed, and deep checks for readiness to see if the pod can handle traffic. 2. Business metric alerting. We set an alert for successful responses but empty bodies. If the percentage of zero-length 200 OK responses spikes, we trigger an incident. 3. Synthetic transaction probes. We implement probes that perform a full end-to-end user action every minute. This is the only true health check. A senior engineer knows that a heartbeat only proves the patient is alive, not that they are functional. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why should you never use the same endpoint for liveness and readiness probes?
Answer, destructive interference. If your database has a 10-second blip, and you use a deep check for liveness, Kubernetes will kill and restart all your pods simultaneously. This causes a massive connection storm and cold start latency when the database recovers. Readiness probes should be deep to stop traffic. Liveness probes should be shallow to prevent unnecessary restarts.
Senior follow-up to the scale and trade-off trap. You implemented deep readiness checks. During a database slowdown, all pods fail their probe. What happens to the users?
Answer, complete outage versus partial errors. By removing the pods, the load balancer returns a 503 error immediately. While this is an outage, it is often better than letting users wait 30 seconds for a timeout. The trade-off is user latency versus error visibility. Failing fast is better for the system recovery.
Senior follow-up 3. The Day 2 migration reality. You are using a headless service for your database. How does health checking work when there is no load balancer?
Answer: client-side intelligence. In a headless setup, the application pod is responsible for checking the health of the database IP it receives from DNS. If the database pod is unhealthy, it must remove itself from the DNS records by failing its own readiness probe, or the client must implement its own circuit breaker.
Senior follow-up 4. Curveball. Your health checks are deep. Yet the site is still returning 500 errors. You check the pod and it is healthy. Why is the load balancer still sending traffic to a failing pod?
Answer: detection threshold failure. A senior engineer checks the failure threshold and timeout in the load balancer configuration. If your load balancer is set to a healthy threshold of 5 and the pod is flapping, it might take 2 minutes for the load balancer to realize the pod is dead. You must tune your thresholds for faster detection.
Pro tip: the health check caching rule.
To prevent your health checks from DDoSing your database, always cache the result of your deep check for 2 to 3 seconds. When the load balancer probes the health endpoint, the application returns the cached result of the last database ping. This ensures that even with hundreds of replicas, the database only sees one ping every few seconds.
The Senior Dev Ops Incident 71. The cross a Z latency spike.
It is Thursday morning. Suddenly, your application latency triples. The order service in Zone A is taking 500 milliseconds to talk to the inventory service in Zone B. Usually, this takes 1 millisecond. You check the pod CPU, it is idle. You check the application code, no changes were deployed. You are facing a cross-availability zone latency spike, where a physical degradation in the cloud provider's inter-zone fiber network has turned your distributed system into a crawl.
Symptoms: the panic moment.
Here is the behavior of the network during the regional congestion. 1. Non-symmetric latency. Traffic from Zone A to B is slow, but traffic from B to C is fast. 2. Metric anomaly. The request_duration metrics show a massive increase in the network I/O portion while compute time remains flat. 3. Error pattern. Intermittent connection timeout and upstream request timeout errors appearing in the service mesh logs. 4. Provider silence. The cloud service health dashboard shows no events. The network is not down, it is just degraded. Decision tree signal. If latency is high only for cross-zone traffic and compute metrics are green, then always suspect and inter a Z physical network degradation.
Hypothesis: thinking like a senior.
A junior engineer might try to increase the application timeout. As a senior, I analyze the physical network path. Hypothesis 1: app thread starvation. Ruled out. Thread dumps show pods are mostly waiting on network sockets. Hypothesis 2: congested NAT gateway. Ruled out. Outbound internet traffic is fast, only internal traffic is slow. Hypothesis 3: physical fiber degradation. A fiber optic link between Zone A and Zone B in the cloud provider's backbone is experiencing high bit error rates. The link is still up, but it is retransmitting 20% of all packets. To verify this, we must perform a zonal ping mesh test to isolate the failing segment. Investigation: the 6-step debugging masterclass.
Step-by-step zonal forensics.
We must isolate the specific network segment that is failing. We execute these steps. 1. Run zonal pings. We use kubectl exec to ping between pods in different zones. We find Zone A to be as 450 milliseconds, while Zone A2 is 0.5 milliseconds. 2. Measure packet loss. We run MTR and find 15% packet loss specifically on the hop between the internal VPC routers of Zone A and Zone B. 3. Identify traffic pattern. We see the latency affects all services equally, regardless of protocol including HTTP, gRPC, or SQL. 4. Check instance types. We verify that the pods are running on Nitro instances, ruling out host-level hypervisor jitter. 5. Analyze service mesh logs. Envoy logs show UO or upstream overflow because the requests are backing up due to the network delay. 6. Root cause identified. Inter a Z link degradation. The physical connectivity provided by the cloud vendor between two specific data centers is failing. Because the link is not cut, the cloud provider's automated failover did not trigger. leaving your cross-zone calls in a state of high latency misery. Let us look at the network report that proved the zonal network failure. The evidence crosses Z latency and loss. This hop is inside the cloud provider's backbone network. The 18% loss triggers TCP retransmissions, which exponentially increases the perceived latency for the application.
The fix, implementation of locality load balancing.
You must immediately stop all cross-zone traffic and force every microservice to talk only to dependencies in its own availability zone. Senior warning: enforcing zonal locality requires that you have replicas of every service in every zone. If your order service is in zone, but your inventory service is only in zone B, your evacuation will result in a 100% outage. You must ensure zonal symmetry before you can use this fix. Here is the YAML implementation for Istio locality load balancing to enforce zonal isolation. Disclaimer: always test code in a non-production environment. By enabling locality-aware load balancing, the proxies will prioritize sending traffic to pods in the same availability zone. This immediately bypasses the degraded inter-AZ fiber link and restores latency to 1 milliseconds for the majority of requests.
Prevention and guardrails, the post-mortem.
To protect our performance from regional instability, we implement these guardrails. 1. Zonal proximity enforcement. We update our architectural standards to mandate same zone first routing for all high-volume synchronous internal calls. 2. Automatic zonal ejection. We configure the service mesh to automatically eject all endpoints in a zone if the P99 latency for that zone exceeds a 100 millisecond threshold. 3. Multi-zonal read replicas. We ensure that every microservice has a local read replica of the database in its own availability zone to minimize cross-AZ data dependency. A senior engineer knows that the best way to handle a slow network path is to never use it. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why does a 15% packet loss cause a 450 millisecond latency spike instead of just a 15% slowdown?
Answer: TCP retransmission timeouts, or RTO. When a packet is lost, the sender waits for an acknowledgement. If it does not arrive, the sender waits for the RTO period before resending. On Linux, the minimum RTO is often 200 milliseconds. If multiple packets in a window are lost, the sender enters an exponential backoff, turning a small network blip into a massive, multi-second delay for the application.
Senior follow-up to the scale and trade-off trap. You enforced zonal locality. One zone has 2 pods and another has 20 pods. What happens to your compute balance?
Answer: resource starvation. Locality routing can cause hot zones. If your traffic is not perfectly balanced by the external load balancer, the zone with fewer pods will be crushed by its local traffic. You trade network latency for compute stability. You must use distributive locality where the mesh can spill over to other zones if the local one is overloaded.
Senior follow-up 3 the day 2 migration reality. You are moving to a multi-region architecture. Does zonal locality still matter?
Answer: yes. It is the first tier of a hierarchical routing strategy. You want to stay in the same pod, then the same node, then the same zone, then the same region. Each layer has a different cost and latency profile. A senior architect designs a locality-first routing tree to minimize both latency and cloud provider egress fees.
Senior follow-up 4 curveball. You have perfect zonal locality. Yet some requests are still taking 500 milliseconds. The delay is only for HTTPS calls to an internal service. Why is TLS making the network slower?
Answer: the OCSP stapling failure. A senior engineer knows that during the TLS handshake, the client may try to verify the certificate revocation status. If the OCSP server is in the degraded zone or the request to it traverses the degraded link, the handshake will hang for 500 milliseconds before falling back. You must enable OCSP stapling on your proxies to provide the revocation proof within the handshake itself.
Pro tip: the NetChecker daemon.
Deploy a network mesh monitor like NetChecker or Goldpinger in your cluster. These tools run as a daemon set and constantly perform pings between every node in every zone. They provide a real-time latency heat map that can alert you to a regional gray failure long before your application metrics or the cloud provider dashboard ever show a problem?
The Senior Dev Ops Incident 72, the Orphan Resource Accumulation.
It is Monday morning. Your monthly cloud budget has been exceeded by 40%. You check the bill and find $50,000 in charges for unattached EBS volumes and orphaned Elastic IPs. You check your Terraform state. It says 0 resources are unmanaged. You are facing the nightmare of orphan resource accumulation, where failed automation runs and manual hotfixes have left a trail of expensive, invisible trash in your cloud account.
Symptoms, the panic moment.
Here is the behavior of the ghost infrastructure in the cloud bill. 1. Billing vertical, costs for storage and networking are rising while the number of running instances is falling. 2. Terraform drift, Terraform plan shows no changes but the cloud console shows thousands of volumes with state available. 3. Regional clutter, the account has reached its hard limit for Elastic IPs, preventing new deployments. 4. Security risk. Orphan security groups exist with 0.0.0.0/0 access, potentially providing a backdoor for attackers. Decision tree signal. If cloud bills rise without resource growth and IAC reports no drift, then always suspect orphan resources from failed lifecycle events.
Hypothesis, thinking like a senior.
A junior engineer might try to delete resources manually in the console. As a senior, I analyze the lifecycle integrity. Hypothesis 1, malicious cryptomining, ruled out. No unknown EC2 instances or Lambda executions are found in the logs. Hypothesis 2, backup policy error, ruled out. Cloud backups are configured correctly and not creating excess snapshots. Hypothesis 3, automation crash residue. The CI/CD pipeline, or the Kubernetes CSI driver, is failing to perform cleanup tasks after an error. When an apply is interrupted, the cloud provider keeps the billable resources, but the IAC tool removed them from its state. To verify this, we must perform a cross-resource inventory scan using the Cloud CLI to compare reality against our state files. Investigation, the 6-step debugging masterclass.
Step-by-step billing forensics.
We must find the trash and identify its creator. We execute these steps. 1. Query orphan volumes. We run a CLI command to find all EBS volumes with the state available, meaning they are not attached to any server. 2. Identify the volume age. We find that 500 volumes were created exactly 30 days ago, correlating with a major cluster upgrade failure. 3. Trace the tags. We look for the cluster tag on the orphan resources. We find they belong to a cluster that was deleted months ago. 4. Check Elastic IPs. We find 50 EIPs that are not associated with an instance or network interface, costing $4 per day each. 5. Verify Terraform state. We discover that the state file was corrupted during a force unlock event, causing Terraform to forget that these resources existed. 6. Root cause identified. Failure to garbage collect on automation error. When a delete command was interrupted by a network timeout, the cloud provider kept the billable resources, but the IAC tool removed them from its memory. The company was paying for a ghost cluster that no longer appeared in any dashboard. Let us look at the CLI query that exposed the orphaned cloud storage. The evidence, orphaned resource discovery. The available status is the key. In AWS, an EBS volume that is not attached to an instance is still billed at 100% cost. These are the prime targets for cost optimization.
The fix, implementation of automated cloud garbage collection.
We must move beyond manual cleanup and implement an automated janitor that deletes any resource that violates our ownership policy. Senior warning, do not run a delete all script blindly. Some orphaned resources might be part of an active passive disaster recovery strategy or a temporary database migration. You must always use a dry run and an approval phase before deleting unmanaged resources. Here is the implementation of a cloud janitor script using AWS Nuke for account-wide cleanup. Disclaimer, always test code in a non-production environment. AWS Nuke is a powerful senior-grade tool that scans your entire account and deletes everything not explicitly protected by a filter. This is the only way to ensure 100% environment parity and cost efficiency at scale.
Prevention and guardrails, the post-mortem.
To prevent resource leaks in the future, we implement these guardrails. 1. Mandatory tagging policy. We use service control policies to physically prevent anyone from creating a resource that does not have an owner and project tag. 2. Continuous janitor. We deploy Cloud Custodian as a serverless function that runs every night, automatically deleting any unattached volume that has existed for more than 24 hours. 3. Terraform post-apply check. We update our CI/CD pipeline to run a resource count check after every Terraform run, alerting us if the number of cloud resources is higher than the state file count. A senior engineer knows that in the cloud, cleanliness is next to profitability. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why does Terraform forget resources during a crashed run?
Answer: non-atomic state updates. Terraform operates in 3 steps: plan, execute, and update state. If the execute phase succeeds but the process is killed before the update state phase, Terraform has no record of the new resource. On the next run, it tries to create it again, which fails with an already exists error, or it simply ignores it, leaving it orphaned.
Senior follow-up to the scale and trade-off trap. You implemented a 24-hour auto-delete policy. What is the forensic trade-off?
Answer: evidence destruction. If a production server crashes, you might want to detach the EBS volume to perform forensic analysis. If your janitor deletes it after 24 hours, you lose the chance to find the root cause. You must exclude resources with a forensic hold tag from the auto-delete policy.
Senior follow-up 3 the day 2 migration reality. You are moving to a multi-account organization setup. How does resource management change?
Answer: centralized governance. Instead of managing janitors in 50 accounts, you use cloud intelligence dashboards and delegated administrators. This allows the platform team to see orphaned resources across the whole company from a single pane of glass, making cost optimization a global strategy.
Senior follow-up 4 curveball. Your cloud bill is perfect. Yet the finance team reports a $20,000 hidden cost in the S3 category. You check the buckets and they are empty. What is the logical orphan here?
Answer: incomplete multi-part uploads. A senior engineer knows that if an S3 upload fails halfway, the partial parts stay in the bucket and you are billed for them forever, even though the file is not visible. You must implement a lifecycle policy to abort incomplete multi-part upload after 7 days to clear these invisible ghosts.
Pro tip: the import plan applies cycle.
If your automation crashes and you suspect orphaned resources, never just apply again. Run Terraform plan and look for already exists errors. If they occur, manually Terraform import the orphaned IDs back into your state file. This reconciles reality with your code, turning trash back into managed infrastructure without needing to delete and recreate.
Category 14 wrap up. The economics of resilience.
Category 14 has redefined our understanding of the cloud, not just as a technical resource, but as a financial and regional entity. We have seen that senior engineering requires a deep awareness of the hidden taxes of the cloud, from inter-AZ data transfer fees to the silent accumulation of orphan storage. We learned that provider-level failures are rarely binary. Gray failures require manual evacuation strategies and deep health checks to survive. A senior architect knows that a system is only truly resilient when it can survive both a regional network degradation and a surprise billing audit. Mastering cloud economics means building architectures that are as optimized for the balance sheet as they are for the latency graph.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
But even a cost-optimized, multi-zonal cluster is a liability if the identities managing it are insecure. We are now moving from the physical and financial layers to the logical layer of permissions and trust. We are entering the domain of identity, security, and the software supply chain.
Category 15, Identity, Security, and Supply Chain.
Focus: Zero Trust Architecture and Identity-Based Breaches. In this section, we tackle the most sensitive failures in the DevOps stack. We will explore the complex IAM role chains that break under dependency, the OIDC token expirations that kill long-running data jobs, and the lateral movement risks inherent in weak network segmentation. We will also examine the vulnerabilities in the software supply chain, from secret rotation crashes to signature verification bottlenecks. This is where you move beyond firewalling and start building a zero-trust ecosystem where every request is explicitly verified and every identity is strictly scoped.
Category 15, Incident List.
We will perform reference-grade deep dives into these 7 high-stakes security catastrophes. Scenario 73, IAM role chain failure, solving complex permission dependency chain breakage. Scenario 74, OIDC token expiration, fixing long-running jobs that fail after the 1-hour token expiry. Scenario 75, lateral movement, hardening weak network segmentation to prevent internal breach spread. Scenario 76, secret rotation crash, dealing with applications that fail to hot reload rotated credentials. Scenario 77, over-permissioned risks, detecting and remediating data exfiltration via overscoped IAM roles. Scenario 78, undetected exfiltration, implementing observability on outbound data flow to catch silent breaches. Scenario 79, signature verify bottleneck, managing Cosign and Sigstore when they block deployments during a zero-day rush. Let us start with the hidden complexity of cloud permissions, the IAM role chain failure.
The Senior DevOps Incident 73, the IAM role chain failure.
It is Monday morning. You are deploying a cross-account data aggregator. The application in account A needs to assume a role in account B, which then assumes a final role in account C to access a sensitive S3 bucket. It worked perfectly in your staging accounts, but in production, the application crashes with a 403 access denied. You have 3 layers of IAM policies, 2 trust relationships, and 1 broken chain of identity that has paralyzed your data pipeline. You are facing an IAM role chaining failure.
Symptoms, the panic moment.
Here is the behavior of the authentication failure across the account boundaries. 1. Consistent 403, the application logs show user is not authorized to perform, assume role on the final hop. 2. Staging disparity, the staging environment uses a single account model where the chain is shorter, masking the complexity. 3. Cloud trail gaps, Cloud trail in account B shows a successful assume role, but Cloud trail in account C shows no incoming requests at all. 4. Manual testing, when you try to manually assume the roles via the CLI, it works for the first hop but fails for the second. Decision tree signal, if a cross-account request fails at the final destination but succeeds at the intermediate hop, then always suspect a transitive trust relationship failure.
Hypothesis, thinking like a senior.
A junior might try to grant administrator access to all roles. As a senior, I analyze the identity propagation constraints. Hypothesis 1, S3 bucket policy restriction, ruled out. The bucket policy explicitly allows the final role C. Hypothesis 2, Service Control Policy SCP block, ruled out. No deny statements exist in the organization for the SDS service. Hypothesis 3, Role Chaining Transit Failure. In AWS, when role A assumes role B becomes the identity. If role B then tries to assume role C, the trust relationship in role C must explicitly trust the assumed role session of role B, not just the base role B identity. To verify this, we must inspect the exact ARN being presented to account C. Investigation, the 6-step identity forensics.
Step-by-step IAM debugging.
We must trace the identity as it mutates through the chain. We execute these steps. 1. Identify the caller. We run AWS SDS get caller identity from the application after the first assumption. 2. Analyze the ARN. We see the identity is ARN:AWS:SDS, account B: assumed role/role B/session ID. 3. Inspect trust policy. We check the trust policy of role C in account C. It trusts ARN:AWS:IAM, account B: role or role B. 4. Verify transitivity. We realize that WSIAM does not automatically treat an assumed role as the same identity as the IAM role itself when chaining. 5. Check session duration. We find that role chaining has a hard limit of 1 hour, regardless of the role's maximum session duration setting. 6. Root cause identified. Principal mismatch in trust policy. Role C was looking for the static IAM role identity, but the application was presenting a dynamic SDS session identity. Because the trust relationship was too narrow, the final hop of the chain was rejected by account C. Let us look at the trust policy mismatch that broke the security chain. The evidence, the broken trust relationship. This is the assumed role principle. When you chain roles, the identity changes from a permanent IAM role to a temporary SDS session. If your trust policies do not account for this session-based ARN, the chain will break.
The fix, implementation of root principal trust.
We must update the trust relationship to trust the entire account, or use wildcards to allow the assumed role sessions to pass through. Senior warning, chaining roles is architecturally fragile and limits your session duration to exactly 60 minutes. If your data job takes 61 minutes, it will fail even if your permissions are perfect. The correct senior fix is to avoid chaining and use direct cross-account role assumption whenever possible. Here is the HCL implementation for a secure cross-account IAM trust relationship using external IDs. Disclaimer, always test code in a non-production environment. By trusting the account root, we delegate the permission check back to account B. As long as account B allows role B to assume role C, the session identity is accepted. This effectively mends the broken chain.
Prevention and guardrails, the post-mortem.
To prevent identity chain failures in the future, we implement these guardrails. 1. Direct assumption policy. We mandate that applications should assume their target role directly from their primary identity, avoiding intermediate jump roles whenever possible. 2. IAM Access Analyzer. We enable IAM Access Analyzer to find and flag any cross-account trust relationships that are too broad or use root principles without external IDs. 3. Policy Simulation in CI. We add an IAM policy simulator step to our Terraform pipeline to verify that the projected identity chain has the mathematical permissions required for the destination. A senior engineer knows that in IAM, trust must be as specific as permission. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why does role chaining limit the session duration to 1 hour, even if the role is configured for 12 hours?
Answer, this is a hard security limit enforced by AWS. When you use a temporary credential role B to assume another role C, the resulting session is capped at 3,600 seconds. This is designed to prevent long-lived credentials from propagating across account boundaries without re-authentication.
Senior follow-up to the scale and trade-off trap. You decided to trust the entire root of account B to fix the chain. What is the security trade-off?
Answer, lateral movement risk. By trusting the root, you are trusting account B to manage its own identities correctly. If an admin in account B accidentally gives a junior developer permission to assume role C, account C has no way to stop it. You trade granular control for operational simplicity.
Senior follow-up 3 The Day 2 Migration Reality. You are moving to AWS organizations with Identity Center SSO. Does role chaining still exist?
Answer: SSO uses permission sets which are provisioned as IAM roles in target accounts. When you log in, you assume that role directly. Role chaining is largely avoided in modern SSO setups because you can grant a user direct access to the final target account, eliminating the need for jump roles entirely.
Senior follow-up 4 Curveball. You have a perfect trust policy. Yet, role A still cannot assume role B. You check the trust relationship and it is correct. What policy type is silently blocking the assumption?
Answer: the permissions boundary. A senior engineer knows to check if role has a permissions boundary attached. If the boundary does not explicitly allow the STS:(assume role action, the assumption will fail even if the identity-based policy allows it. The boundary acts as a maximum allowed ceiling for permissions.
Pro tip: the external ID requirement.
Always require an external ID for cross-account trust relationships, especially when working with third-party vendors or intermediate accounts. This prevents the confused deputy problem, where an attacker who knows your role ARN could otherwise trick a shared service into assuming your role and accessing your private data.
The Senior Dev Ops Incident 74. The OIDC token expiration.
It is exactly 3:01 a.m. Your nightly data processing job, which has been running perfectly for 60 minutes, suddenly crashes with an expired token error while uploading to S3. You check the AWS credentials. They are dynamic OIDC tokens provided by Kubernetes Ursa. You restart the job and it works again. For exactly 1 hour. You are facing the OIDC token expiration trap, where the ephemeral identity of your pod has a shelf life shorter than your business logic.
Symptoms: the panic moment.
Here is the behavior of the timed identity failure. 1. Predictable crash: the job fails at the 61st minute of execution every single night. 2. Error log com.amazon.aws.services.s3.model.amazon S3 exception: the provided token has expired. 3. Pod state: the pod remains running but all subsequent AWS SDK calls fail. 4. Identity method: the cluster uses IAM roles for service accounts or Ursa via an OIDC provider. Decision tree signal: if a pod successfully authenticates with the cloud but fails after exactly 1 hour of uptime, then always suspect an OIDC token expiration.
Hypothesis: thinking like a senior.
A junior might try to use a permanent IAM user key. As a senior, I analyze the identity token lifecycle. Hypothesis 1: role session duration. Ruled out. The IAM role max session duration is set to 12 hours. Hypothesis 2: cloud provider outage. Ruled out. New pods can still assume the role and work for another hour. Hypothesis 3: Kubernetes projected volume expiry. By default, Kubernetes mounts OIDC tokens for Ursa with a hard-coded 3,600 second expiration. If the application or SDK does not hot reload the token from the disk, it continues using the expired one in memory. To verify this, we must inspect the pod's projected volume mount and the token metadata. Investigation: the 6-step identity forensics.
Step-by-step OIDC debugging.
We must find the expiry date inside the pod. We execute these steps. 1. Locate the token. We find the Ursa token at /var/run per secrets/eks.amazonaws.com/service account/token. 2. Decode the JWT. We use step crypto JWT inspect to read the token's expiration field. 3. Confirm the limit. We find the token was issued for exactly 3,600 seconds from the pod's start time. 4. Audit the SDK. We check the application's AWS SDK version. It is a legacy Java SDK version from 2018. 5. Identify the static logic. We realize the old SDK reads the token once at startup and caches the credential object forever, never checking if the file on disk has been refreshed. 6. Root cause identified. OIDC token stale caching. Kubernetes automatically refreshes the token on disk before it expires, but the legacy application code never rereads the file. When the first hour passes, the in-memory credential becomes invalid, and the 2-hour data job is left without an identity. Let us look at the JWT payload that proved the 1-hour shelf life. The evidence, the expiring OIDC token. The X field is the timestamp of death. If your application logic lasts longer than the difference between IAT and EXP, you must implement token reloading or increase the expiration seconds.
The fix, implementing token expiration overrides.
We must either upgrade the SDK to support auto-reloading or explicitly request a longer-lived token in the pod manifest. Senior warning, do not request 24-hour tokens for all pods. This violates the principle of short-lived credentials. Longer-lived tokens increase the window of opportunity for an attacker who manages to steal a token from a pod's memory. Only extend the expiration for specific batch workloads. Here is the YAML implementation for configuring Kubernetes. URSA token expiration for long-running batch jobs. Disclaimer, always test code in a non-production environment. By explicitly setting the expiration to 4 hours, we provide enough headroom for the 2-hour data job to complete even if the SDK fails to reload the token from disk. This is the safest way to support legacy applications.
Prevention and guardrails, the post-mortem.
To prevent OIDC timeouts from breaking batch jobs in the future, we implement these guardrails. 1. SDK version enforcement. We use SNIKE to identify and mandate an upgrade of all AWS SDKs to versions that natively support the Web Identity Token File Credentials Provider auto-refresh logic. 2. Credential lifetime alerts. We set a Datadog alert on the AUS_SDS_, assume _role_ with _web_identity_duration metric to find any jobs consistently hitting the 1-hour ceiling. 3. Static analysis of YAML. We use KubeScore to flag any service account or pod that relies on default token projection settings for jobs labeled as batch or cron. A senior engineer ensures that the identity of the process lasts exactly as long as the process itself. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why does Kubernetes automatically refresh the token file on disk? And how often does it do it?
Answer: Kubernetes refreshes the token file when it reaches 80% of its total lifetime, or when the token is older than 24 hours. This kubelet-managed refresh ensures that a pod running for months always has a valid token on the file system, but it relies on the application to periodically reread that file from the disk.
Senior follow-up to the scale and trade-off trap. You increase the token expiration to 12 hours for all pods to be safe. What is the security impact of a pod escape vulnerability?
Answer: increased breach window. If an attacker gains access to the pod's file system, they can steal the OIDC token. With a 12-hour expiration, that token can be used from any machine to assume the IAM role for 12 continuous hours. Short-lived 1-hour tokens minimize the replay value of stolen credentials.
Senior follow-up 3 the day to migration reality. You are moving from EKS to a self-managed Kubernetes on EC2. Does URSA still work?
Answer: not natively. URSA depends on a pod identity webhook and a service account token volume projection which are pre-configured in EKS. On self-managed clusters, you must manually install the Amazon EBS CSI driver and the OIDC webhook, or use Kube2 IAM as a legacy alternative.
Senior follow-up 4 Curveball, you have a 4-hour token. Your job takes 2 hours, yet it still fails with expired token at the 90-minute mark. You check the token on disk and it is valid. Why is the SDK using an old one?
Answer: the credential provider chain. A senior engineer knows that many SDKs check environment variables before checking the web identity file. If your CI/CD pipeline accidentally injected a static AWS_session_ token into the pod's ENV, the SDK will use that short-lived session token and completely ignore the 4-hour projected token file on disk.
Pro tip, the SDK credential refresh rule.
When writing custom code to interact with cloud APIs, never instantiate a credential object as a global static variable. Always use a credential provider that is designed to be called for every request. Modern SDKs use providers that handle in-memory caching and automatic expiry check logic, ensuring your application seamlessly picks up the refreshed OIDC tokens provided by Kubernetes.
The Senior DevOps Incident 75, the Internal Lateral Movement Breach.
It is 11 p.m. Your intrusion detection system fires an urgent alert. A compromised pod in the public website namespace is scanning internal ports on the billing DB in the finance namespace. You have a firewall at the edge of your VPC, but inside the cluster, the network is flat. An attacker who gained a foothold via a simple web vulnerability is now moving freely through your infrastructure, harvesting data from your most sensitive internal services. You are facing a lateral movement crisis caused by weak internal network segmentation.
Symptoms, the panic moment.
Here is the behavior of the internal network during the active breach. 1. Anomalous traffic, Cilium Hubble or VPC flow logs show a surge of rejected connection attempts from a front-end pod to internal database ports. 2. Security alert, Falco triggers a sensitive file opened and unexpected outbound connection alert on a public-facing container. 3. Network state, every pod in the cluster can successfully ping and telnet to every other pod across all namespaces. 4. Blast radius, the attacker has already mapped your entire internal service graph using simple network scanning tools. Decision tree signal, if an external-facing pod is attempting to communicate with internal resources, it has no business logic dependency on then always suspect active lateral movement.
Hypothesis, thinking like a senior.
A junior engineer might try to just kill the compromised pod. As a senior, I analyze the blast radius and the lack of isolation. Hypothesis 1, misconfigured security group, ruled out. Security groups protect the nodes, but they do not restrict traffic between pods on the same node. Hypothesis 2, compromised IAM role, ruled out. The attacker is moving via the network layer, not the cloud API layer. Hypothesis 3, lack of zero trust segmentation. The Kubernetes cluster has zero network policies applied. The CNI defaults to a permissive mode where all pod-to-pod communication is allowed, providing an open highway for an attacker to move from low security zones to high security zones. To verify this, we must check the default policy state of the CNI and the internal traffic logs. Investigation, the 6-step security forensics.
Step-by-step breach investigation.
We must identify how far the attacker has traveled. We execute these steps. 1. Identify the entry point. We trace the compromised pod and find a vulnerable version of a PDF processing library was used to execute a remote shell. 2. Analyze network flow. We use Cilium Hubble to visualize the traffic. We see the compromised pod attempted to reach 45 different internal IPs on port 5432. 3. Verify policy coverage. We run kubectl get netpol- and confirm that zero network policies exist in the cluster. 4. Test cross-namespace access. We spin up a test pod in the default namespace and successfully reach the finance database, proving a total lack of isolation. 5. Inspect MTLS state. We check our service mesh Istio and find it is in permissive mode, meaning it accepts unencrypted, unauthenticated traffic. 6. Root cause identified, flat network architecture. The organization relied on perimeter security but ignored internal security. By failing to implement a default deny posture, a single compromised container became a gateway to the entire company data store. Let us look at the network flow log that exposed the attacker's internal scanning. The evidence, internal lateral scanning logs. This is the nightmare scenario. A public-facing front-end pod should never be able to directly establish a TCP handshake with a back-end database. This proves the internal network has zero segmentation.
The fix, implementation of zero trust network segmentation.
We must immediately apply a default deny network policy and enforce identity-based MTLS across the cluster. Senior warning, do not apply default deny to the entire cluster at once. This will immediately break all internal communication, including DNS and monitoring. You must roll out segmentation namespace by namespace, starting with a default deny, and then explicitly whitelisting valid business flows. Here is the YAML implementation for a zero trust default deny and explicit allow network policy. Disclaimer, always test code in a non-production environment. The empty curly braces in a deny all policy select all pods in the namespace. Since no ingress rules are provided in the first block, all incoming traffic is now blocked by the CNI kernel-level filter. In the second block, we create a pinhole in the firewall. Only pods that we have explicitly labeled as the Finance API are permitted to reach the database. The attacker in the public namespace is now physically blocked.
Prevention and guardrails, the post-mortem.
To prevent lateral movement breaches in the future, we implement these guardrails. 1. Namespace as a boundary. We mandate that every namespace must include a default deny network policy as part of the initial CI/CD bootstrap process. 2. MTLS enforcement. We configure Istio to strict mode for MTLS, ensuring that even if a network connection is established, it is rejected if it does not possess a valid service-to-service cryptographic identity. 3. Runtime threat detection. We deploy Falco with automated remediation. If a pod attempts a port scan or opens a shell, the system automatically terminates the pod and isolates the node for investigation. A senior engineer knows that inside the cluster, identity is the only true perimeter. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. How does the CNI physically enforce a network policy at the Linux kernel level?
Answer: most CNIs like Calico or Cilium translate Kubernetes network policy objects into either IP tables rules or eBPF programs. When a packet enters a pod's virtual Ethernet interface, the kernel checks these rules. If no allow rule matches, the packet is dropped at the per-routing chain, ensuring the application code never even sees the unauthorized connection attempt.
Senior follow-up to the scale and trade-off trap. You implemented strict MTLS for 500 microservices. What is the impact on your internal latency?
Answer: encryption overhead. Every request now requires a TLS handshake and AES encryption/decryption at the proxy level. This typically adds 1 to 3 milliseconds of latency per hop. In a deep microservice call chain, for example, 5 hops, you are adding up to 15 milliseconds of total latency. You trade response speed for absolute security.
Senior follow-up 3 the day 2 migration reality. You are moving to a multi-cluster setup. How do you maintain network segmentation across clusters?
Answer: cluster mesh and global policies. We use a CNI that supports multi-cluster peering like Cilium Mesh. We implement cluster-wide network policies that use labels to identify workloads across different clusters. This ensures that the front-end in cluster A is still blocked from the database in cluster B using the same zero trust principles.
Senior follow-up 4 curveball. You have perfect network policies. Yet, an attacker still successfully accessed your database from a compromised pod. You check the policies and they are active. How did they bypass the CNI?
Answer: the host network escape. A senior engineer knows to check if the compromised pod was running with host network true. If a pod uses the host network, it bypasses the pod-level network namespace and the CNI's virtual filters entirely. It shares the IP of the worker node. You must use pod security admissions to explicitly ban the host network privilege.
Pro tip: the policy audit mode.
Before enforcing a new network policy in production, always use audit or log mode if your CNI supports it, like Cilium or Calico Enterprise. This allows you to see exactly which valid traffic would have been dropped by your new rules. It is the only way to move towards zero trust without causing a self-inflicted outage on day 1.
The Senior Dev Ops Incident 76. The secret rotation crash.
It is Thursday afternoon. Following security best practices, your automated system rotates the password for your primary Postgres SQL database in AWS Secrets Manager. 5 minutes later, 100% of your application pods start crashing with fatal password authentication failed. You check the secret on disk. It is updated. You check the database. The new password works. But your running application is still trying to use the old password from 10 minutes ago. You are facing a secret rotation crash, where your safe security update has just taken the entire company offline.
Symptoms: the panic moment.
Here is the behavior of the authentication failure after the security update. 1. Massive error spike. 100% of user requests are returning 500 internal server error. 2. Auth errors. Application logs show access denied or invalid password despite no code changes. 3. In container state, execing into a pod and running cat/etc per secret/db_pass shows the correct new password. 4. Readiness state. The pods are staying ready because the health check only verifies the process is running, not the database connection. Decision tree signal. If an auth failure occurs immediately after a secret rotation while the disk file is correct, then always suspect an in-memory credential caching issue.
Hypothesis, thinking like a senior.
A junior might try to manually restart all pods. As a senior, I analyze the state lifecycle of the application. Hypothesis 1, database replication lag, ruled out. The password was updated on the primary and the replica is synced. Hypothesis 2, external vault outage, ruled out. AWS Secrets Manager is responding normally and serving the new value. Hypothesis 3, static secret injection. The application was designed to read the database password once at boot time as an environment variable or a startup file read. It does not watch the secret for changes. When the rotation happened, the app became a zombie using stale credentials trapped in its memory. To verify this, we must compare the application's internal memory state with the updated file system secret. Investigation. The 6-step secret forensics.
Step-by-step rotation debugging.
We must prove the application is ignoring the new reality. We execute these steps. 1. Verify rotation success. We confirm AWS Secrets Manager updated successfully at 14 p.m. 2. Check secret mirroring. We confirm the external secrets operator updated the Kubernetes secret at 14:01 p.m. 3. Inspect volume mount. We check the pod and find the kubelet successfully refreshed the secret file on the mount path at 14:02 p.m. 4. Trace app startup. We look at the code and find the DB connection pool is initialized in a global static block. 5. Confirm stale memory. We restart one pod manually. It connects successfully. This proves the issue is purely the lack of an auto-reload mechanism. 6. Root cause identified, static credential binding. The application lacked hot reload capabilities. Because the deployment manifest was not modified by the secret rotation, Kubernetes saw no reason to restart the pods, leaving the entire fleet running with invalid credentials in their RAM. Let us look at the code pattern that caused the application to ignore the new password. The evidence, static configuration binding. This is the architectural flaw. By reading the secret during the initialization phase and storing it in a constant, the application has no way to react to the security lifecycle of the infrastructure.
The fix, implementation of automated rolling restarts.
We must bridge the gap between the secret rotation and the deployment state by forcing a rolling update whenever a secret changes. Senior warning, do not try to write custom file watcher code inside your application to reload passwords. It is complex, error-prone, and requires reinitializing connection pools which can leak memory. The correct senior fix is to use a Kubernetes controller that handles the pod lifecycle for you. Here is the YAML implementation for automating pod restarts using the reloader controller. Disclaimer, always test code in a non-production environment. By adding this annotation, the reloader controller watches the secrets and config maps mounted to this deployment. When the password is rotated, Reloader detects the change and triggers a standard Kubernetes rolling update. The pods restart, read the new secret, and stay healthy.
Prevention and guardrails, the post-mortem.
To ensure secret rotations never cause an outage again, we implement these guardrails. 1. Multi-user rotation. We move from a single password to a dual-user rotation strategy. The new password is created on a separate user, and the app is updated. This ensures both old and new credentials work during the transition. 2. Configuration checksums. We update our CI/CD Helm charts to inject a checksum of the secret as a pod annotation. This ensures that any Terraform apply that changes a secret will naturally trigger a pod update. 3. Readiness probe depth. We update our readiness probes to attempt to select one against the database. If auth fails, the pod is removed from traffic, providing a clear signal of the failure. A senior engineer knows that security is a life cycle, not a one-time event. The senior follow-up stack.
Senior follow-up one mechanism deep dive. Why does Kubernetes not automatically restart pods when a secret or config map is updated?
Answer, predictability and control. Kubernetes follows a declarative desired state model. A secret update only changes the data stored in etcd. Since the deployment manifest has not changed, the controller assumes the user does not want to disrupt the running pods. Automatically restarting pods on every minor config change would make it impossible to perform zero downtime rolling updates manually.
Senior follow-up to the scale and trade-off trap. You decided to use dual user rotation Postgres role A and role B. What is the operational trade-off?
Answer: credential proliferation. Instead of managing 1,000 secrets, you are now managing 2,000. You must ensure that your cleanup scripts eventually delete the old user once the new user is verified. The trade-off is zero downtime security at the cost of higher identity complexity.
Senior follow-up 3 the day 2 migration reality. You are moving to HashiCorp Vault with dynamic secrets. Does the reload problem go away?
Answer: no, it shifts. Vault issues short-lived credentials that must be renewed. If your application or the Vault agent sidecar fails to renew the lease, the credential dies. You still need a mechanism like a sidecar exit signal or a reloader to ensure the app picks up the new dynamic lease before the old one expires.
Senior follow-up 4 Curveball. Your reloader is working. The pods are restarting. Yet the DB still rejects connections for 60 seconds during the rollout. You check the DB logs and see too many connections. Why did your security update crash the DB?
Answer: the rollout connection surge. A senior engineer knows that during a rolling update, the old pods are still running while the new ones boot. If you have 500 pods, you briefly have 1,000 pods during the rollout. Each pod opens a connection pool. This double count of connections can exceed the DB limit. You must use a DB proxy like PG Bouncer or Reduce Max Surge to prevent the security rotation from becoming a self-DDoS.
Pro tip, the config checksum trick.
If you cannot use the reloader controller, use this Helm trick. Add an annotation checksum or config. Include print$.template.basepath per secret.yaml. Pipe SHA-256 sum to your pod spec. This forces the deployment SHA to change whenever the secret content changes, ensuring Kubernetes performs a native rolling update every time your security team rotates a key.
The Senior DevOps Incident 77. The over-permissioned IAM exploit.
It is 2 a.m. A security auditor flags an anomaly. A small image resize microservice is currently downloading terabytes of raw customer data from a restricted FinData S3 bucket. You check the code. The service has no reason to touch that bucket. You realize a developer used a shared IAM role across 10 different services to save time. A single compromised container has now become a skeleton key for your entire data lake. You are facing a data exfiltration event caused by overscoped IAM roles.
Symptoms, the panic moment.
Here is the behavior of the identity-based breach. 1. Anomalous egress. S3 server access logs show GET object requests coming from an unexpected VPC endpoint. 2. IAM identity. The caller is identified as common service role which is attached to 50 different pods. 3. Metric spike. CloudWatch shows bytes downloaded from the sensitive bucket has jumped from 10 megabytes to 5 terabytes in 1 hour. 4. Unauthorized path. The resizing service, which should only access the public assets bucket, is successfully listing objects in the private ledger bucket. Decision tree signal. If a service is accessing data outside its functional domain and uses a generic role name, then always suspect an over-permissioned IAM risk.
Hypothesis, thinking like a senior.
A junior might try to delete the S3 bucket. As a senior, I analyze the identity granularity. Hypothesis 1, compromised access key, ruled out. The requests are coming from an internal pod using an IAM instance profile, not a static key. Hypothesis 2, public bucket policy, ruled out. The bucket is set to block all public access. Hypothesis 3, identity-based overscoping. The common service role uses wildcards like S3:* on resource:*. While convenient for development, it violates the principle of least privilege, allowing any pod using that role to traverse the entire S3 hierarchy. To verify this, we must use the IAM policy simulator to see the effective permissions of the pod. Investigation, the 6-step identity forensics.
Step-by-step IAM debugging.
We must prove the role is a security liability. We execute these steps. 1. Identify the instance profile. We run AWS SDS get caller identity inside the resizing pod. 2. Export the policy. We pull the JSON of the common service role and find the allow statement for S3. 3. Audit resource wildcards. We find the resource is set to ARN:AWS:(S3), which includes every bucket in the account. 4. Simulate access. We use the IAM policy simulator to test if this role can access the secret fin data bucket. The result is allowed. 5. Trace role usage. We use IAM Access Advisor and find that out of 5,000 S3 permissions, the resizing service has only used 2 in the last 90 days. 6. Root cause identified, failure of role separation. The organization prioritized developer velocity over security isolation. By creating one role for many services, they bypassed the security boundary that Kubernetes namespaces were supposed to provide. Let us look at the toxic IAM policy that allowed the data exfiltration. The evidence, the overscoped IAM policy. Using a wildcard for actions is dangerous. This service only needed to read images, but it was granted permission to delete buckets, change policies, and download encrypted ledgers.
The fix, implementation of IRESA with fine-grained scoping.
We must migrate the service to its own dedicated IAM role for service accounts, or IRESA, and restrict access to the specific bucket and prefix it requires. Senior warning: do not just change the existing role. If you remove the wildcard from a shared role, you will break the other 9 services that rely on it. You must create a new, scoped role and perform a rolling migration. Here is the HCL implementation for a zero-trust IAM policy, restricted by bucket and prefix. Disclaimer: always test code in a non-production environment. By explicitly naming the allowed actions, we ensure the service cannot be used to delete data or modify the infrastructure. This is the definition of least privilege.
Prevention and guardrails, the post-mortem.
To prevent overscoped roles from recurring, we implement these guardrails. 1. IAM Access Analyzer. We configure a weekly report that flags any IAM role with resource : or administrative wildcards for immediate remediation. 2. Service Control Policies. We implement an AWS SCP that forbids the attachment of the Administrator Access Managed policy to any role used by a Kubernetes pod. 3. Automatic Role Generation. We use an internal developer platform tool to automatically generate a unique, scoped IAM role for every new microservice during the bootstrap phase. A senior engineer knows that a shared role is a shared risk. The Senior Follow-up Stack.
Senior follow-up 1 mechanism deep dive. What is the difference between an IAM policy and an S3 bucket policy, and which one wins?
Answer: IAM policies are attached to users or roles who can do what? Bucket policies are attached to the resource who can access ME. For a request to succeed, both must allow the action. However, if either one has an explicit deny, it will override any allow from the other, making deny the most powerful tool in your security arsenal.
Senior follow-up to the scale and trade-off trap. You moved from 1 shared role to 500 unique service-specific roles. What is the operational trade-off?
Answer: management complexity. Managing 500 roles via the AWS console is impossible. You trade identity security for infrastructure code volume. You must implement a standardized Terraform module or a controller like ACK or Crossplane to manage these identities as code, or you will face massive configuration drift.
Senior follow-up 3 the day to migration reality. You are using AWS EKS. How do you ensure a pod and namespace cannot assume the IAM role meant for namespace B?
Answer: trust policy conditions. In the IAM roles trust relationship, you must use a condition block that checks the subfield of the OIDC token. You restrict the role to only be assumed by a specific service account name in a specific Kubernetes namespace. This prevents role hijacking by malicious pods in the same cluster.
Senior follow-up 4 Curveball. Your IAM policies are perfect. Yet, a pod still managed to download data from a bucket it was not allowed to access. You check the pod and it has no IAM role. How did it get the data?
Answer: hidden cause, the MD's metadata service. A senior engineer knows that if IRESA fails, an SDK may fall back to the node's IAM role via the instance metadata service. If your Kubernetes worker node has a broad node role with S3 access, every pod on that node can inherit those permissions. You must block access to 169.254.169.254 from the pods using a network policy.
Pro tip, the IAM Policy Sentry.
Use a tool like Policy Sentry to generate your IAM policies. Instead of writing JSON by hand, you provide a list of actions and resources, and the tool generates a least privilege policy for you. It prevents the common lazy wildcard habit that leads to multi-million-dollar data breaches.
The Senior Dev Ops Incident 78, the undetected data exfiltration.
It is Monday morning. The finance department flags a $15,000 spike in internet egress costs for the last weekend. You check your ingress logs, traffic was normal. You check your application dashboards, there were 0 errors. You check the cluster, everything looks perfect. Yet, terabytes of data have left your network to an unknown IP address in another country. You are facing a silent exfiltration event because your network observability stops at the pod and ignores the exit path.
Symptoms, the panic moment.
Here is the behavior of the silent network breach. 1. Billing Vertical AWS Cost Explorer shows a massive spike in data transfer out bytes. 2. Log blindness. Application logs show no unusual activity. No failed logins, no massive database queries. 3. Network state. The VPC has an internet gateway with a wide open default route for outbound traffic. 4. Missing signal. There are no alerts for high outbound throughput because the monitoring team only focused on inbound latency. Decision tree signal. If cloud costs spike for egress traffic while ingress is flat and app logs are clean, then always suspect undetected outbound exfiltration.
Hypothesis, thinking like a senior.
A junior might try to block all outbound traffic. As a senior, I analyze the network perimeter visibility. Hypothesis 1, authorized backup to another region, ruled out. The S3 logs show no cross-region replication activity. Hypothesis 2, compromised VPN, ruled out. VPN logs show only authorized employee logins. Hypothesis 3, egress blindness. A container was compromised via a supply chain, attack a malicious dependency. It is now streaming the contents of the local database or environment variables to a command and control server. Because we lack egress filtering and flow observability, the attacker is using the open highway of our NAT gateway to steal data. To verify this, we must enable and analyze VPC flow logs to identify the destination IP. Investigation, the 6-step network forensics.
Step-by-step exfiltration analysis.
We must find the leak in the network pipe. We execute these steps. 1. Enable flow logs. We realize VPC flow logs were disabled to save cost. We enable them immediately on the NAT gateway subnets. 2. Isolate high-volume flows. We use Athena to find the source private IP responsible for the 5 terabytes egress spike. 3. Map IP to pod. We use the kubectl get pods -o wide history to find which pod held that IP during the weekend. 4. Identify the process. We use inspect process to see active network connections on the suspicious pod. We find a curl process streaming data to a non-AWS IP. 5. Analyze the destination. We run a whois on the target IP and find it belongs to a known malicious botnet hosting provider. 6. Root cause identified. Lack of egress control. The network was designed with an implicit trust model for outbound traffic. Because any pod could talk to any public IP without restriction, the attacker was able to tunnel data out using standard HTTPS port 443, making it invisible to standard firewall rules. Let us look at the VPC flow log query that finally caught the thief. The evidence, outbound flow analysis. This is the smoking gun. While the traffic to S3 is normal, the 5 terabytes of data going to an unverified external IP is the literal definition of exfiltration. The network layer allowed this because it had no deny rule for unknown destinations.
The fix, implementation of egress filtering, and FQDN whitelisting.
We must move to a default deny posture for outbound traffic and only allow connections to verified domains. Senior warning, do not just block all IPs. Modern applications rely on hundreds of dynamic cloud IPs. If you block by IP, Your app will break every time AWS updates their CIDR ranges. The correct senior fix is to use an L7 egress gateway that filters by domain name FQDN rather than just IP address. Here is the YAML implementation for Cilium-based egress domain filtering. Disclaimer: always test code in a non-production environment. This is the senior level security fix. By using fully qualified domain names, the CNI will only allow the pod to resolve and connect to trusted partners. Any attempt to reach an unknown IP like 185.x.x.x will be dropped at the kernel level.
Prevention and guardrails, the post-mortem.
To prevent undetected exfiltration in the future, we implement these guardrails. 1. Egress throughput alerting. We set a Datadog alert on aws.natgateway.bytes_out. If outbound traffic deviates from the 7-day average by more than 50%, it triggers an immediate investigation. 2. Deep packet inspection. We deploy AWS Network Firewall to perform signature-based inspection of outbound traffic. Looking for common command and control C2 communication patterns. 3. Zero Trust Egress. We mandate that every new microservice must submit an egress manifest listing all external dependencies before it can be promoted to production. A senior engineer knows that the exit door is just as important as the entrance. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why is egress filtering at the IP layer 3 ineffective for modern cloud applications?
Answer: ephemeral IPs. Cloud services like S3, Stripe, and Twilio use thousands of different IP addresses that change without notice. If you hardcode an allow list of IPs, your application will experience frequent random outages as the cloud provider rotates their infrastructure. L7 domain-based filtering is the only way to maintain both security and availability.
Senior follow-up to the scale and trade-off trap. You implemented FQDN filtering using a proxy like Squid or Cilium. What is the DNS poisoning risk?
Answer: validation bypass. If an attacker can compromise the internal DNS server core DNS, they can point api.stripe.com to their own malicious IP. Your egress filter will see the allowed domain name and permit the traffic. You must combine FQDN filtering with TLS server name indication SNI verification to ensure the destination identity matches the name.
Senior follow-up 3 the day 2 migration reality. How do you handle egress for legacy, non-HTTP traffic that does not have a domain name?
Answer: static CIDR blocks or private link. For legacy database traffic, we use AWS Private Link to ensure the traffic never even touches the public internet. For everything else, we use the smallest possible static CIDR range and implement aggressive logging and alerting on that specific CIDR volume.
Senior follow-up 4 curveball. You have perfect egress filters. Yet, an attacker still exfiltrated 100 gigabytes of data. You check the logs and see the traffic went to your company S3 bucket.s3.amazonaws.com. How did they use your own infrastructure against you?
Answer: the S3 data tunnel scenario. A senior engineer knows that if you allow .amazonaws.com, an attacker can simply upload your data to their S3 bucket using your network. To fix this, you must implement VPC endpoint policies that only allow outbound traffic to S3 buckets owned by your organization's ID.
Pro tip, the honeypot IP.
Add a dummy database IP address to your internal DNS that points to a non-existent service. Create an alert that triggers if any pod in your cluster ever attempts to connect to that IP. Since no legitimate service should ever use it, any connection attempt is a 100% guaranteed signal of an internal breach or a lateral scanning attempt.
The Senior Dev Ops Incident 79, the signature verification bottleneck.
It is 4 p.m. on a Friday. A critical zero-day vulnerability is announced in a core library. Your developers push a patch in 20 minutes, but when you try to deploy, 100% of your Kubernetes clusters are rejecting the new image. The error says, image signature could not be verified. You check the signing server, it is under heavy load. Your security safety net has just become a stranglehold, preventing you from fixing the very vulnerability it was designed to protect you from.
Symptoms, the panic moment.
Here is the behavior of the block delivery pipeline during the zero-day rush. 1. Deployment stalls. Every kubectl apply or Helm install returns a 403 forbidden error from the admission controller. 2. Error message denied by cosign.sigstore.dev, no valid signatures found. 3. Pipeline failure, the CI job succeeded in signing the image, but the public key required for verification is unreachable from the cluster. 4. Global impact. Every team in the company is trying to push patches simultaneously, DDoSing the Internal Certificate Authority or Key Management Service. Decision tree signal. If deployments fail with signature errors during a high-velocity event, while the registry is healthy, then always suspect a verification bottleneck.
Hypothesis, thinking like a senior.
A junior might try to uninstall the security admission controller. As a senior, I analyze the supply chain dependencies. Hypothesis 1, image tag mismatch, ruled out. The digest in the manifest matches the signed digest in the registry. Hypothesis 2, registry outage, ruled out. Docker pull works perfectly, only the Kubernetes admission step fails. Hypothesis 3, verification latency and key access. The admission controller Kyverno or policy controller is timing out while trying to fetch the cosign public key, or the OIDC Fulcio root of trust, from a remote server that is currently saturated by the global patch storm. To verify this, we must inspect the logs of the admission webhook and check the external connectivity to the Sigstore services. Investigation, the 6-step supply chain forensics.
Step-by-step bottleneck discovery.
We must find why the security gate is stuck. We execute these steps. 1. Check webhook logs. We see context deadline exceeded errors in the Kyverno/cosign pods. 2. Audit external calls. We realize the cluster is configured to use the public Sigstore transparency log record. 3. Verify network latency. We find that outbound calls to record.sigstore.dev are taking 10 seconds because the entire world is hitting it to verify 0-day patches. 4. Identify the timeout. The Kubernetes API server has a 30-second webhook timeout, but the combination of signature fetch and record verification is exceeding this limit. 5. Analyze key management. We find the public key is stored in a vault instance that is currently being rate limited by the cluster's own management traffic. 6. Root cause identified. External dependency on a critical path. The cluster security posture was designed to rely on a public API for runtime verification. During a global security crisis, this external API became a single point of failure. The cluster could not verify its own safety because the verification server was overwhelmed by the rest of the planet. Let us look at the admission controller log that exposed the verification timeout. The evidence, verification timeout logs. This proves the API server waited for the verification, but the external security service took too long to respond. The system failed closed, stopping the critical patch from deploying.
The fix, implementation of local cache and break glass policies.
We must move the source of trust inside our network and provide an emergency bypass for critical patches. Senior warning, do not leave your break glass policy active forever. It is an emergency tool that bypasses security checks. You must automate its expiration or pair it with an intense manual audit of any image deployed while the check was disabled. Here is the YAML implementation for a time-limited break glass admission policy. Disclaimer, always test code in a non-production environment. By requiring a specific, time-bounded annotation, we allow the SRE team to push the critical patch without disabling security for the whole cluster. We trade assurance for availability during a crisis.
Prevention and guardrails, the post-mortem.
To prevent supply chain bottlenecks in the future, we implement these guardrails. 1. Local record/Fulcio instance. We deploy our own internal Sigstore stack record and Fulcio within our VPC, eliminating the dependency on the public internet for verification. 2. Key bundling. We update our admission controller to use a local public key stored as a Kubernetes secret rather than fetching it from a remote KMS during every pod creation. 3. Failure policy tuning. We change the admission webhook to failure policy. Ignore for a subset of trusted system namespaces like kubesystem to ensure the cluster can always recover itself. A senior engineer knows that a security check you cannot perform is a denial of service. The senior follow-up stack.
Senior Follow-up 1 Mechanism Deep Dive. What is a transparency log like Recor, and why does Cosine use it?
Answer: a transparency log is an immutable, append-only ledger that records when an image was signed. It provides non-repudiation. Even if an attacker steals your private key today, they cannot backdate a signature in the Recor log. This allows you to verify that an image was signed before the key was compromised.
Senior Follow-up to the Scale and Trade-off Trap. You move to an internal SigStore stack. What is the maintenance trade-off?
Answer: operational burden. You are now responsible for the availability and backup of the transparency log database. If you lose your internal record data, you lose the ability to verify every image in your company. You trade external reliability for internal responsibility.
Senior Follow-up 3 The Day 2 Migration Reality. You are moving to keyless signing. How does the identity of the signer change?
Answer: from static keys to OIDC. With keyless signing, there is no private key file. Instead, Cosine uses a temporary certificate issued by Fulcio based on your GitHub or GitLab OIDC identity. The verification now checks if the image was signed by sictrunner@company.com rather than checking a math-based public key.
Senior Follow-up 4 Curveball. Your verification is fast and local. Yet the pod still fails with image pull backoff. You check the logs and see digest mismatch. Why did your signed image break the pull?
Answer: the tag rewrite scenario. A senior engineer knows that signing is tied to the digest the hash, not the tag. If your registry or a cleanup script overwrote the v1.4 tag with a newer image after it was signed, the signature is now invalid for that tag. You must always pull by at SHA-256 digest to ensure the signature and the content match 100%.
Pro tip: the policy audit first rule.
When implementing image signing, never start with a block policy. Start with a warn or audit policy for 30 days. This allows you to identify all the legacy or third-party images in your cluster that are unsigned. If you block first, you will break your cluster's ability to run critical infrastructure components like the CNI or the CSI drivers.
Category 15 Wrap Up. The Sovereignty of Identity.
Category 15 has forced us to confront the reality that in a cloud-native world, identity is the only true perimeter. We have seen how complex IAM role chains can create fragile dependencies that paralyze cross-account data flows, and how the short-lived nature of OIDC tokens requires applications to be context-aware to survive long-running jobs. We learned that a flat network is an invitation for lateral movement, and that the simple act of rotating a secret can take down an entire fleet if your deployment lifecycle is not synchronized with your security lifecycle. A senior DevOps engineer knows that security is not a barrier to be bypassed, but a fundamental property of the architecture. Mastering identity and the supply chain means building systems where trust is never assumed, but always cryptographically proven and strictly scoped.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The Elite Transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
But our journey does not end with a single secure cluster. In the enterprise, we manage fleets across regions and clouds, and we must intentionally break our systems to prove they can survive the unthinkable. We are now moving to the final frontier, multi-cluster federation and chaos engineering.
Category 16, Multi-Cluster Federation and Chaos.
Focus, managing fleet-wide operations and resilience testing. This is the Staff Plus level of infrastructure management. In this final section, we look at the failures that occur when you scale beyond a single control plane. We will explore the XDS propagation lags that cause cross-cluster blackholing, the uncoordinated MTLS rotations that trigger global authentication storms, and the chaos experiments that go wrong and threaten the control plane itself. This is where you prove you can manage not just a cluster, but a global ecosystem of distributed machines, and that you have the courage to test your assumptions through intentional failure.
Category 16, Incident List.
We conclude our masterclass with these 4 elite-level scenarios. Scenario 80, XDS cache desync, solving Istio configuration propagation lag that causes regional blackholing. Scenario 81, MTLS rotation storm, recovering from uncoordinated certificate updates across multiple federated clusters. Scenario 82, OTel trace propagation failure, fixing distributed tracing gaps caused by sampler configuration errors. Scenario 83, chaos test catastrophe, managing the fallout when a fault injection experiment breaks the cluster control plane. Let us begin with the most complex failure in the service mesh world, the XDS cache desync.
The Senior Dev Ops Incident 80, the XDS cache desync black hole.
It is Monday morning. You are running a global service mesh spanning 2 Kubernetes clusters in different regions. You deploy a standard update to the inventory service. Suddenly, all traffic from the order service in US East 1 to the inventory service in EU West 1 starts returning 503 service unavailable. You check the pods, they are healthy. You check the routing rules, they are correct. Your service mesh control plane has correctly calculated the state, but your edge proxies are stuck in a logical time warp. You are facing an XDS cache desync.
Symptoms, the panic moment.
Here is the behavior of the black-holed traffic across the federated mesh. 1. Selective failure. Intra-cluster traffic is 100% successful, but cross-cluster traffic is 100% failing. 2. Error pattern. Envoy proxies return 503 UC upstream connection failure or NR no route found. 3. Control plane state. Istio cuddle proxy status shows all proxies as synced with the pilot control plane. 4. Configuration delay. The failover rule was applied 10 minutes ago, but the proxies are still trying to send traffic to decommissioned IP addresses. Decision tree signal. If Istio cuddle says everything is synced but traffic is black holing to old endpoints, then always suspect an XDS propagation lag or cache inconsistency.
Hypothesis, thinking like a senior.
A junior engineer might try to restart the entire Istio control plane. As a senior, I analyze the state propagation chain. Hypothesis 1, MTLS handshake failure, ruled out. Sidecars can successfully establish secure tunnels for other services. Hypothesis 2, cross-cluster DNS failure, ruled out. Core DNS correctly resolves the remote service to its gateway IP. Hypothesis 3, XDS cache stale state. The pilot control plane has updated its internal state, but the incremental XDS push failed to update the specific envoy cache for cross-cluster endpoints, leaving the proxy with a zombie routing table that points to non-existent pods. To verify this, we must perform a low-level dump of the envoy proxy's internal clusters and endpoints. Investigation, the 6-step mesh forensics.
Step-by-step XDS debugging.
We must prove the discrepancy between the control plane and the data plane. We execute these steps. 1. Query pilot state. We use Istio cuddle proxy config endpoint to see what the control plane thinks it sent to the pod. 2. Dump envoy state, we use curl localhost colon 15,000 / clusters inside the failing pod to see what envoy actually knows. 3. Compare IP addresses. We find the control plane has the new pod IPs, but the envoy cache is still holding the IPs from 20 minutes ago. 4. Identify push errors. We check Istiad logs for XDS push timeout or NAC negative acknowledgement from specific proxies. 5. Check resource saturation. We find the Istiad pod is struggling with high CPU, causing it to drop incremental updates for a subset of the fleet. 6. Root cause identified, incremental XDS update loss. Due to control plane CPU throttling, Istiad failed to deliver the Endpoint Discovery Service EDS update to the federated gateway. Because it was an incremental push, the gateway never received the new state and continued black-holing traffic to the old, deleted endpoints. Let us look at the Envoy cluster dump that exposed the stale endpoint cache. The evidence, Envoy stale endpoint cache. This is the smoking gun. The proxy is holding a zombie IP in its cache. Because Istio reported a successful sync, our standard monitors remained green while the traffic was being sent into a black hole.
The fix, implementation of proxy cache refresh, and control plane scaling.
We must force a full-state synchronization and ensure the control plane has sufficient resources to process the XDS stream. Senior warning, do not just restart the pods. This will cause a thundering herd of XDS requests that can crash your already struggling Istiad pods. You must scale the control plane first, then perform a staggered refresh of the proxy state. Here is the CLI implementation for forcing an Istio XDS cache refresh and scaling the control plane. Disclaimer: always test code in a non-production environment. This command tells Istiad to ignore its incremental delta tracking and push the absolute current state of the world to all connected proxies. This overwrites the stale cache entries and restores connectivity instantly.
Prevention and guardrails, the post-mortem.
To prevent XDS desyncs in the future, we implement these guardrails. 1. Control plane HPA. We configure horizontal pod auto-scaling for Istiad based on buffer usage and CPU to ensure it can always handle peak XDS push volume. 2. Endpoint consistency monitoring. We deploy a mesh audit script that periodically compares a sample of Envoy caches against the Istio registry, alerting on any delta older than 30 seconds. 3. Circuit breaking for discovery. We implement outlier detection on our cross-cluster gateways, ensuring that if a gateway returns 503S due to stale cache, the source pods automatically failover to a healthy regional endpoint. A senior engineer knows that in a distributed control plane, synced is a status, but consistent is a reality. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. What is incremental XDS, and why is it more efficient but higher risk than full XDS?
Answer: incremental XDS delta XDS only sends the changes. For example, delete IPA, add IPB rather than the entire multi-megabyte routing table. This drastically reduces the CPU and network load on Istiad. However, if a single incremental update is lost or improperly acknowledged NAC-KED due to a race condition, the proxy state becomes desynced until a full push occurs.
Senior follow-up to the scale and trade-off trap. You decided to disable incremental XDS to gain stability. What is the impact on a cluster with 5,000 pods?
Answer: control plane meltdown. With 5,000 pods, a single change to one service would trigger the transmission of a massive configuration file to every single pod in the cluster simultaneously. Your network bandwidth and Istiad CPU would be saturated, leading to update latency of minutes rather than seconds. You trade state consistency for system scalability.
Senior follow-up 3 the day 2 migration reality. You are moving to ambient mesh sidecarless. Does the XDS desync problem still exist?
Answer: yes, but the target changes. Instead of sidecars, the XDS updates are pushed to the Z-tunnel on every node and the waypoint proxies. The desync now happens at the node level, potentially affecting all pods on a single host rather than just one application pod.
Senior follow-up 4 Curveball, your proxies are 100% synced. The IPs are correct. Yet cross-cluster traffic still returns 503. You check the destination gateway and it is healthy. What is the MTU ghost here?
Answer: hidden cause, the packet fragmentation trap. A senior engineer knows that MTLS adds encryption headers which increase the packet size. If your cross-region network has an MTU of 1,500, but your MTLS packets reach 1520 bytes, they will be dropped by regional routers. You must either enable Path MTU discovery or reduce your service mesh TCP MSS to account for the encryption overhead.
Pro tip, the istio_ctl describe command.
When debugging mesh routing, stop using kubectl get. Use istio_ctl describe pod name. This provides a human-readable summary of every istio policy, destination rule, and virtual service affecting that pod. It identifies conflicts and shadowed rules that are invisible to standard Kubernetes tools, saving you hours of manual YAML cross-referencing.
The Senior Dev Ops Incident 81, the MTLS rotation storm.
It is 10 p.m. on a Friday. Your automated certificate manager, Cert Manager, initiates a routine rotation of the MTLS root CA for your global service mesh. Within minutes, every cross-service connection in your multi-cluster environment fails with TLS certificate unknown. Your microservices are healthy and your certificates are new, but the trust has been broken. You are facing a MTLS rotation storm, where a failure to coordinate the old and new roots of trust has turned your security layer into a global kill switch.
Symptoms, the panic moment.
Here is the behavior of the shattered trust during the rotation. 1. Global auth failure. 100% of internal gRPC and HTTP calls return 503 service unavailable. 2. Error log pattern. Envoy logs show UC upstream connection and SSL_C_cert_chain_ failure. 3. Control plane state. All pods report that they have synced the latest secrets from Kubernetes. 4. Cluster asymmetry. Cluster A pods cannot talk to cluster B pods, even though both have been updated with new certificates. Decision tree signal. If a routine security update results in mass TLS handshake failures, then always suspect an uncoordinated root CA transition.
Hypothesis, thinking like a senior.
A junior might try to delete the certificates to restart the process. As a senior, I analyze the trust bundle lifecycle. Hypothesis 1, expired certificate, ruled out. The new certificates have a 1-year validity window. Hypothesis 2, key mismatch, ruled out. The private keys and public keys match perfectly in each pod. Hypothesis 3, missing root transition. The system performed an atomic swap of the root CA. Pod A is now using root new, but pod B is still using root old. Because root new does not trust root old, the handshake fails. You have created a trust island where different parts of the fleet are speaking different security languages. To verify this, we must inspect the trust bundle inside the sidecar memory. Investigation, the 6-step identity forensics.
Step-by-step MTLS debugging.
We must find where the trust chain is broken. We execute these steps. 1. Inspect pod secrets. We run OpenSSLX509-/etc/cert/root-cert.pem-text inside a pod in cluster A and cluster B. 2. Identify the split. We find that cluster A has issuer, root v2, and cluster B has issuer, root v1. 3. Verify trust bundle. We look at the CA_ bundle in the Envoy configuration. We find it only contains a single certificate, root v2. 4. Simulate handshake. We use OpenSSLS_client between pods. The client v2 rejects the server v1 because it does not recognize the v1 signature. 5. Audit rotation logic. We realize the automation script performed a delete and create instead of an append and roll. 6. Root cause identified. Failure to implement the double root transition. In a multi-cluster MTLS environment, you must have a period where all pods trust both the old and new root CAs simultaneously. By performing an atomic swap, the system entered a state of mutual hostility where no pod could verify its peers during the rollout window. Let us look at the OpenSSL results that prove the trust mismatch. The evidence, mismatched roots of trust. This is the definitive proof. Cluster A received a certificate signed by v1, but its internal trust store only contained v2. It physically could not verify the identity of its own sibling cluster.
The fix, implementation of the trust bundle merge.
We must immediately manually merge the old and new root certificates into a single trust bundle and distribute it to all clusters to restore connectivity. Senior warning: do not delete the old root CA until 100% of the pods in all clusters have been restarted and issued new certificates signed by the new root. If you remove the old root too early, you will re-trigger the outage for any pod that hasn't yet rolled its identity. Here is the Bash implementation for merging and distributing a multi-cluster trust bundle. Disclaimer: always test code in a non-production environment. By concatenating both certs into the root cert.pem file, every pod will now trust identities signed by either the old or the new CA. This provides the bridge required for a safe transition.
Prevention and guardrails, the post-mortem.
To prevent MTLS rotation storms in the future, we implement these guardrails. 1. Double root rotation policy. We mandate a 48-hour overlapping period for all CA rotations, where the trust bundle must contain both the expiring and the new root certificates. 2. Cross-cluster connectivity probes. We implement a mesh pinger that specifically monitors cross-cluster MTLS handshakes and alerts us if the success rate drops below 100%. 3. Automated bundle verification. We add a CI step that uses OpenSSL Verify to confirm that a test certificate signed by the new CA is successfully validated against the current production bundle. A senior engineer knows that in cryptography, trust must be built before the identity is changed. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. Why does MTLS require a trust bundle CA chain rather than just the leaf certificates?
Answer: decoupled verification. In MTLS, POD A does not have POD B certificate stored locally. Instead, POD A uses the public key of the root CA to verify the signature on POD B certificate. The trust bundle provides the source of truth that allows any pod in the cluster to verify any other pod's identity without a central registry lookup.
Senior follow-up to the scale and trade-off trap. You decided to use a single global root CA for all 10 clusters. What is the blast radius trade-off?
Answer: total compromise risk. If your single root CA private key is stolen, every service in your entire company is vulnerable to impersonation. You trade operational simplicity 1 rotation for security concentration. A more senior approach is to use an intermediate CA per cluster, all chained back to an offline root CA.
Senior follow-up 3 the day 2 migration reality. You are moving from Istio managed CA Citadel to AWS private CA. How do you handle the transition?
Answer: trust domain migration. We must add the AWS private CA root to the Istio Casert's secret as a trusted peer. We run in permissive MTLS mode for the duration of the migration, allowing services to talk via either Citadel or AWS-issued certificates until the transition is verified.
Senior follow-up 4 Curveball, your trust bundle is perfect. Both roots are there. Yet one specific Go-based microservice still fails TLS. You check the logs in CX509, too many intermediates. What is the chain depth limit here?
Answer: hidden cause, the verification max depth. A senior engineer knows that some language runtimes like Go or older OpenSSL versions have a default maximum certificate chain depth, usually 2 or 3. If your new CA architecture adds an extra layer of intermediates, you must manually increase the max underscore depth in your application's TLS configuration.
Pro tip, the istio-cutl check upgrade command.
Before rotating anything, run istio-cutl times check upgrade. This command performs a holistic scan of your multi-cluster state and warns you if your control plane or sidecars are using deprecated trust settings that could break during a rotation. It is the best pre-flight check for service mesh maintenance.
The Senior Dev Ops Incident 82, the distributed trace propagation failure.
It is Wednesday afternoon. You are investigating a high latency issue in a complex distributed request that crosses 15 different microservices. You find the trace ID in the logs of the entry point service, but when you search your tracing platform, only 3 of the 15 spans are visible. The trace just stops halfway through the call chain. You check the instrumentation, it is perfect. You check the network, it is healthy. You are facing an open telemetry trace propagation failure, where mismatched sampler configurations have turned your distributed visibility into a collection of disconnected fragments.
Symptoms, the panic moment.
Here is the behavior of the fragmented observability during the investigation. 1. Incomplete waterfalls. The tracing UI shows a route span but no child spans for downstream services. 2. Log trace mismatch. Logs in service B show the correct trace ID, but those logs are not linked to any span in the UI. 3. High sample rate. The entry point service is configured to sample 100% of traffic for debugging. 4. Downstream silence. Downstream services show zero traces being exported, even though they are processing thousands of requests. Decision tree signal. If trace IDs exist in logs across services but spans are missing from the UI, then always suspect a context propagation or sampling decision mismatch.
Hypothesis, thinking like a senior.
A junior might assume the tracing agent is down. As a senior, I analyze the context lifecycle. Hypothesis 1, mismatched headers, ruled out. All services are using the W3C trace context standard. Hypothesis 2, collector backpressure, ruled out. The OTel collector metrics show zero drop spans due to queue fullness. Hypothesis 3, parent-based sampling conflict. The upstream service made a sample true decision, but the downstream service is using a ratio-based sampler that independently decided to drop the span, ignoring the parent's instruction. To verify this, we must inspect the trace flags in the raw HTTP headers between services. Investigation, the 6-step observability forensics.
Step-by-step propagation debugging.
We must prove the downstream service is dropping a valid context. We execute these steps. 1. Capture traffic headers. We use TCP dump on the network between service A and service B. 2. Analyze the trace parent header. We find the header value ends in -01, confirming the upstream service has set the sampled flag. 3. Inspect downstream config. We check the OpenTelemetry SDK configuration for service B. We find it uses the trace ID ratio-based sampler set to 0.1. 4. Verify sampler type. We realize service B is not using a parent-based decorator, meaning it ignores the sample true flag from the caller. 5. Check SDK logs. We enable OTel internal logging and cspan dropped by sampler messages for the specific trace ID. 6. Root cause identified, fragmented sampling logic. The entry point was configured for deep debugging, but the downstream microservices were configured to save costs by independently sampling only 10% of traffic. Because they did not respect the parent's decision, 90% of the debug traces were decapitated at the first hop. Let us look at the SDK configuration that caused the trace fragmentation. The evidence, mismatched sampling configuration. This is the error. In a distributed system, a downstream service should almost never make an independent sampling decision. It must respect the decision made by the entry point service to ensure the trace remains contiguous.
The fix, implementing parent-based sampling.
We must wrap all downstream samplers in a parent-based decorator to ensure they respect the upstream decision. Senior warning, enforcing 100% propagation can lead to an observability DDoS. If your entry point service has a bug and samples everything, your downstream collectors and storage will be crushed. You must implement rate limiting at the OTel collector layer as a final safety valve. Here is the JavaScript implementation for a parent-based sampler that ensures distributed trace integrity. Disclaimer: always test code in a non-production environment. This is the senior grade fix. The parent-based sampler acts as a logic gate. It checks the incoming trace parent header first. If the header says the request is already being traced, it forces the current service to record its spans, regardless of the local ratio.
Prevention and guardrails, the post-mortem.
To protect our distributed visibility forever, we implement these guardrails. 1. Global sampler policy. We mandate the use of parent-based samplers in our shared internal libraries, preventing developers from overriding the propagation logic. 2. Span-to-log correlation. We enforce the inclusion of trace_ID and span_ID in every structured log message. We alert if logs contain a trace_ID that does not exist in the tracing backend. 3. Collector-side sampling. We move the data reduction logic away from the microservices and move it to the OTel collector using tail-based sampling, allowing us to make complex keep decisions based on errors or latency. A senior engineer knows that observability is a team sport. If one service stops passing the ball, the whole game is lost. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. What is the W3C trace context standard, and why did it replace the older B3 headers?
Answer: W3C trace context provides a standardized HTTP header format traceparent and trace state that is supported by all major cloud providers and observability vendors. Unlike the Zipkin B3 format, W3C is an official web standard, ensuring that traces can propagate seamlessly through third-party proxies, CDN, and multi-vendor environments without being stripped or corrupted.
Senior follow-up to the scale and trade-off trap. You move to 100% trace propagation. What is the impact on your network bandwidth?
Answer: throughput overhead. Every span generated by a microservice must be serialized and sent over the network to a collector. In a deep call chain, the telemetry to business data ratio can become significant. At extreme scale, the cost of the network bandwidth and the CPU required for serialization can exceed the value of the traces themselves.
Senior follow-up 3 the day 2 migration reality. You are using Service Mesh Istio and application SDK OTel tracing simultaneously. Who should be responsible for generating the spans?
Answer: the hybrid approach. The service mesh should generate network spans, the hops between pods, while the application SDK should generate internal spans, database calls, function timing. For this to work, the application must forward the headers received from the Envoy sidecar, or you will end up with 2 disconnected traces for the same request.
Senior follow-up 4 Curveball, your headers are correct. Your samplers are parent-based, yet you still lose traces exactly when a service is under high load. You check the collector and it is healthy. Where is the loss happening?
Answer: the UDP/gRPC buffer drop. A senior engineer knows that OTel exporters typically use a non-blocking background buffer. Under high CPU load, the application may prioritize business logic over telemetry. If the internal buffer fills up, the OTel SDK will silently drop spans in memory to prevent the application from crashing. You must increase the max_q_ size in your SDK configuration.
Pro tip, the trace state baggage.
Use the Open Telemetry baggage feature to propagate business-critical metadata like customer_tier or region across the entire call chain. This metadata is not stored in the spans, but is passed in the HTTP headers. It allows your downstream services to make priority-based decisions like bypassing a cache or increasing a timeout based on the context of the original user at the edge.
The Senior DevOps Incident 83, the Chaos Test Catastrophe.
It is Thursday morning. You are running a routine resilience test using Chaos Mesh to verify that the checkout service can survive a pod failure. You configure the experiment to kill 1 pod every 5 minutes. 5 minutes into the test, your entire Kubernetes cluster control plane collapses. The Kube API server stops responding, all deployments are frozen, and the cluster autoscaler is paralyzed. Your experiment has successfully tested the cluster, but the cluster failed. You are facing a chaos catastrophe where the fault injection targeted the brain instead of the body.
Symptoms, the panic moment.
Here is the behavior of the cluster during the failed experiment. 1. Control plane failure. kubectl commands return the connection to the server was refused. 2. Target mismatch. Instead of the checkout pods dying, you see core DNS and kube proxy pods being terminated. 3. Recursive failure. The chaos engine itself is crashing because it cannot talk to the API server it just helped to kill. 4. Blast radius. All namespaces in the cluster are experiencing pod deletions, not just the checkout namespace. Decision tree signal. If a targeted chaos experiment results in cluster-wide infrastructure failure, then always suspect an overly broad label selector or namespace exclusion failure.
Hypothesis, thinking like a senior.
A junior might blame the Chaos Mesh tool for being buggy. As a senior, I analyzed the blast radius isolation. Hypothesis 1, insufficient master node CPU, ruled out. Metrics showed the API server had 60% headroom before the test. Hypothesis 2, etcd latency, ruled out. etcd was healthy until the mass deletion event started. Hypothesis 3, selector overreach. The chaos experiment was defined with an empty namespace or a generic label like app, engine X. Because the ingress controller and other system components also use those labels or exist in a non-protected namespace, the Chaos Engine treated the entire cluster as a target. To verify this, we must inspect the exact YAML manifest of the Chaos experiment. Investigation, the 6-step resilience forensics.
Step-by-step chaos debugging.
We must find the scope error that killed the cluster. We execute these steps. 1. Recover the manifest. We pull the pod chaos YAML from the GitOps repository. 2. Audit the selector. We find label selectors app API. We check the cluster and find that 4 different services in 3 namespaces use that exact label. 3. Identify the namespace trap. We see that namespaces was left blank. In the Chaos Engine logic, a blank namespace defaults to all namespaces. 4. Trace infrastructure hits. We see the Chaos Engine killed the API gateway pods and the internal DNS pods because they were labeled with API. 5. Verify system protection. We check the Chaos Mesh controller configuration and find that allow system namespace was set to true. 6. Root cause identified, lack of blast radius guardrails. The experiment was configured with a non-specific selector and 0 namespace isolation. This allowed the fault injector to target critical system infrastructure, DNS, and API gateways that the cluster requires to function. The experiment was functionally a self-destruct command. Let us look at the dangerous YAML that caused the cluster collapse. The evidence, the unbounded chaos manifest. This is the most dangerous line in any chaos tool. Without a specific namespace restriction, the engine has admin permission to kill pods in kubesystem, Istio system, and your core security namespaces.
The fix, implementing explicit scoping and namespace protection.
We must immediately terminate the chaos experiment and refactor our policies to blacklist system namespaces from all fault injection. Senior warning: never run a chaos experiment in a cluster where the chaos controller has the permission to modify the kubesystem namespace. You must use Kubernetes RBAC to physically restrict the Chaos Engine service account to only touch specific, non-critical application namespaces. Here is the YAML implementation for a hardened and scoped chaos experiment. Disclaimer: always test code in a non-production environment. By pinning the experiment to a specific namespace, we provide an absolute safety wall. Even if the labels are duplicated elsewhere, the Chaos Engine is physically unable to see or touch the cluster's control plane pods.
Prevention and guardrails, the post-mortem.
To ensure chaos testing remains a tool for stability and not destruction, we implement these guardrails. 1. System namespace blacklist. We update the Chaos Mesh controller configuration to hard code and exclusion of kubesystem, monitoring, and security namespaces, making them untouchable by any experiment. 2. Automatic stop loss. We implement a health check for our experiments. If the cluster-wide 500-level error rate spikes by more than 5%, the Chaos controller automatically pauses all active experiments. 3. Game day shadowing. We mandate that any new Chaos experiment must be run for 24 hours in a shadow mode where it only logs what it would have killed before it is allowed to perform a real injection. A senior engineer knows that you must prove a system is resilient before you try to break it. The senior follow-up stack.
Senior follow-up 1 mechanism deep dive. How does a chaos engine like Chaos Mesh physically kill a pod? And how does it differ from a standard kubectl delete?
Answer: most chaos tools use API level or CRI level intervention. A pod failure action often uses the Kubernetes API to delete the pod. However, more advanced network or IO chaos uses sidecars or eBPF to intercept system calls at the kernel level. This allows for partial failures like 10% packet loss, which are much harder for applications to survive than a total pod restart.
Senior follow-up to the scale and trade-off trap. You decided to run continuous chaos in production. What is the monitoring noise trade-off?
Answer: alert fatigue. If you are constantly killing pods, your standard liveness and readiness alerts will fire 24/7. You must implement chaos-aware alerting where your monitoring system ignores expected failures during an experiment window. The trade-off is the risk that a real failure happens during an experiment and is accidentally ignored.
Senior follow-up 3 the day 2 migration reality. You are moving to a serverless architecture Lambda. How do you perform chaos testing when when you do not own the infrastructure?
Answer: application-level fault injection. We use libraries like Chaos Lambda or AWS Fault Injection Simulator, FIS. We inject code that artificially increases the latency of the function or throws random exceptions within the business logic. We test the timeouts and retries of the calling services rather than the health of the underlying server.
Senior follow-up for Curveball, your experiment is perfectly scoped. It only kills one pod in the checkout namespace. Yet the Cube API server still crashes. You check the master nodes and find CPU is at 100%. Why did killing one pod crash the control plane?
Answer: hidden cause, the watch storm. A senior engineer knows that if 10,000 internal services have an open watch on that specific pod, killing it triggers 10,000 simultaneous notification events from the API server. If your cluster is over-provisioned with watchers, the simple act of a single pod restarting can trigger a control plane DDoS through event serialization. You must tune your API priority and fairness settings.
Pro tip, the steady state hypothesis.
Before running any chaos experiment, you must define your steady state. This is a measurable metric that represents normal. For example, checkout success rate is 99.9%. If you cannot define and monitor your steady state in real time, you are not doing chaos engineering. You are just breaking things in the dark. Your experiment should only continue as long as the steady state remains within its defined guardrails.
Category 16 wrap-up, the sovereignty of the fleet.
Category 16 has taken us to the absolute edge of DevOps engineering. We have seen that managing a global fleet of clusters requires more than just automation. It requires an understanding of eventual consistency in the control plane and the fragility of cryptographic trust. We learned that XDS propagation is a race against scale, and that MTLS rotations are a dangerous dance of overlapping routes. Finally, we saw that chaos engineering is a powerful medicine that can become a poison if the blast radius is not mathematically isolated. A staff-level engineer knows that as the system grows, the management of the system becomes a more significant source of failure than the application itself. True resilience is built not by avoiding failure, but by intentionally and safely mastering it.
Part 2 wrap-up, from the kernel to the global mesh.
In this second volume, we have descended into the ghost in the machine. We have explored the physical limits of the Linux kernel, the distributed logic of database consensus, and the hardcore performance engineering required to survive at scale. We have moved from simple pipelines to the complex physics of the cloud. You have now completed the most comprehensive incident forensics course in the industry. You have developed the senior-level intuition to diagnose the silent packet drops, the stale read mysteries, and the thundering herds that keep the world's largest platforms awake at night.
Final conclusion, the senior DevOps mindset.
This concludes our two-part masterclass on 83 real-world DevOps incidents. We have covered the entire stack, from management leadership to kernel abyss. Remember, being a senior or staff engineer is not about knowing every command. It is about having a systemic decision tree that allows you to remain calm when the metrics lie and the logs are empty. It is about building guardrails that make the wrong thing impossible and the right thing automated. Use the debug framework, test your assumptions, and always look for the architectural cause beneath the technical symptom. Watch Part 1 again. If you missed any of the platform and automation foundations, click the link in the description or the end screen to watch Part 1. Mastery is a result of repetition. Go back, solve the curveballs.
The universal interview tip. Whenever you ask a tech VP or an industry mentor how to crack a tough interview, they all give you the exact same tip. Get familiar with the most commonly asked interview questions. It sounds simple, right? But here is the problem. The search nightmare. Finding the actual most commonly asked questions for senior roles is a nightmare. Generic Google searches only give you basic textbook definitions, and those will not help you clear a lead architect or senior engineer round where production reality matters. Imagine a master vault. Now, imagine a vault where the absolute most commonly asked interview questions for your specific role are already collected for you, perfectly organized by interview rounds like 1. Most commonly asked technical-based question and answers. 2. Most commonly asked scenario-based question and answers. 3. Most commonly asked real-world problem-solving question and answers. 4. Most commonly asked system design question and answers. 5. Most commonly asked behavioral-based question and answers. Cross-domain mastery. I built the ACE Interviews Master Vault for the modern architect. We did not just do this for one role. We covered everything: SAP, cybersecurity, DevOps, software testing, data engineering, Java, and Python. The ultimate all-access deal. Instead of paying for individual PDFs, you can now unlock our entire database. Get over 1,000 plus PDFs containing 50,000 plus of the most asked question and answers for a mere 1,499 rupees a month. The elite transformation. Stop studying just to pass. Equip yourself with the cross-domain confidence of a true architect and walk out of your next interview choosing between 2 or 3 elite job offers. Unlock the vault now. The era of buying individual guides is over. Click the link in the video description below right now to unlock the Master Vault. Now, let's get back to the masterclass.
For more exciting tips, tricks, and more importantly, for valuable insights of interviews, please share, like, and subscribe to my channel. It has a lot of valuable information about various insights of interviews. It has a wide range of real-world portfolio projects of various technologies for interviews, and it has wide range of most asked interview questions and answers of various technologies like data science, SAP, AWS, DevOps, and full-stack web development, and more. That will be useful during interviews. It has a wide range of most asked interview questions and answers and real-world portfolio projects of various technologies for freshers. For 2 to 3 years, experienced candidates, and for 5 or above years, experienced candidates to test their skills by knowing most asked interview questions and make themselves ready for interviews.